So good morning, everyone. Welcome to this 199th edition of the Zak World of Façades conference series. My name is Ahmed. I'm part of the organizing team here at Zak. I'll quickly introduce the conference series for those who are attending this for the first time. So we've been organizing the Zak World of Façades conference series since 2012. This is our 7th edition in Canada, our 3rd one in Toronto. We've had 2 editions in Montreal and 2 editions in Vancouver. And we've got events from here until New Zealand. So it's a big portfolio of events which we have. 47 countries, to be precise, is where we've organized these events. The way facades are designed, engineered, installed in different regions are completely different. The Western world is more about sustainability, about carbon reduction. The Middle East is more about giga projects. Asia Pacific is more about cost control. So every event is curated to that respective region, and we grow from strength to strength, taking learnings from one region and then bring those to another region. So it's a wide spread of events. We went to places we never thought we would ever go. We went to Uzbekistan, we went to Georgia. I mean, these are places where we've never had a facade conference ever in their life, or don't even have facade engineers, or facade engineering is in a very, very nascent stage. So for us, it's been a fabulous challenge in doing these events in different places. It excites us. Today is all about storytelling. Every speaker of ours has a story to tell about their project or their product. And this is what we keep doing around the globe. So this is our 199th edition. Our 200th edition is in London on the 5th of November, which is actually our largest event in the series, close to 1,000 people with a gala awards dinner. So this is what we keep doing across the globe with these events. Let me just adjust this. And I think today's agenda is a reflection of that. We've got new topics from the last time around when we were here. It was around 18 months ago. May 2024 is when we had the last event. So we have people from inside Canada as well as overseas who would be talking about their stories in designing, engineering, installing facades. These events are courtesy our event partners. We have 47 of them, so I'm not going to explain what each partner does. I'll probably just start with our presenting partner, Reynears. So Reynears, if you see, is omnipresent across this conference series here in North America and at today's event. So Reynears is a Belgian company. They are into aluminium, door, window, and curtain wall systems. They've been present in the Canadian market from quite a while, and they've been growing over here. So they are our presenting partners for this event. And then I'll quickly introduce our 47 associate partners. All of them have a tabletop booth, so please do meet them during the course of the day. So this event is recorded, so you can watch the recording of this event post the event. So even if you're networking with them, if you miss any presentation, you can see the YouTube link. Of course, a couple of presentations we've been asked to blacklist because of the confidential nature, so you will not find them on the YouTube recording, but you'll find most of the presentations on the YouTube link. So we'll start with Eternia, which is a brand of Anatolia, AFC, American Fiber Cement Cladding, AGC Interpaint, Air Out Shield by SRP, Alucoil, Amico, Bothwell Accurate, Cosentino, Dry Design, EOT, Engineered Assemblies, Innova, Equitone, Euramax, Euro Architectural Components, Exterior Technologies Group, Fassada, Fit Anchoring Systems, Glass Curtain, Glass Wall Systems, Guardian Glass, Django, Jansen, Kalebodur, Lumon, Mitrex, MSI Aesthetics, Northern Facades, Nortech, Ontario Panelization, Autocompu, Thermafiber, QDP, Rigidized Metal Corporation, Rotoblas, RWDI, Weiss, Siderice, Sound Solutions, Technical Building Products, Taiwan Glass, Tonality Facades, Yukon Systems, Unity Wall, Viracon, Vitro, Walker. These are our 47 associate partners and our main presenting partner. As I mentioned, all of them have a booth outside, so please do visit them. It's a wide range of products we have, from unitized panels to range screen systems, to clips, to membranes, you name it. I think we've got the biggest portfolio of products. We had 19, I mean, this is the growth we've had in Canada. We had 6 in our first edition, May 2022. We had 19 in May 2024, and we have 48 now in October 2025. So a wide range of products for you guys to explore. A quick glimpse of our 2026 North American events. At least for Canada, new would be Calgary, so that's another place we want to go and explore. We return to Toronto again, so we'll make the Toronto event an annual edition. We come back to Toronto this time next year almost. Vancouver is in May, and of course our debut in Calgary in April. So these are our events in Canada, and of course we've got a few events in the United States also. So this is what we keep doing. We bring people to tell stories together and make all of you meet together. We have a lovely expo display, which I urge all of you to go and meet our exhibitors. And yeah, I think my role ends here. I'd like to call upon today's event host and convener. He's going to be taking you through until the end of the day. Yeah, just before I end, there was one more slide, Arjun. This is a new version. Right. Okay. Post the event, we have a magician and a stand-up comedy actually doing a small act in the exhibition area for around 30-40 minutes. His name is Gambit. He's a self-proclaimed second funniest magician in the Greater Toronto region. So he's going to be performing over drinks and reception at the end of the day. So if you're staying back, please do get entertained by him. I had a slide about him, but I don't know where it's missing. But he's going to be performing post the event in the exhibit area. So can I call upon Diamant? He's a principal at Teeple Architects. He's going to be leading you through until the end of the day. Thank you very much.
Good morning, everyone. So thanks, Ahmed, for that intro. And yeah, great to be here. Good morning, everyone. As Ahmed mentioned, I'm the convener, the MC, maybe glorified timekeeper is a better way to put it for today. Yeah, so for today, I just have some quick housekeeping notes, and then we'll get the show on the road. So we have 2 coffee breaks and a lunch hour to network and engage with exhibitors in the expo hall. It's a great opportunity to see the materials up close, and we thank them for their support today. If you'd like a certificate of completion for OAA, AIA credits, there will be a sign-up sheet at the end of the day at the registration table, and you must sign up on the sheet to receive either. We ask that speakers for each session return to the stage at the conclusion of your session for a quick photo op and a thank you from Zak. And the venue kindly asks you not to bring lunch into the forum ballroom. Drinks and coffee are okay. So, yeah, I'm actually intrigued to hear that there's a stand-up act and magician, and I'm quite relieved actually because I was gonna start the day with a tight 5 comedy routine on facades, and then I realized I'm not a comic, but I thought at the very least I could come up with a really terrible, awful, embarrassing, cringy, facade-based pun. But you know what? Our program today is so riveting that I think we should just get right into it. Sorry. Okay, so without further ado, we'll start with the first of our 4 sessions, and I'd like to introduce our first presenters for the day. Lilia Koleva, partner at NEUF Architects, and Marco Chow, senior architect at NEUF Architects. Thanks.
Yeah? Okay. Perfect. Thank you. So, good morning. Thank you, Tobiasz, for the introduction. Thank you for having a full room. I'm surprised at 9 a.m. that we were able to get everybody here on time. So, we'll start by, I was already introduced. My name is Lilia, and I'm a partner at NEUF Architects. We are Montreal-based firm originally, but the last 10 years, we've seen a lot of growth in Toronto, and I'm the partner in charge of our Toronto office. And with me is Marco, senior architect at NEUF as well. So what we wanted to share today is a typology of a project that we don't often see in these types of presentations, but it's something that is a big market for NEUF, and it's a growing sector for us. It's airspace architecture. So when we think of airspace architecture, where's the clicker? This is the clicker, right? Yeah. Okay, when we think of airspace architecture, we often think of an industrial box, and a lot of people just equate it to a Costco box or a warehouse, and I could sincerely share that there's almost nothing in common between an industrial box and an airspace building. First of all, it's, for example, the project that we would talk about today is for over 2,000 people in just one shift. So when you think of the scale of the project and that this is a home to what people call, you know, their daily environment, it's comparable to a lot of other workplace types of spaces we create. And then there is the scale that you have, the human scale, the employees, and you have this big aircraft inside that is getting assembled. So it needs to be functional, efficient, it needs to feel like a community, it needs to be environmentally comfortable as well. So I'll go into the next, so we went through these. So the project that we would go through today is the Global Manufacturing Center and the fuel test hangar for Bombardier at Pearson Airport, which our team completed in 2024. So in May last year, it was completed, substantially completed. It comprises just under 1 million square feet, 2 main buildings, and it was done in collaboration with Bombardier and with Stantec for all of the engineering. NEUF was the lead architect and interior designer. So how we got to the site? So historically, Bombardier was operating at Downsview, and it's a site that's currently under redevelopment as well. So the move was being made from the Downsview, where there were 336 acres, to about 41 acres at Pearson. So a very substantial reduction in the footprint of their operations, while increasing also the efficiency and the output of the operations. And one of the things that they asked us to do is to create a comfortable, human-centric environment that is extremely efficient and highly sustainable. That was the kind of the constraint. So what this diagram here shows, it was the complexity of the project. So we started in 2019, just before COVID, and we were ramping up. We had 17 binders of detailed requirements from, you know, extraction of processes inside the building that had to be brought to the exterior, all the way to, you know, oil containment spills that we needed to contain within the floor slabs. So we were ramping up to the project, and then COVID hit in beginning of 2020. So over 100 people that we were collaborating with, because the team was quite large. Just on the architectural side, we were over 32 people, 32 architects. We had to move to a digital environment and do that all remotely. So the meetings were done remotely, the work was done remotely. You could see kind of in the diagram here, the amount of effort, how, you know, by 2020 we were really at the high point of dealing with the design. And then I heard that South Asia usually talks about cost. Well, in 2020, when COVID hit, when there was so much uncertainty, cost and supply chain became a big topic for us for this project, where we would get all of the materials that we need to build this building with slated construction 2021. And we had no flexibility in the schedule whatsoever, because Bombardier had to move out of Downsview by 2023, 2024. And continue uninterrupted operations. So I'll go now into the elements that affected the facade. So what are the elements in terms of site and code regulations? So the first thing here, I don't know if I could point. Oops. Okay. I don't know where the pointer is, but the site is right here. You see the runway. This is runway, the busiest runway in Canada, 0523. And our site, I don't, is this the big one? I won't try because I don't want to. The site is just here at the end of the runway. So we were usually, when we think of, for example, of an aviation project, we're quite far. You could see the terminal building at Pearson Airport. It's quite far from the active runway. We were actually very close to the runway in this case. And we had to comply with a number of requirements related to construction near an active runway. And funny enough, by the time we were starting construction, the world was reopening after COVID, so we actually didn't benefit from the downturn on aircraft movement. So the site being about 750 meters, almost a kilometer along the runway, also presented an amazing opportunity to do something quite unique in terms of presence on the runway, visibility to the project. And we took full advantage of that. So going to the next. So this is the site. Now you could see it in more detail. So it's a very irregularly shaped site. We had to work within the constraints of the offsets from the runway itself. And we only had 3 touch points to what we called ground side, or the city of Mississauga roads. So we had constraints on one side in terms of runway, and on the other side, all of the in points. So how we ended up designing it is, so you see here at a very kind of high level approach, what would be normal on this side is the typical manufacturing hangar. And this is what Bombardier had at Downsview. And that's a very common typology, generally speaking, where you have the production is a linear production with offices along the linear side, and you have about 40% of the offices and the environment actually getting no natural light because you're lining up the offices on one side of the production floor. We designed instead a building that is a U-shaped production line organized around the module of an aircraft, which is about 40 meters by 40 meters. And we were able to demonstrate a much higher level of natural light and windows for all of the offices. And one thing I need to mention here is that we had over 120,000 square feet of offices, material labs, testing labs, so all kind of high-end, state-of-the-art facilities that many of them required natural light. So we were able to go roughly from a typical 40% natural light penetration to over 70% by just the massing and the approach to massing. So this gives you an indication a little bit of how it was shaped and how the material flow worked. So you have the runway at the bottom, and then you have 2 production lines within the primary manufacturing center. And then on the other side, once the aircraft is out, we call it gets to a weight on wheels, and then it gets wheeled out as an unfueled aircraft. It gets fueled, takes its first flight, and then it gets its number of flight testing operations in the flight test hangar, which is designed as a fueled aircraft. And Marco will talk in a minute about all of the issues we had with some of the envelope challenges. Okay, I'm going to keep an eye on time. So the contextual thing, what I was mentioning earlier, the reason this is an important consideration in these types of facilities, because every facility in Canada will have to comply with the so-called obstacle limitation surface. So it's similar to an angular plane in any of the city projects. But the constraint here is that it's not only that you need to meet the angular plane, this OLS line in the ultimate build, you have to meet that line during construction as well. So you can't just put a crane and go within the within the OLS penetrated, you need to get special permits from the Airport Authority and from Transport Canada to be able to construct it. So that had an impact on our schedule. We had to ask for night shifts, closure of the runway in order to be able to construct, which obviously for an envelope, we were trying to close the envelope as quickly as they can, had a huge impact. So one thing, you know, one day when I retire and I have time, I would want to do research on how we could build these types of facilities in an efficient way, because right now when we think of envelopes for these types of buildings, we think of insulated metal panels, tilt-up panels, and precast. Like, you know, is there some other form of envelope structure that would allow you more light penetration, for example, is a big conversation in my mind that needs to be had for these types of facilities. So this is an example of the process. So to give you an appreciation of the level of complexity. So the bottom graph is we had to submit to Transport Canada and NEUF Canada every extreme coordinate of the building. So first of all, unfortunately, we had no choice but to go with many setbacks in order to hit this OLS line. And second, we had to give all of the coordinates for each of those extreme points. And we had to do that for construction and for the ultimate build. And we needed to say how, like what type of equipment would be penetrating the OLS at any given time. And then from here, we would go into some of the unique challenges that were part of the process, and Marco will take over here. Okay. You can take it.
Okay. Thank you, Lilia. I'll continue with a couple of examples of key elements that impacted our design and the envelopes. So the main building cladding assembly for the Bombardier Manufacturing Center here comprised of two systems, mainly insulated metal panel with translucent panel integration and curtain wall system. So the concept was to have a building envelope that would be energy efficient, quick installation to meet project schedule, and an aesthetic appearance that can be maintained throughout, despite of the many specific program needs. So an example of that, what you see here up on the screen is the blast panels. So due to the hazardous materials that were contained behind the panels, we had to allocate a specific area in the facade that is able to be disconnected from the main structure in the event of a blast. So working closely with the structural engineers and the IMP suppliers, we engineer the connections and the tether system with strand cables to be connected to the standard IMP panels. Then the blast panels would then only be released from the subframing when the pressure exceeds 100 PSF. So here's an elevation and section detail showing that system. So in the event of a blast, then the direction of the blast would then be controlled. Finally, the human aspect of the facility. While such projects are often categorized as industrial, this facility is not just about manufacturing. Like Lilia said, it's a workplace for over 2,000 people in one single shift, and the design needed to merge the two scales. The immense scale of aircraft production, requiring clear spans, high ceilings, and large open areas, and the personal scale of human needs, like intuitive navigation, reasonable travel distance to restrooms, for example, and well-lit workspaces. So daylighting played a critical role in the concept of human-centric design. We used vertical translucent panels in the facade for wayfinding in the shop floors. Single bands indicating exits and 3 bands indicating a natural light source, allowing workers to navigate the vast space intuitively. Allowing clusters of office spaces were positioned to maximize natural light for both offices and production areas. The result was a facility with over 70% of spaces benefiting from natural lights, almost doubling the traditional benchmark of 40%. Here's an exterior view of a typical seamless IMP integration with translucent panels. A view of the interior shop floors benefiting from access of the natural light through the translucent panels. This critical principles of daylighting and human scale design continue through the use of translucent fabric for the large aviation doors. These hangar doors on the self-elevation represent over 55% of the facade on the self-elevation, illuminating the entire assembly shop floor. So here's an image of the larger of the many aviation doors, spanning 75-meter across, clear span, and there's 2 of them. So when the aviation doors are opened, the view completely opens up to the runway at the airport, blurring the interior and exterior work environment, also offering a glimpse of the aircraft assembly operation when you're on the runway, taking off. View from inside of the hangar with workstations on the shop floors. And this principle of daylighting is also carried through into the interior office spaces. Where spaces did not have access to exterior, we utilized large LED backlit translucent ceiling panels to mimic daylighting strategies. So I'll jump to the next sections, which talks about some of the 3D integrated shop drawings that we were utilizing for this project. So even though the building massing is rather simple and the facade assembly is limited with fairly standardized details, 3D shop drawings were still instrumental in identifying issues and clashes while early in the design phase prior to steel fabrication. This was especially important for us, understanding we had over 9,000 tons of structural steels that was required for the project and that we had to coordinate. So in the case, the steel fabricator provided us with the Trimble model, and we used that as an opportunity to see every structural elements and connections that make up the superstructure and the subframing for the facade. Our team then further integrated the 3D shop drawing models and linked it with the architectural live models. So it allowed us to see basically live of the shop drawings versus our models and quickly able to communicate those clashes, whether that's steel locations for facade openings or the HVAC distribution and overhead clearances, which was critical for the operation. So this is a sample of the live Revit model synchronized with the steel fabricator shop drawings, highlighting the various clashes in colors for different types. So in addition to the 3D shop drawings tools, there were other communications tools and design that we had used from the start of the project through construction that were critical to the success of the project. As mentioned earlier, this project kickstarted at the beginning of the pandemic, so there wasn't really sort of a blueprint to follow for virtual project coordination. So having integrated tools allow us to flag issues and resolve them with the contractor in a timely manner. Expect the unexpected. So with every project, there are often surprises, in particularly with site conditions that we all may not have been expected. So something that we obviously didn't expect related to facade was the plant growth that we had encountered along the bottom edge and expansion joint of the fire-rated IMPs comprised of the mineral fiber. All of a sudden, we had, walking for a site visit, we had a green wall along almost half of the northern elevation of the flight test hangar. So working with the building science engineer, it was determined that the panels cannot be stored unprotected in the elements prior to installation, where then the panels were contaminated with plant spores and possibly some dirts collected in the mineral fiber, creating a suitable substrate for plant growth. So to resolve this, we had to eliminate one of the following factors: water, fresh air, suitable substrate, or the spores. As the air cannot be managed within the wall system, then that leaves to water as a primary factor that we had to eliminate. So this was where we found the plant growth exactly occurring in areas where the sill flashing wasn't installed flat or negatively sloped, restricting the drainage, contributing to the plant growth. So at those various locations, the remediation process we had was to open up the IMP to remove the plants and the molds that had been built up over time. The adjustment had to be made in the IMP finishing trims and steel angles supporting the IMP to allow for the positive water drainage. The second one is the IMP shimming. So that's another example of a facade example that we did not expect to have occurred. So in the case of this project, it was critical to maximize the length of the IMP envelope, to minimize building envelope joints, to speed up construction. However, using longer span panels also meant there's tighter tolerances, requiring each of the supporting horizontal steel girts to be on the same plane and columns to be vertically plumbed. As structural bays were, this stringent tolerance was not met. Additional shimming angles at various depths were required to make up the gap difference between the panels and the structural steel. Here is a section detail showing that the shimming angles details requiring at the foundation, the intermediate sections, and at the top of the panel, all varies between 3 millimeter and up to 150 millimeters. The takeaway for this is that understanding of the envelope systems and its tolerance and its limitation is critical, and that we'll highly recommend to be conveyed at the beginning of the project or, and with the various subcontractors. So just to wrap up the presentations here, a couple of images from the Bombardier facilities following occupancies. Thank you.
That was great. Thank you, Lilia and Marco, for a fascinating presentation. Yeah, I really appreciated that, seeing the typological innovation and the human-centric considerations about the workplace. And you know, I really appreciated seeing an angular plane that kind of makes sense, as opposed to what we're typically used to seeing here in Toronto and other contexts. So our next presenter, Brian Hubbs and David Stanton from RDH.
All right, well, while we're getting the AV set up, my name is Brian Hubbs. This is my colleague, David Stanton. We're here to talk to you today from RDH Building Science about choosing the right facade for an iconic building. Excellent, guys. So, a little bit of a disclaimer, legalese I'm required to show, and now on to the presentation. We're gonna go quick. We're gonna take any breaks, even to breathe. So, really, when you build a building, right, first step, concept and form, energy optimization, and then you choose your facade typology, and then you get into working drawings. And that selection of just choosing what you're gonna draw is the thing I'm gonna talk about today. And that's where we come in usually. The first time we get to see the building is a cool rendering, right? Zianko Design, they were playing around with AI, they crumpled some paper up, said make a building. This is what I'm given. It's like, Brian, make this work, draw the details. It's like, well, what are we gonna use to draw the details? And if we start to think about what we're gonna use, how much is it gonna cost, and how much risk are we gonna take, and all those things. So you wanna set it up so that what you're drawing eventually is the thing that's gonna be used. You don't wanna go back and forth. You don't wanna start drawing something that ends up being too expensive, and your client says, no, we're tendering it out. We got prices for this thing, and it's totally different, and you have to go back and redo all your drawings. So we wanna get in there, get it right the first time, get the drawings done right, build the building, get out of there. So it's this little red box, I call it. It's the red box between the magic that occurs at an architectural firm, which I feel is magic as a structural engineer. By training, it's magic. You come up with a form, you blend it into the landscape, you draw it, it's amazing. It's Kengo Kuma's first sketches from Alberni. And then we have to decide how are we gonna build this? What are the nuts and bolts that we're gonna use so that we can put together a package that we can tender out, okay? And so it's this red box, and this red box often gets missed, right? Because in a normal building, if it's just a standard office building with glass and spandrel panels, you don't need much of a red box. You could use any system, and it's just a question of how much do you want to pay for it, Costing is going to be pretty accurate. What do you want it to look like? It's pretty simple. But on an iconic building, which is what we're talking about today, this is really important, right? Worked on buildings that have been $50 a square foot for this facade. I've worked on facades that are $800 a square foot. And when you go iconic, that's the range that you can choose from to make it work. So we want to make sure we're on the right, we're near the bullseye, near the start. Right, so the first thing we do is some parametric energy modeling. So we look at all the possible ways that we can achieve the energy and the carbon, CO2 gas emissions and embedded carbon emissions in our system. So we look at many different ways to do it, all the possible ways, and then we start looking at what those mean. We pick a couple of them, right? It's too complicated to read, but you get the sense. There's lots of different options, right? This is one here with a really good center wall value, like a big panel, like maybe speed wall or something like that, with any window you want, because the wall's so good you can use any window you want. So there's a good combination. Key is, can you use a big panel on your building? We don't know. If you look at the previous building, Alberta, you can't use a big panel. Everything's bespoke, in a 3-meter zone. Okay, another option you can use, here's another option. This is the mega panel option here, where you got mega panels and you've got punch windows. Previous option, it was more curtain wall, conventional curtain wall. So you have less window to wall ratio allowed. You got to blend all this together, and you hit your targets. All right. So the other thing you got to worry about is that once you think about performance and you get a bunch of ideas on how you're going to meet that performance criteria, and you run a parametric analysis, you got to include some costing, right? So you select your options and you kind of run them, and you go, okay, how does the effective R value, what's the cost per square foot of all these different values? And you can kind of look at them in increasing R value, and you can see these big inflection points. That's probably where you're going from window wall to curtain wall, or maybe curtain wall to mega panel, or using quad glazing instead of double glazing, right? These are big inflection points, right? And if you're here, there's a good discussion to be made with your mechanical consultant to be here. Is there anything that can squeeze a little bit more economy out of our mechanical system that can reduce our envelope price by $2 million or $3 million, right? So these are all good conversations to have, and your optimization is not 2 silos. It's not mechanical, and it's not electrical, and it's not enclosure. At this point, you got to get together and figure out the best system for the building, right? And so those inflection points are really good to know. You got to have good costing for that. And like I said, what do you use? You can't just use a standard cost database for means, because it could be 50, it could be 800. It really depends on what you choose. Okay? So, now that we've got a system that meets our clients' objectives financially, meets our objectives from an energy standpoint and from a carbon emissions standpoint, we're looking good. Now we've got a couple options to get there, right? We know the energy performance. Now we have to look at the actual building and how the building is going to move and how complicated the building is. We can choose window wall, we can choose curtain wall, and we can choose big panel systems for these kind of buildings. We can also choose regular windows, but iconic buildings aren't typically done with standard windows. So here's some examples here. You've got curtain wall, window wall, site-built windows, so stick-built curtain wall, and large panels. So these are the kind of 4 basic typologies that we're going to choose from. Some of these can work on every building. Some of them shouldn't be used on some buildings. Some of them are much more expensive as you get to more complicated buildings. And you got to know that, and this is sort of why we're talking here, is to try and get everybody thinking about these things before we draw them.
So just looking at how buildings move, right? So we're looking at inner story drift right now. A lot of people look at that moving image and think, oh, that's an earthquake. Could happen with wind too, right? So we're gonna have, buildings gonna move regardless of whether or not you got an earthquake. We've got kind of 2 levels of inner story drift that we're looking at. We've got an elastic and an inelastic. That elastic one is really, we gotta be able to take up that movement, and the facade still gotta stay air and water tight, right? In Toronto area, that's usually governed by wind. Until you hit a post-disaster building, then you're looking at a service earthquake that does exist in the code. Inelastic is the big one, right? Big earthquake. Really all that we're trying to do is make sure nothing falls off the building because we got bigger things to worry about by then. And thinking about it in 3D, right? You're gonna have it going side to side and it's gonna go in and out. So that really comes into play right at the corners. We also gotta think about vertical movement, right? We've got deflections, we've got creep, shrinkage from wood, and that's all gonna shift our facade down if we're, hanging it or bearing it on our structure. So we gotta be able to take that up without obviously staying air and watertight and without anything falling off or getting damaged. So quickly, iconic building facade types, right? Pretty much everything falls into a unitized curtain wall or window wall. Even these mega panels kind of fall into some form of this. It's either on a curtain wall chassis or it's hung or bottom bearing similar to a window wall. So curtain wall, unitized curtain wall, we hang it from the top, right? It's gonna fly by our slab edges. So it's like a curtain over the building. Our window wall is just gonna go bottom bare right on our slab. It's gonna have a slab bypass panel that's gonna cover that slab edge. And then it's gonna be restrained at the top from wind. Just quick glossary terms for anyone that maybe doesn't know these. So the curtain walls we've got at the top, that anchor, that's what's taking your gravity load. Like we said, we're hanging it from the top, so that's where your anchor is generally. That'll be the gravity anchor. Then you got the stack joint right at the middle. That's gonna take that wind load, stop you from going in and out. It's also gonna allow for that movement up and down. And then you've got your lifting lug. That's really just how you're picking it up and putting it in place. Window wall, so like we said, bottom bearing, so we're gonna have it shimmed and we've got a sill angle at the back there. That's gonna take that wind load at the bottom. And then you got a deflection header that's gonna allow the up and down, and it's gonna stop it from getting pushed in, rotating. So is this window wall or curtain wall? That's kind of classic curtain wall, right? And then window wall, curtain wall, we're back to window wall. So again, classic window wall. So the facade generally takes up movement in three kind of different ways. We've either got racking, which is essentially gonna deform your panel, or this is how stick-built curtain wall generally moves, right? You deform and the glass slides inside of the mullions. And then you've got rotating, pretty simple. The whole panel is just gonna rotate as the slab moves. And then translating is just gonna slide along the slab, right? So curtain wall, unitized curtain wall generally is gonna rotate, and then your window wall is generally translating. Where this gets tricky, especially with translating, again, that corner. As soon as you hit a corner, it doesn't wanna move anymore. So now it's maybe gonna have to rotate, or we're gonna have to figure out how to take it up in that corner. So it gets tricky there. It's just a quick example of a window wall translating, right? So we've got to take up that movement in the corners. This has got a separate piece in the corner that's going to allow for that extra movement, and it's going to rotate. That corner piece is rotating to take up that movement. This is a translating curtain wall. This one's actually got bolt-on balconies that it'll just ride with the curtain wall. Same thing, rotating corner. And your window wall is translating, or your curtain wall, sorry, here is translating.
This is a mega panel.
Yeah, this one's a mega panel. And then this is classic rotating curtain wall, right? So it's just rotating. You can see that corner getting pretty close at the back, and then at the front here. If those clash, right, you could have breaking glass, you could have damage. It's not quite hitting, so it's actually good. And then this one's kind of got all of it. This one's got racking, we got rotating, we got translating, right? This one we'll get into a little bit more later. And then for the big one, like we were saying, all that we're really caring about is that it doesn't fall off the building. So this damage, we've got damage to some of the anchors, we've got damage to that corner, and we've got some, cracks in glass and stuff. That's all okay, as long as it doesn't fall off the building. Again, that's from that inelastic movement.
All right, so that's all great, and now that's nice and simple. We've figured that all out. Now let's add a bit of complexity. So we'll make our building more iconic by adding some balconies. We add a balcony. It's pretty simple with window wall, right? We just leave the window wall portion of the slab band bypass out where the balcony is. Doesn't affect the system. It's not even penetrating the system. The system's installed around it. Works really good with balconies, right? Whereas if you have curtain wall, you have to punch through the system. The curtain wall is hanging outside your building, so somehow you have to punch through it to make your balconies work, okay? So when you have curtain wall at balconies, you introduce quite a bit more complexity. Window wall is not so bad. It's meant for that. Curtain wall, you have complexities. So you can hang it, right? And then at your balcony, you can align the stack joint, you can offset the stack joint, or you can bottom bare everything, okay? And the best way to do it, just spoiler alert, try to align the stack joint so it runs all the way around the building at the same level, and you're not jumping it. We call it jumping the stack. Every time you jump the stack, you increase complexity. Whenever you increase complexity and in field installation, you increase cost. Costs more to make it, costs more to install it, and you take higher risk. So this is the way to minimize that. You don't have any of those. You run it all the way around the building. It works great, especially if you have curbs at balconies, which we do and you guys don't do. So in Toronto, you're gonna drop that at least at the door to get a accessible threshold. But that door is under a balcony above. It's protected from rain and water. Works pretty well there. So you're basically just aligning that stack, dropping your door down, putting it in. That's nice and simple. That's your lowest risk, lowest cost option, and it's highly recommended. It's one of the first things I recommend. You jump the stack, and now at the edge of the balcony, where it's the wettest, where the water's flowing off, you're gonna change the curtain wall where it moves, and you're gonna step it like this, and you're gonna have some vertical differential movement there. Increased cost, increased complexity. There are systems out there that do a better job than others, that are easier, but nonetheless, adds cost, adds complexity, adds risk. So this is a window wall system at a balcony, nice and easy, goes around the balcony, works good. Oh, sorry, this is a curtain wall system at a balcony that we hang from the slab here, that's sitting on the slab above, and you can see the clear problem right here, right, where you've got that differential movement. There it is. Now let's increase complexity more, make our building a little more iconic. Let's randomly offset the balconies, so now they're not in a stack. That becomes really complicated, right? So there's a good example of a more complicated project with offset balconies. So now you don't have overhang protection over all your doors, the one story above, so they're more exposed to water. And then how are you gonna do it? Are you gonna hang hang the curtain wall here in between, and then stack this? Then what do you do here? You have to hang it off the slab. So now you have a ton of complexity. On this building, the curtain wall manufacturer from Turkey, he said, I'm gonna do something pretty special here. I'm gonna run a band all the way around the building that's attached to that slab, and then I'm gonna bottom bare everything above that. So each floor now gets 2 pieces installed. Brilliant solution, very expensive solution. If he had to recost that now, it would be probably twice as much as he costed it at, because you have to install things twice. You have to install a slab band, and then you have to install the curtain wall above it. That makes it almost twice as much to install, but that's actually more than twice because that slab band has to be aligned and rotated, and so the anchors and everything else are very, very expensive. So this is our Franken mock-up, where we're doing everything. We're rotating, we're racking. We managed to get it to work after about 3 tries, because he was developing a brand new system here. But net is much more risk, much more installation time, and much more cost to do something like this. And it doesn't look like that when you step back and you're just looking at a building, you know, and then you're just thinking, how much is it gonna cost? Well, this would be, if we did it again, probably $200 a square foot. Don't do it. Now let's add a bit more complexity. Let's bolt some balconies on. So bolt-on balconies can reduce complexity and they can increase complexity depending on how you do them. So there's a building here we did with bolt-on balconies, right? Concept is curtain wall with bolt-on balconies. Great. How are we gonna do that? We're gonna leave a hole. We're gonna have an anchor through there. We're gonna bolt the balconies on after. That's gonna work pretty good. It's gonna be pretty low risk. How the contractor actually did it. Built half the balcony, bolted it on. Oh wait, now we can't get the curtain wall in. So we have to bring the curtain wall to site unfinished, put it in, finish it on site, so site finish the curtain wall, and then go back and fix the balcony. So this ended up costing a lot more and adding a ton more risk. Extras like this, right? This is the window wall job, and this job is all window wall. There's no penetrations through it because all of the cool stuff, the iconic stuff, is bolted to the balconies. So bolt those to the balconies, paint them, get them all done, put the window wall in from the inside, works great, right? Much more difficult to do this kind of thing with curtain wall because curtain wall needs to be installed from the outside. So these are all things you need to think about, packaged together to get the system that's going to work for your building. That was fairly economical. There's another building we worked on in Honolulu. It's got a free-form wall on the outside. That's got to be curtain wall, right? Structurally glazed, free-form, large format. Every panel's different. It's going to be window wall. But the other side of the building, standard balconies. Or that's got to be curtain wall. Other side of the building, standard balconies, window wall, all day and all night. So we did curtain wall, we did window wall, and in a very protected space between the two, they were combined together. Here's another shifting balcony example where we don't have balconies aligned in a stack. That's done with curtain wall. This is curtain wall. Curtain wall. Window wall. Curtain wall. You know, this one here, most difficult, most risky thing we did on this whole job on Shangri-La was those balcony penetrations, where we tied in this curtain wall system to the balcony. Very difficult with that system that we chose to marry it to the balconies. There are other systems out there with great big internal gaskets made of silicone that make that a lot easier. So even within the curtain wall field, there are better options for tying into balconies and penetrations if you've got a lot of them. Curtain wall, right? This is bespoke, everyone's different, rotates a lot, high spans, high wind loads. Curtain wall, right? This curtain wall system on far West Georgia had to support soil and planters and look good and have very, very little sort of exposed mullions. So clearly, unitized curtain wall and structural glazing. This one here would normally be done in stick built. I'd never done one in unitized. The manufacturer came to the table and said, we want to do this in unitized, and they did it. I didn't think it was possible, but they did. And that's really a testament to the CAD design we have now and how much can be done by computers and by automated equipment. This is one, it's window wall. It's iconic in a way, right? They've got really neat mullion caps that span floor to floor, right? Take the window wall, put those on, the window wall in. You can do some really neat things with window wall and make it look a little more like curtain wall. And we've got our woofs and waffets, right? This is a bespoke curtain wall system. You need to redesign the internals of it because when it's not vertical, it doesn't drain. When you slope it back, it becomes a skylight or a Y-light, I like to call it. So you need to make the internals drain.
Yeah, so energy efficiency targets are kind of pushing us away from just straight curtain wall systems now. So like this is KMH actually out in Toronto here. They're putting in a double facade to try and hit their energy targets. So it's curtain wall and the inner one's also another layer of curtain wall. When you can't afford two curtain wall systems, you go to mega panels, right? So then this is the Academic Wood Tower. It started out as curtain wall all the way around, couldn't hit the targets, had to introduce a mega panel to basically take up that, increase our energy efficiency right there. Same thing here. This is Toronto Western Hospital, and that's the PMU for it. That's just another mega panel, and then wood-based, again, mega panel here at this 230 Royal York here. And then this is the hybrid system that we've got going on at, what's it, LeBreton Flats in Ottawa. Yeah. So.
Yeah, LeBreton Flats is a neat new bespoke system that, that combines the idea of a mega panel into a conventional window wall, pulled together to fly past the floor slab, but still kind of sit and be supported by the floor slab. So a unique hybrid, which I think has a lot of merit as we move forward and try and increase our energy targets. Last but not least, I'd like to end on this. Oh, I can't go back. Here we are. Can I go back? You just restart me. I got one more, then I'll get off the stage. I really blew that, didn't I? Just for everyone in the room, this is like, we do a lot of work drying buildings out after construction and just working with them over the years after we've constructed them. With everything I've showed you so far, all the testing that we do, we talk about initial water tightness, initial air tightness. None of those test time of wetness. How long is it wet? How long does it take to dry out? And when is it going to start to decay? Right? Because we don't care. It's silicone, it's aluminum, it's stainless steel. Don't care. When we introduce wood into our facades, you need to care about that, and you need to do something to figure that out. This is a job in Brisbane. I was at Zak in Brisbane. This was outside my hotel. I took a picture of it. It's already starting to decay. Now we've got a call on it. The other one is a job where the architect wanted to use wood, but we used a 1080p frit on the back side of the spandrel glass from a picture of his wood. And the architect liked the look of this better when we did our mock-ups. So pretty cool. And for those that want to get my presentation, look at this. This is a great nomograph. This is a natural nomograph for how much overhang protection you need for wood to keep it looking good. This is out at UBC. It's right near Brock Commons. Anybody can go look at it if they're in Vancouver. There's your overhang. There's your overhang on the other elevation. You can see here where you've got lots of overhang protection, your wood looks good. Where you have less overhang protection, and you can see this is even a windy day, there's wet here, you can see that wood doesn't look good. And it's gonna need to be fixed pretty soon. And then you can see over here where it's fully exposed and it needs to be fixed now. Wood is not something that you can just run through a standard PMU and say, it worked, it's watertight, it's airtight. You need to think about how long it's gonna be wet, how long it's gonna take to dry out, and when it's gonna decay. That's what it's just gonna end on. Thank you.
Thanks.
Thanks, guys. Thanks, Brian. Thanks, David. That was great. I'm going to be having anxiety nightmares about your Franken mock-up. But I do love to see a good chicken head detail in the morning. Okay, so next up, Tobiasz Staszak from Reynears Aluminium.
Thank you. Good morning, everyone. My name is Tobiasz Staszak, and I'm responsible for development of Reynears Aluminium in North American market. My today's presentation combines two elements, our approach and support for projects, as well as utilization of virtual reality. It's great to see a lot of people that we already work with, but I think there is also a group that never heard of us, so I will start with a very brief introduction of our company. To start with, we do not extrude aluminum and we don't make windows and doors. We are known as one of the European leaders in terms of design, engineering, and marketing of facade solutions. And it's very simplistic, but also with all these characteristics behind me, it's difficult to understand it, so let's go step by step. First of all, we are a family business, started in 1965 by Jan Reynears. Jan used to work for an extrusion company, and he realized that the windows and doors available in Belgium market were very difficult to install. And already knowing aluminum product, he came up with his own design, and created company that designed and fabricated windows and doors. At that point, we were fabricating windows and doors. But within 2 years, other fabricators in that region started asking him, okay, we like your system, why won't you focus on it, and we will take care of fabrication and installation. So that's how the idea was created of Reynears being a system house. But Jan wanted to have a company not just with the, okay, here's the profile, here's the catalog. He wanted to build environment that supports all his business partners, whether it's fabricators, architects, general contractors. Unfortunately, he died 8 years later in a car accident. He left his wife with the company and 5 children, and they decided to continue. They decided to continue with his business model, the vision, and of course with the DNA of the fabricator. And today, this year, we are celebrating 60 years. The business is transferred over to the 3rd generation. We grew from the small player to international facade company with offices in almost 50 countries and business activities in 70. Since more or less a decade, we are present in North America, and really since few years, this is the fastest growing market for us. And as a company with such experience and international exposure, we see the challenges, everyday challenges, such changing requirements, building codes. These building codes, they change not from country to country, they vary from city to city. Sustainability, supply chain interruptions, skilled labor shortage. It's not just in here, it's everywhere, all over the world. So we as a company, we believe that it's our duty to support our business partners with all these aspects. So we aim to be a company that's the centerpiece and a glue between investors, engineers, contractors, architects, and of course, fabricators in the center. And our motto is together for better. To give this presentation a concrete example, I will use the project 89 Avenue. So the project, it's a 21-story building here in heart of Toronto with 28 luxury apartments. We also have some lounges, dining, pool and cabana. And the project immediately, when we started the discussion, showed few challenges. Of course, air, wind, water, acoustics, that's number one. Then aesthetics. Everybody, of course, nowadays wants to have the slimmest possible sight lines, ideally without any reinforcement. We have a large portfolio of products. Okay, which one would be the most suitable for this design? The stakeholders were really insisting on anodized finish, but the medium bronze was a little too light and dark bronze was a little too dark, so we had to come up with the custom one. And also flat on the inside, but mechanically brushed on the outside. We have curved elements with some very difficult radius, curtain wall profiles, brushed, again anodized, so we only identified one supplier in Europe who could do it for us. We had some challenges with penthouse sliding elements. And at the end, okay, we still have to fabricate all these custom solutions within the schedule and, of course, budget. So number one, okay, the right product. So at Reynears, we have an in-house testing facility, which is one of the largest in our industry. We can do air, wind, water, seismic, durability testing, acoustical, impact, and everything we offer in North America, of course, it's certified to NEUF and NFRC and validated by UL or Intertek. So immediately we had a spec. We selected few products, stick curtain wall, window door system, lift and slide, folding, and our cladding system. The nice thing right away was that we were able to achieve the required performance with double glazing instead of triple glazing. So of course this introduced cost savings immediately. And now I will tell you a little bit about Avalon itself. So the 3D is nothing new. It's been with us for a very long time. It's basically two images, slightly different perspective, one for each eye, and our brain combines them, creating this three-dimensional environment. And there is a lot of different devices you can use. You probably saw them or used them at some occasions. But the challenge with these devices is that everybody using it, it's immersed in its own virtual reality, making it impossible to collaborate together, which kills the purpose. So when we take it to the next level, we end up at caves. And caves are heavily used in automotive and airplane industry. Car manufacturers, they boot several models in virtual reality before they proceed with the actual prototype. And we can do three different kinds of evaluations: the concept, technical, and high quality. It really depends on the stage, the phase of the project, the type of stakeholders, and what they actually try to get out of it. And it's on a weekly basis, we receive different type of groups. Sometimes we have an architect who's really trying to convince the investor. Sometimes we have an architect who's discussing technical details with the general contractor. And the following video will show a few different applications.
Welcome to Avalon, a space to explore architecture through a shared virtual reality experience. Did you ever wish you could walk into a building that is still in the design phase? Avalon can take you anywhere you want. 25 projectors make architectural designs come to life in unequaled resolution, with cutting-edge laser technology creating the most vivid colors, contrast, and brightness. Active 3D glasses create a natural spatial awareness, and as a user, you are instantly immersed in a true 3D environment that creates an incredible sense of scale and depth. You are able to share the experience with your partners, allowing you to discuss and evaluate your projects before they are built. Avalon is a collaborative working tool, offering a joint experience between architect, contractors, investors, engineers, fabricators, and Reynears experts. Virtual reality is set to play an important role at all stages of the architectural process, from evaluating design options and showcasing proposals to detecting construction issues before breaking ground on site. Starting at the conceptual phase, VR has proven to be effective in exploring the relationships between spaces. VR gives you an immediate feeling of being inside the building. You can experience the impact of light on a room, or evaluate the different interior viewpoints. The spatial realism makes Avalon an incredibly powerful tool to communicate design intent. When the architectural design is further specified, BIM files are effortlessly translated into VR, providing architects with even better tools to communicate about their choices and improve their designs. Enabling architects to effortlessly move between BIM and VR truly revolutionizes the way buildings are designed. Avalon allows you to explore your projects inside your usual design software. Its powerful main workstation handles 3D models produced in any commonly used software in the architecture industry. By tracking the visitor's movements, real-time rendering engines create the ultimate VR experience, from initial sketches through detailed technical models and realistic scenes. Before your visit, you provide the 3D model of the project. In consultation with the building team, the objectives are set and the model is adapted accordingly and prepared for VR. Different options can be prepared to compare several Reynears systems, configurations, bespoke solutions, or specific design variants for your project. Avalon is perfectly suited to create diverse virtual mockups. You can make sections, explain complex technical setups, or examine specific construction details or project solutions. This new way of virtual prototyping reduces costs and increases efficiency drastically. The high-resolution real-time renders allow you to see every detail so you can experiment with different configurations, evaluate simulation or BIM data, and further improve your design. You are able to experience Reynears systems up close and compare the different solutions for your project. Discover Avalon, the space where future projects become a reality.
Okay, why do we do this? We do it for two reasons, and I'm sure all of you are familiar with both. Number one is to avoid mistakes. We know that most of the mistakes in our industry are not very complex. There is just with the tight schedules and the workload, it's very easy to miss the detail, oversee something, and down the road it costs a lot more money and time to fix it. And then decision making. So yeah, we have different stakeholders, architects, general contractors, we have engineers, etc. All looking at the same project from a different point of view. So the decision-making process can be very complex. We look at different details, different configurations, different installation methods, comparing samples. It goes on and on, often for months for no reason. Here you can see the 89 Avenue team. So you have a developer, builder, facade contractor, Reynears engineers together looking at a project, working on it. When we receive the file for the project, it takes us 2 to 4 weeks to prepare the Avalon itself, but also that gives us a time to proactively think about these challenges and the discussion points so we can come up proactively with solutions and alternatives. So to give you a few examples, when the developer showed us the project, looked at our portfolio, he immediately said, okay, I would like to use Masterline 8 Renaissance. We looked at we looked at it in the file, and then, okay, with this kind of grid, with this kind of mullion transom configurations and opening types they would like to utilize, said no, this will, in our opinion, this will be too bulky, too expensive, and the Renaissance version is a little bit more complex to fabricate, which will take longer time. So we proposed Slimline. And here you can see the original rendering showing the Masterline 8 Renaissance, and the next one, it's SL38. So immediately they were able to visualize the difference, and the choice was very simple. Same with the sliding doors. You can see the original rendering, and then our proposition for the slimmer version. We did several, we put several different units so they could also see the windows from the inside. And then we identified the next detail. So between the bottom, the top of the window and the bottom of the louver, we had this 5-inch detail, which originally was drawn as a curtain wall. And with this kind of application, we said, oh, this will be way too expensive and time consuming. So we proposed a transom connection between the window and the louver, and we had something off the shelf, but it was 4-inch, or if they really would like to keep the 5-inch detail, we could make it custom. But we showed it in Avalon. Can you even see the difference? No. Okay, let's go something off the shelf. Okay, so now we identified what system we want to use. We know what the connection is between the window and the louver. Now we have to put it in our software, and quickly we are notified that we have to use the internal reinforcement. And because we already knew that there will be internal shading, okay, we knew this will be a point of discussion. So we started thinking, what can we do? And we redesigned this window in a way that we ran the transoms across instead of the vertical mullions, and that eliminated the need of having the reinforcement at all. Then we had some challenges. We each call it a cherry on the cake. These are penthouse elements. So the penthouse owner, he wanted to, of course, on one side to see an obstructed view of Toronto downtown. So this was the original design. We came up with the detail that it's a 2-panel door. Each unit is 1,500 pounds and hides nicely into the wall. So that addressed that issue. And on the other side, he convinced the builder to install the external car lift, so he can take his unique car and drive it right to the unit. So we proposed the folding door with the 0 threshold detail on the other side. Now we are talking about anodized, mechanically brushed profiles, folding doors, pocket, lift and slides, curtain walls, radius. How do we make it efficiently? How do we to keep the quality and stay on the schedule? So this takes us back 60 years when Jan Reynears wanted to create this company offering this, what we call ecosystem. So on one side, we have systems, profiles, accessories, we have machinery, we have software, digital environment, and everything is connected. Every detail talks to each other, making it very simple to fabricate. Our software, once you insert your project in our software, this generates your cut details, beam files, material list. Once the fabricator receives our material, the cutting list is taken care of. All the millings, it's done by, it's pre-programmed by us. All our solutions are available in North America, also in Toronto. Everything's fabricated locally and supported by the local team on all different levels. And this allows us to look at the project a few months later as a great reference without headaches. And for those of you who like more challenging projects, probably a lot of people are familiar with 138 Yorkville. Avalon is being utilized on this project. I hope next year we'll be able to present it to you. It's a very complex development, almost 100 custom articles. It's a hybrid between unitized and window wall system. and then also River Cree Hotel and Casino. Last month, we had 11 stakeholders in Belgium discussing final details, and as we speak now, the performance mock-up is being installed in our headquarters in Belgium. This concludes my presentation. So if you would like to learn more about us, about our systems, solutions, if you find yourself in troubles or you familiarize yourself with these two challenges I mentioned, and you would like to put your project in Avalon, let's talk. Thank you.
Thank you, Kristoph. I'm gonna hit you up later for a pair of those Avalon glasses just to wear around town as a fashion statement. Okay, so next up we have, sorry, thank you, Tobiasz. I said Kristoph. Next up we have Kristoph Karbach from Lumon, Canada. Is Kristoph around? Yeah, there you go.
Okay, good morning. Pleasure being here today, and I guess I have the privilege as well of being the last speaker before the first coffee break, and we're already running a bit behind. But nice to be here today, and thank you for that introduction. So here's what we'll be covering in the next 15 minutes. I'll talk a little bit about Lumon, a little bit about balcony facades, some of the solutions that they present to today's challenges, and then some contemporary Canadian case studies. But first, I'd like to start off on this image, and that's because I think, to me, it's a little bit of a metaphor of the housing market today. When we look out from this balcony, we see that the forecast is unpredictable. We're pretty sure that we're going to get rained on if things don't change course in a sort of proverbial sort of way. Then we know that there's a lot of noise here, a lot of people talking about who or what is to blame for the situation that we're in. And then we even tried to add some of this netting to keep some of the mess out, but it doesn't really seem to be addressing the real issues. And I'm not here to give a lecture about the housing market today, but really maybe present one solution that needs to be part of the many solutions that can get things back on track. And there's no coincidence that I'm using a balcony as an example here. When we look at a balcony today, from the end user's perspective, it can be seen as a thing that they really, really want, that private outdoor space that they want, but really never use. For a developer's perspective, or an engineers and architects, it can be a costly addition and complicated addition to the project that may not bring the returns that they would like. And so people are asking legitimately the question of to balcony or not to balcony. And I know I'm using a modified quote of Shakespeare's Hamlet here, and what we see is Juliet's balcony in Verona, but at the end I digress. The question is really about, what if we were to reimagine the balcony into something that's actually useful to the end user, that can create a differentiating factor in the marketplace, and that can address some of those issues that we face in construction today related to energy savings, sustainability, and noise? Well, then maybe we have an interesting, innovative solution. And how do we do that? We introduce balcony glazing, frameless balcony glazing, and balconies or terraces, as you see here. Now, this concept, which is relatively innovative here in North America, is one that took off in the early 1990s in Northern Europe, and it really changed the way that homeowners interact with their balconies. By having this versatile, minimalist system that opens and closes, you can really extend the amount of time you spend outside and also the amount of livable space in your unit. This became so popular that it actually changed the architectural landscape of many cities in Finland, where the summers are very short and the winters are dark. Which brings us to the company that started it all, Lumon. Not to be confused with Lumon Industries from Severance. As with many humble companies, our origins started in a small chicken coop in rural Finland in 1978. And we started in the window repair business. And after about a decade of different strategic pivots and name changes, we developed this concept of frameless retractable glazing. Since then, we've grown internationally in the late 1990s, all over Europe and other areas. In 2011, we opened up our location here in Canada. Originally, we were 2 staff. Now we have 2 offices, one here in Ontario, one in BC. We have a manufacturing facility in Vaughan, and then we have dealers all across the continent. Globally, we are out of 3 to 4 different manufacturing facilities, which gives us the flexibility to really adjust our workload according to supply chain challenges or even pandemics and threats of tariffs. And today, ultimately, we see ourselves as a design company. Our purpose is to create more room for life by bringing the indoors out. We just happen to do it with glass. Which brings us to this glass, the Lumon balcony facade. It's made of two main elements. The lower component, which is the Lumon railing system. It's a minimalist engineered railing system to have really wide spans with any support posts. And then the top element, which is the retractable glazing system, is where the magic happens. These are independent glass panels that are manually operated to slide and open and pivot to be able to give the user either an open, a closed, or a semi-closed balcony based on their desired space. When you put these together, you have this beautiful facade. From a more technical perspective, some connection details here. The system is a top hung system that is attached to the underside of the slab through a telescopic profile that we can adjust in case there's some movement in the slab. Then the railing system itself is horizontally supported, attached directly into the walls at the end of the balcony or through vertical aluminum posts. And then the very bottom profile, the aluminum profile, is slightly chimped for drainage and then anchored into the ground. When you put all these elements together, you end up with a facade that looks something like this. This Roots project in Hamburg, Germany. This is Germany's tallest skyscraper, they would call it. That's wood-only construction. 18 stories, 181 apartments there. The entire building is encapsulated with Lumon glazing, creating breathtaking views, energy efficiencies, and also protecting the wood from the harsh harbor elements. Or this project in Zutrecht, Antwerp, in Belgium. It's a 24-story concrete building where you have these large balconies that are randomly placed on this concrete precast exoskeleton. Or this very interesting project in Copenhagen, Denmark. It's a beautiful renovation project completed in 2021, and it's unique because before the renovation, it was called the ugliest building in Denmark. And after the renovation, it was known to be a project that really handled the climatic, the acoustic, the thermal issues that the building had, while also fostering social cohesion, meaning that these balconies are semi-private, shared, where all the residents can come outside and connect with each other. But let's dive a little bit deeper into some of the solutions that may be brought by bringing glazing to the market. First, sustainability. Our system reduces the carbon footprint of our homeowners. With 95% recycled materials and a very efficient manufacturing process, we reduce the amount of carbon emissions in the building over its lifespan compared to what's created during the manufacturing process. And that's also backed up by our APD, which we received in 2023. But we wanted to take a little bit of a deeper look into what that meant in practical terms. And so over the years, we've done several analysis and case studies. Dr. Ted Kessick from the University of Toronto, some of you may know him, he is very familiar with our product, and he presented last year at the Ontario Association of Architects some of those research findings that we've done over the years, looking at 27 different balconies on 11 different buildings over a period of 10 months, and they found a significant reduction in heat loss of the glazed balconies, between 15 and 22%, really increasing the overall performance of that building. But we wanted to take a look at what does this mean in terms of a local context, Toronto Green Standard. And so Ted Kessick also did a model for us that basically looked at how, if you add glazing to a building, what is the impact of key Toronto Green Standard metrics? And so this model looked at different window-to-wall ratios, looked at all the different cardinal solar orientations, and it determined between 19 and 30% reduction in key Toronto greenhouse performance, key Toronto Green Standard performance metrics. Sounds like I have a greenhouse purchase in mind later on. But basically proving that our system really represents a feasible alternative to increase the levels of thermal insulation envelope airtightness for your building. The fact that it's also a passive system means that it's a really effective, cost-effective means of increasing the thermal resilience of your building. Another element and challenge today is, of course, the materials that you're putting on your building and the reliability over its performance. So Lumon, again, the product made of tempered glass. Looks like we have some graphics issues there, but that's we'll survive. Made of glass, tempered glass and aluminum, it's really low maintenance and lasts for a really long period of time. As a matter of fact, it adds longer period of time between your maintenance intervals and reduces the need for renovations. Taking a look at this example here behind us, well, it looks like it's AI generated. I assure you it's not. This is a real image, and you can see the degradation in the concrete facade there and the unglazed balconies versus the glazed balconies, where you now have allowed that moisture to come into the backside of the balcony and penetrate that concrete. When you add Lumon glazing or balcony facade, you increase the lifespan of that building by 30 to 50 years. This is a really interesting proposition in purpose-built rentals, where you really need that asset to perform over an extended period of time. Another thing that you want to check, of course, especially when you're bringing new or innovative technology, is that it's been thoroughly vetted. And so Lumon has been vetted and certified globally. And in 2012, we received our first CCMC certification. It's important to note here that some of the terminology used in this is helpful for site plan approval. Because of the innovative nature of the product, there's no real classification NBC or OBC. So often the system is defined as an enclosure, but it's been specifically designed not to be hermetically sealed or thermally broken. Therefore, it should not count towards GFA or FSR, which is something that the City of Toronto agrees with us on. And another thing, especially in tower construction, is the wind considerations that you may need when you're putting this glazing on your balcony. And so we work with engineers to determine the pressures and suctions. And the Lumon system has a max wind capacity of 3 kPa. And in this example, this 50-story building here, there are only 2 very small sections on the bottom right-hand side here where the wind exceeds that. Obviously very present today, especially in more infill projects, is noise. The Lumon system really reduces up to 50% of the perceived noise, and is also compatible with MPC 300 guidelines. To take a deeper look at this, we did an in-situ study this year. We partnered with Acoustics, and we set up a mock-up on the 22nd floor of 10 Abaya Street in Vaughan, nestled between Jane Street and a metal stamping plant. And we put these simultaneous indoor and outdoor microphones to determine the noise reduction between the outside of the balcony glazing and the inside of the balcony. The study was done in 3 different configurations, first with open panels as a control group, and also to mimic what an unglazed balcony would be like, with closed panels, and then in a third configuration, closed panels and additional noise reduction seals. And it saw a decrease of 13 decibels in the best configuration here. This really means that the system can be a really suitable alternative to be an enclosed noise buffer, according to NPC 300, especially in Class 4 developments. Here you see the graphs, the difference between the open panels on the left and the closed panels on the right. The noise pattern is similar in both, but you can see the difference when you do have that additional layer of glass. And ultimately, while it's very good as an enclosed noise buffer for Category 4, this also means that it's very suitable perhaps as a value engineering solution instead of costly STC window upgrades in other noise areas. Which brings us to livability. And in a market today where we're designing more for the end user as opposed to the investor, this is increasingly important. And so what does this mean in terms of balcony glazing and our balcony facade? It means adding additional time that you can spend outdoors, which is really important to have that connection to nature. And then secondly, it increases the space that you can use in your unit at a fraction of the cost of actually increasing that unit. Here's what that actually looks like. Take a look at the balconies on this building in Laval. Every single balcony is really being used. Similar example here in Langley, BC, another project. And you can see how full of life this is, whether it's an outdoor dining room, a lounge, an art studio, or even an outdoor play area for the kids. It's full of life. And then looking back at some of Ted Kessick's reports, the graph here shows how much you can really double the amount of time you spend outdoors by adding a balcony glazing, which is one of the main reasons why Bosa Properties from BC decided to strategically partner with us and use balcony glazing as the main differentiating factor on the market for their users. And I quote here, "It was a strategic decision driven by our insights on how customers want to live, the need for a year-round connection to nature, and flexible and functional spaces emerging as a priority. I'll end off just quickly here with some other Canadian projects. I'll run through them pretty quickly. I would like to mention, before I get into this one, is that we've done over 3,800 balconies across Canada since our coming here in 2011. We have another 6,000 under construction or in our pipeline, of which 3,500 are in high rises. This is an example here in Ontario, in Barrie, Lake House project, 174 balconies on 10-story concrete building. Another project in Barrie finished last year, Luna with Pratt Homes. This is the first of a 3-building series with just under 100 balconies. Madame Homes, we have Carting House that just finished, 42 units, and then another Madame Homes project, Clockworks, will be completed next year. This adds to our portfolio with Madame Homes. We've done over 400 units in 4 different projects, not including these 2 here with Madame Homes since 2019. Our first major project in the prairies in Canmore, Rundle Park, is an outdoor luxury spa with 97 units and some common space that will be glazed. And then, of course, Bosa Properties, the Sohals project in Burnaby, BC. This will be completed in 2028, and that's 430 units over 44 floors. Quick summary of what we talked about, but I'd like to come back to this picture. And while I'm under no impression here that somehow Lumon's balcony facade is the magic bullet that will change course, I hope that I've given you a glimpse into an innovative solution that may be part of those many different things that we need in your projects in this current market environment. So thank you.
Thanks, Kristoph. Lots to think about there, and you know, the optimist in me likes to speculate that maybe the current market conditions will force a bit of a pause, a bit of a recalibration, so that when things roar back, it's not necessarily business as usual, and I can certainly see some big advantages to implementing these types of systems. I also think there's a real noise pollution problem, especially downtown, that we don't talk enough about it as architects in Toronto, and this could play a real role in mitigating some of that. Okay, so next up we have a scheduled coffee networking break. I think there's going to be a chime or some kind of signal to indicate that we're resuming. Thanks. Oh, and can the speakers come back up, please, to get photographed? Thanks. Yeah, we're good. Okay. Is everybody back and caffeinated? All right, so let's just dive right into our next session. We'll begin with Adrian Betanzos from VIA. Take it away, Adrian.
Thank you. Thank you for the very brief and good introduction. You got my name? So, hola, good morning. This is in Spanish because I'm Mexican, and so that's my main language. I try to speak English. Don't try me with French. And like my grandma used to say, you have to salute when you see people, and so you have to say hello and good morning, because it's still morning. It's still morning. So my name is Adrian, or Adrian, or like Rocky Balboa said, Adrian in Rocky. That's me, so you can remember the name. And I'm one of the partners of VIA. This is a pseudo-new facade consulting company that we are basically facade consultants, facade geeks. We're a group of about 45 people. We have, so I'm not in your way. We have 5 offices. We just opened one in Dubai last month. We have an office in Seoul, San Francisco, London, and Hong Kong, and Dubai, as I said. And we get to work in a lot of really cool projects around the world. These are 12 images of some of the projects that we are involved, or we have been involved, and our teams have been working on. They're fun. They goes from let me see, this is a new thing. No. Yeah, it works. It goes from like a bench all the way to high rises. And here's the title of my presentation today. There's no bad materials. And as I had said in a comment before, it's like he knows of a few materials that are actually bad, and that's true. There's really bad materials in the world. but not the ones that we collectively are trying to work together with. And this is what I'm trying to talk about. I started this conference, besides saying hello, to tell you that I have 2 kids, and it's what has changed my internal world for, I'll say, for better. These 2 kids are what keeps me alive and what actually, in this case, helped me to come up to the name of the presentation, to the one-sentence presentation, because I didn't have a presentation nor a name, so I came up with it. And so these 2 kids, although they can be very, very sweet, and you can see how they start getting the bond together. They're my 2 kids, Adrian, the older, and then Bruno, the youngest, 3 and 7. They're so sweet. They can be super nice, and they get in this bond together, and then especially when they're sleeping, they're super nice. Or when they have sugar. And as long as the sugar lasts, we're good. But they're kids. They're kids, and they misbehave, and they have fun, and they test your limits. And sometimes they fight. They fight more than you can think of. I have brothers too, and I know that. And they pretend they're fighters and Star Wars and lucha libre and stuff. And sometimes they try to hit each other with stronger things. And we don't have pictures of that because usually it's me and my wife are running around just trying to separate them and not to hurt them too much. But it's in those moments when the chaos starts within the family. And it happens in the house and it happens outside the house. And it's in one of those moments when it happens outside the house that you start getting all this wonderful feedback or uncalled recommendations of how to educate your kids. Very uncalled, sometimes taken out of context, and sometimes, if not most of the times, really bad recommendations or suggestions of how to work with your kids. But there are comments, and they are good. And this is one of those. They recommended us these 2 books, No Bad Parts and No Bad Kids. You're getting the gist of where I took the name from. This book talks about that all the parts of your body, especially also your feelings, are not bad, and then you have to live with them, tolerate them, and if you try them with a compassionate way or positive way, everything can be used, and so you have to teach them how to use them. The next one is about discipline without shame, and I thought, I can discipline and I don't have any shame, but it's actually the other way around. It's like you have to learn how to discipline without giving them shame about it. It's interesting about how to make sure that this is not a bad behavior, but they're trying to communicate. They're trying to see the shows. Like if they're screaming, they may be hungry, they may be sleepy, or they may be tired, similar to sleepy, or they're communicating. They're trying to show you that they need something. That's the communication. So I use this book and cross it out, and I realized that I should have used AI to put my face maybe in there and make it nicer than just crossing out the names. But so this is where I got the name from. There's no bad materials, no bad kids, and what I'm trying to present here in the next follow slides is that yes, well, there are materials that can be used, and they need to be used to the best of its performance. They need to be understood, they need to be cared for, they need to be loved for what they are, not overuse them, but really understand each part of the molecule of the material and use it properly to your building. And that's what I'm trying to show. So I did a quick study of these 6 materials plus 1 extra surprise material that it has nothing to do with construction. It's not that bad. It's not as bad as radioactive materials, but it's something to think about. So I compared the materials with the carbon footprint. And the carbon footprint, you can see how you have the aluminum, which tends to be, at the moment, one of the highest carbon footprints materials we have, and that we use a lot. We have acrylics, glass, stainless steel, GFRP or GFRC, cementitious things. Even though concrete and cement looks very small, cement is supposed to be not as good because of the amount of cement that is produced rather than the cement itself. Anyway, and then there's other material that when you put it in the graph, it doesn't really fit in the graph. So I decided to shrink the graph, change the scale, lift it up, bring it up again, that up to about 60, which is 4 times the aluminum. Now, before I go and tell you what material this is, it's really important to understand that lately, and we've been getting that a lot from design teams, that they don't want to use aluminum because aluminum is really bad. Let's just not say that. Beef. Beef, the production of beef per kilo is 4 times of the aluminum. So if you think the aluminum is bad, you need to start becoming vegetarians. I am not vegetarian. I had some piece of steak yesterday in Little Italy here with some friends in a nice Italian restaurant called Sito Sito. So if you want to go, it's nice. But let's take this beef out of the equation. And if we put the materials again, now we have the embodied energy. And each follows a similar graph, or aluminum is really high and the other materials are tapering down. But if you think about the recycling potential of these materials, then suddenly aluminum is the best, and glass, and of course steel. And steel is the product that can get reused the most and gets reused the most and recycled. And you know that aluminum is the most abundant metal in the crust of the Earth. So the crust of the Earth is the first, some people say 100 kilometers or 70 kilometers of the top of the Earth. So aluminum is the most abundant material. And the third most abundant material, no, the most abundant metal, and the third most abundant material after oxygen and silicon. Silicon produces silica dioxide, which is silicon dioxide, which is a silica, which is silica sand, which is how we make glass. So glass and aluminum are coming from the most abundant materials that we have on Earth. So instead of just thinking about numbers and graphs, I wanted to show you other levers that actually help us decide what materials to use in each project, or at least inform, so you can see if that's how you make it do it. You have the design intent that always there. Everybody wants to use the material, say, let's call it again aluminum, with the 100% post-recycled consumer product that has been used, the cleanest grid in the world, and that you can get it next day. But then you talk about the price, and then now, well, maybe 10% instead of 50%, or maybe then you start thinking about all the things that you don't want to do, or what of the sizes? You want to have a big piece of glass. It can only be made in 3 or 4 parts of the world. So it's location, supply chain, we were talking about in the previous presentations. Or what about, I want to use more glass because it's inert and recyclable, but you don't want to have a glass bottle in your shampoo, and if it breaks in your shower, well, that's not a good idea. Safety. So suddenly plastic can be a better material in that occasion. So it's about where you want to use it. Sometimes glass might sound like it's very weak, but it's actually very strong, and you can use it in structural elements and make stairs out of it, and so on and so forth. There's materials that you can use, and these are the levers that you can sort of start thinking about it. So I have 4 projects that I want to show you, pretty nice pictures of projects. This one is the Sugar Cloud in Hong Kong. It's a beautiful light fixture on this monumental lobby. The idea of this sugar cloud comes from the architect's idea that is a sugar cube, that with the lights and the movement and the undulation of the elements, it becomes like a cloud. So it's a sugar cloud light fixture of the lobby. We compare glass and acrylic. The acrylic is 6 times more the carbon footprint of the glass. But acrylic is what was used here. But also, glass is twice the weight of the acrylic. So you would have to have, for the same thickness of this material, you would need to do, it would be twice as heavy. But guess what? This is on top of your head, so you cannot put a piece of glass monolithic on top of your head. So you have to laminate it with a polymer, and a polymer is a plastic, in other words. And so it can be certainly it's not 6 to 1 the comparison to the glass and acrylic. Plus, you would not be able to use this project with glass anyway. These towers in Qatar, there are 4 towers all together designed by Foster. They had a really interesting schedule. This is all aluminum. This is 40% visual area, 60% solids. The comparative was between these 4 elements, 4 materials: aluminum, stainless steel, glass, and concrete. It was part of a master plan, also designed by Foster's, and the building here below is the stadium for the opening and the closing of the FIFA World Cup in 2022. So that's just part of the entire project. The schedule time became a very important design factor to decide what materials to use. The design started, the end of 2018. The contract was awarded in spring 2020. The fabrications needed to start by the end of that year. But, we had this little thing called COVID that, I don't know if you remember about that. So the whole thing had to happen within those 2 years because the World Cup was not being canceled. And it didn't get canceled. Anyway, this is how the towers look. If you put them together, there's about 1.1 kilometers of length. And so the same levers were used, weight, design intent, materiality, carbon footprint, supply chain. So stainless steel would have been a great material to put in here, but it was more expensive and heavier and couldn't be sourced locally or close by, and couldn't be done faster. So in this project, we use an untreated aluminum marine grade piece. Luckily, that it can also be found with a good grit and used for this project. The design also needed to put, have some extra elements, and it needed to be, because of all the shape, it needed to be solved, with triangles, but the architects didn't like it, so we used planar quads, but it was not creating the effect. So we ended up using cold bend glass in these corner plats. So what it did, when you have all these spaces, you have extra, the red things are extra spaces of material that you needed to fill. And so what we used by cold bending it is we reduce the amount of material and cost. So basically, instead of having this length piece of material, you push the glass, you make it work, and at the same time, because you have less material and it's more efficient, so we were about 30% more efficient in terms of thermal by using creative engineering. And this is how they look, the cold bend panels, and this is how they look, the project almost at the end of this project. Similar scale of a project. This project is going to start getting built in Qiddiya in Saudi Arabia, next to Riyadh. It's going to be the Performance Arts Center, designed by Tom Wiscombe, where it's trying to bring all the art into these elements. And then similar comparative, aluminum, stainless steel, and glass. And in this case, we were invited to, or asked to review all the work that some other people have done to see if everything was working well. And the project wanted to do stainless steel, but still wanted to compare all the options with the aluminum to see if that would work. So we did that. Again, the comparative, we not only compare materials, but sizes. What if the aluminum can do wider or smaller, or all the different things you can do. But at the end, the stainless steel stayed. And if you have the time and the money, it's more durable. It's a better product. Also with the glass, we checked how you can attach the glass, 3 points, 4 points, the thickness of it, the size of it, and we were able to optimize the size so you can fit better into the float production that you can get for this project. So at the end, saving thickness of the glass and saving material by itself. About 25% material. And it looks like that, or it would look like that. And there's more projects coming in the back. And the last project that I wanted to show you about is this project in China, the Suzhou Art Center, Museum Art Center. It has this series of undulated ripple facades with glass. The idea of the project is that there's 12 pavilions all linked together with this undulating ripple facade of glass with stainless steel roof elements. Here, the comparative for the decision was not between different materials, but different finishes on the glass. The ripples wanted to have these lineal patterns or undulations or flutes. So there's two ways to do it. One is you find a pattern glass that has been stamped, and the other one is you carve it. And because this project had money from the government said you have to make sure that many contractors have the possibility to bid for this project. So carving the glass or milling the glass was rejected because of that. You could not find that many good fabricators that can do it that way. So pattern glass was the way to go. Then it had to be curved, and you had to check that you can lift up the glass to curve it. And it's how it ended up looking. And then the roof, even though that roof by itself, because it's a series for connecting a stainless steel undulating roofing within the 12 pavilions and the gardens, that project deserves a 20-minute by itself, only on the roof, but we're not going to go there because we have very little time. So what's next? You can sit down and relax and watch something you want to watch on your phone, which, by the way, this bench was also made with the same aluminum that was used for the Lusail Towers. Is the same bench, the same aluminum that was used because it needed to be something that could be touched, could be warm, could be durable, and exposed as a metal. Anyway, going back to the question, what's next? So in my point of view, what's next is that you need to make sure that whenever you decide what material to use, you convince yourself, you convince the others, and you make it for the right reasons. And not just because I want to have a painted panel here, or I want to have wood here. Sometimes, the previous presenter, Brian, showing that, sometimes architects want to use wood. But wood is not the right answer for every project. So let's just be careful where to use the material. And I promise this is the last graph I'm going to show. This is I was watching a TED Talk, and I thought, we need to promote more of these. So this graph shows age on the horizontal and happiness on the vertical. And there's this graph called the humor cliff. And the humor cliff goes like this, where it's a Gallup survey of about 1.4 million people that were asked in about 166 countries or something like that. Don't quote me on that. But it shows how the graph goes down, and it asks the questions like, did you laugh or smile a lot the day before? And it started declining very quickly. And the good thing is it started going up again right around when you're 80 or so. And because we are in Canada and the life expectancy is 82 years, you are in the right track. You might be able to be there, but because you're in Toronto, and if you're a male, you might be screwed. Because you might not even catch the coming up. But if you're a woman, you might be able to laugh that your husband gone, or something about it. But we need to laugh more. I started reading more about this topic, and then the topic says that a kid that's 4-year-old, which is about the age of my youngest kid, they laugh about 300 times per day, in average. So maybe some kids are laughing more. For a 40-year-old average, which is about the room here, or 30, it is 2.5 months until you reach your 300 laughs. I laugh a lot, so I'm not included in that reading. So I just wanted to show you this graph because, yes, we talk about facades and construction and materials and stuff, but we're still people, and you need to just enjoy life. Like these architects who are just enjoying color and things and songs. And I don't know if do I have time or not time? Yeah? Yeah, I asked permission because this is a video that, it's the architect who's designing this tower in Kenya. And I show it because these architects are having fun with their project. They're trying to get it built, and even before they put the first, part of the building, they're doing videos about their building.
A stage from another world, built for this world. The future of performing arts is coming to Qiddiya City.
To just have fun, enjoy the ride. And this is my email if you need anything, and thank you.
Some really inspiring work there, and your title reminded me of a book I had growing up. There are no bad dogs, only bad dog owners. I don't know what that says about me and my crazy Australian shepherd that barks at any skateboard within 100 yards. Anyway, our next presenter, Matias Reyes, apologize if I'm not saying that right, from Vitro Architectural Glass.
Good morning, everybody. I'm hoping you're all doing well today. Just to quickly introduce myself, my name is Matias, and I am with Vitro Architectural Glass. And today I'll be speaking to you about biophilia and how incorporating architectural glass into your designs is an important element. Biophilic design is not just about creating beautiful spaces. It directly impacts our health and well-being. So by introducing natural light, greenery, organic shapes and forms into our designs, we can help alleviate anxiety and stress, promote productivity, and also help somewhat discourage us from falling ill during the next winter months. So as we proceed into these next couple of months, we all fall victim to the common cold and end up looking a little bit something like this guy right here. So my goal for today is to showcase how embracing biophilia in facades and in your designs, coupled with innovation in architectural glass, can support healthier choices and also create spaces that promote both human and environmental resilience. During the next couple of months, you may notice those around you, or even you yourself, pulling away from these more social events. You might even start to experience seasonal depression. And that's largely because we pull away and we start to become more recluse and stay indoors. So how do we fix that issue during these winter months? How do we connect with the outdoor environment? Well, that answer is fairly simple. It's through biophilia. Through numerous studies, scientists and medical professionals have found the link between humans and nature. The biophilia hypothesis is the idea that humans possess the innate tendency of seeking connection with nature and other forms of life. This idea has been expanded on and tested many times over. Numerous studies have also demonstrated that a disconnect from nature can negatively impact both our physical and psychological well-being. So in strengthening that connection to the outdoor environment, we're able to promote healthier life choices. We're able to promote a better physical well-being and also productivity. So this message is fairly simple, but yet powerful. In moments of stress or feeling overwhelmed, we as humans instinctually find the need to go outside to ground ourselves to nature and take several deep breaths of fresh air. Biophilic design is an emerging architectural movement centered around reconnecting people with nature through built environments. By the use of high-performance exterior glazing, we're able to enhance buildings' function, increasing their aesthetic appeal and also supporting the well-being and productivity of their occupants. Former CEO of the International Living Future Institute, Amanda Surgeon, began the Biophilic Institute with other like-minded individuals within her design community. This nonprofit organization in Seattle is centered around encouraging you guys to make more sustainable choices through thoughtful material selection. I'm proud to say that Vitro has been a part of many forward-thinking projects, including this one that you see here, the Bullet Center, which is home to the International Living Future Institute. By using Vitro glass to maximize on daylight and to provide this expansive view to the outdoor space, we've been able to transform this functional space into a warm and inviting space that also grounds us to nature. So as I move forward through my presentation, I'll be walking us through several recent examples of projects that have embraced biophilia and have managed to blur the lines between the indoor and outdoor space. This project here, One River North, is a perfect example of this. This building, in my opinion, exemplifies how modern architecture can harmonize both urban living with its surrounding landscape. The architects at Mad Architecture drew inspiration from Colorado's mountains and canyons, transforming these otherwise conventional outdoor spaces into these striking vertical landscapes. The result is a design that celebrates its surrounding environment, creating a unique immersive experience for its occupants. The natural curves or the soft curves of the balconies, coupled with the more earthy tones and the use of warm lights, have made a seamless blend between the indoor and outdoor environment. The use of curved glass here in the facade accentuates the organic fluidity of the architecture and also enhances the biophilic experience. This thoughtful use of glass reinforces the dialogue between structure and nature. Similarly, healthcare environments have also embraced biophilic design to support human well-being. In hospitals, of course, patients often experience many challenges, both physical and psychological. So by adopting these principles and incorporating a strong connection to the outdoors, a high amount of visible light, and introducing greenery, we can help reduce stress and promote healing. Studies have shown that patients with a strong connection to the outdoors heal faster, experience fewer complications, and require less pain medication. So again, by adopting these principles, we're creating a space that is not only beautiful and striking, but also calming. And for those of us who've had the misfortune of being stuck in an airport terminal for 5+ hours, we're typically first greeted with endless corridors, escalators, endless carousel of luggage, and crossing our fingers to hope that our luggage has actually arrived. Well, contrast that with dual terminals at Singapore Airport. You step off the plane and are immersed in this lush, light-filled biodome. Under this oppressive dome, travelers step into this lush oasis. The jewel provides or proves that architecture infused with nature can simply change a functional space into one that is a wellness experience. Its center waterfall is less like an airport and more like a luxury resort, transforming a stressful and draining journey at times into one that restores and uplifts. Studies have shown that even just 10 minutes of immersing oneself in nature can reduce stress, boost cognitive function, and also improve one's mood. Most tech companies are the culprit in disconnecting us with nature, but some have embraced biophilic design in their own campuses. Amazon's downtown Seattle's office has 3 conjoining glass domes where there are no desk space, no cubicles, no walls. In fact, the spheres resist straight lines and right angles. Instead, employees walk amongst the trees through these curved pathways and balconies overlooking open workspaces. Besides its employees, the dome is home to over 40,000 plants that live and grow here. All these elements combined to create a totally reimagined office space. So Amazon spheres have managed to redefine what we know as office space and blending urban office life in a living rainforest. The expansive glass walls create a transparency into the cityscape while allowing the biophilic design experience immerse its employees and offer relief from work's sometimes daunting stresses. A perfect and powerful example here in our own community is Moriyama Tashima's Ontario Secondary School Teachers Federation. The mass timber workplace overlooks the Don Valley Ravine and seamlessly connects its occupants to the outdoors. Its mass timber structure creates warmth and a tactile connection to nature through the exposed wood. The expansive windows create a sweeping view again to the Don Valley Ravine, bringing the outdoor environment inwardly. So as we design commercial buildings, it's critical to be mindful of how they interact with their surrounding ecosystems as well. New mandates surrounding bird-friendly design call for thoughtful material choices to protect avian life. Applications like Walker's acid etch treatments allow for compliance with TGS while allowing for a significant amount of light to still pass through your glass units. So typically when we review glass, we're focused on these 3 main criteria, which is your visible light transmittance, solar heat gain coefficient, and U value. However, for projects that you're considering ultra clear or very neutral glass, I would encourage you to review your CRI value or your color render index. This value is typically used in interior applications where we look at how does artificial light change color tones of objects, where in architectural glass, it's how do the objects behind a sheet of glass change, similar to the photo that I am sharing with you here. So your CRI value is a value expressed from 0 to 100, 100 being ultra clear glass. You can see here that we have 4 different neutral coatings to offer you. Typically, the approach for ultra neutral glass is low iron glass. A product that I always like to highlight is our Solar Band 65. You're achieving a very high CRI value here. So my message for today isn't to encourage you to use an excessive amount of glass in the designs of your building, rather making more mindful choices that promote both function, sustainability, and well-being. Thank you guys. Again, my name is Matias, and if you have any questions, please come over to our booth.
Thank you, Matias. Thanks. And thanks for ending on that great articulation, explanation of CRI. And I think it's something that I find myself reminding or explaining to young designers at our office constantly, especially these days in a time of Enscape and kind of ready-made renderings that are only getting easier and easier to generate with AI. I think there's a tendency to kind of see glass as a lack of material instead of what it often really is, like a very solid material with its, especially like standard IGUs with energy requirements being what they are and quite low CRIs. So yeah, that was a great reminder. Next up, we have Peter Dushenski from Glass Curtain.
Northern resilience. Zero tariff facades for net zero buildings. So thank you very much, everyone. My name is Peter Dushenski. I'm the managing director of Glass Curtain, and as many of you will already know, we're Canada's leading manufacturer of fiberglass framed curtain walls. For almost 15 years now, we've been developing and delivering building envelope solutions that leverage innovative material science to elevate new projects towards our nation's energy goals, carbon targets, and cold climate realities. And today we're going to take a closer look together at the Red Deer Justice Center. Who here has even been to Alberta before? Okay, almost half. Who here has been to Red Deer? Okay, like 10 brave souls, not bad. So this recently completed $250 million courthouse, which sounds like quite a bit until we remember that this was actually tendered in 2020, and if we did that today, it would be quite a bit more, as I think we can all well imagine. But this is a project that shows what's possible when locally made systems are specified with intention. This isn't about idle theory or pie-in-the-sky nice-to-haves, but about real-world results on a rather high-stakes and high-profile public building, and in a rather challenging climate, no less. So our journey begins in central Alberta. So the Red Deer Justice Center, did I skip one? Too many? Yes, sorry, the Red Deer Justice Center is an 8-story provincial courthouse, and it's actually the tallest building in all of Red Deer as well. If those of you who, the 10 of you who've been to Red Deer will get that joke. It's not a joke. So designed by DLR Group in collaboration with Group 2 for Alberta Infrastructure as the client. And as you can imagine, this project represented a major investment in the province's civic landscape. And it came at a time when the lifeblood of Alberta, its sort of major oil and gas industries, was frankly in the doldrums. But there was still a sense of optimism, particularly when it came to projects like this. And with performance standards on the rise, not just around energy and carbon, but also for durability, reliability, and long-term public value, the base building code compliance was obviously never going to cut the mustard. So the strategic decision was made to target Canada Green Building Council net zero standards to reduce life cycle costs, improve the quality of the interior environment, and ultimately reflect responsible stewardship of public funds. For the client and the architect, this meant that the building envelope needed to be of central importance and needed to make meaningful advances towards operational efficiency, cost certainty, and of course, climate goals. The facade therefore had to be more than just aesthetically attractive, reflecting the prairies and even sort of reflecting the northern lights. It also needed best-in-class performance on day one and then consistently for decades and even generations to come. And so this created an opportunity for a more thoughtful specification process. Because this was a public sector project, the design team could seek holistic building envelope solutions to reduce carbon over the building's full life cycle and also to think more deeply about procurement. Now, this particular project's procurement obviously happened before the world went tariff crazy, but it still had to manage COVID-era supply chain dislocations, which negatively affected so many projects that we're familiar with and that we've all experienced. So to the lasting credit of the design team at Red Deer Justice Center, they demonstrated to us all how a little bit of foresight paid all kinds of dividends for reliable delivery of quality products, minimizing unpleasant surprises down the road, and creating a kind of built-in insurance against unwanted risk. So how did this project manage to have its cake and eat it too? Well, by a little bit of planning. It might seem like, a while ago now that curtain wall specs, just focused. I thought it was great that we, had a shout out for CRI as well. these sort of narrow metrics, right? But these are the things that are easily calculated. It's U values, it's solar heat gain, even CRI, maybe even embodied carbon if we're lucky to find a good client to manage that as well. And these metrics still hold a huge amount of value in separating the wheat from the chaff. But it's also not hard to see that we no longer live in the boringly predictable world where that's all that matters, which is just fine, because it means we just have to adapt, which means that we need to focus more of our attention, not just on what we buy, but where it comes from, how it's made, and who it supports. So 100% Canadian supply chains are therefore now more critical than ever, and we needn't even get stuck in the political weeds to understand why. It's just a practical, pragmatic consideration in 2025. If the last 5 years have shown our industry anything, it's how fragile and frequently capricious global logistics can be, all of which introduce, of course, as we've seen, unwanted uncertainty and can often add cost to new projects. Whether we're building hospitals, schools, or courthouses like the Red Deer Justice Center, none of us can afford more delays to construction schedules and chewing up more of ever-growing contingency funds, which is why we're seeing more and more specifications take this into account. We all want reduced risk, shorter timelines, and faster troubleshooting, and that's exactly what Canadian manufacturers, like Glass Curtain, provide. And this is really what it's all about adding value. At Red Deer Justice Center, the decision to specify our ThermaFrame 7 fiberglass frame triple glazed curtain wall system on the 22,000 square feet of curtain wall here added less than 0.5% to the overall project budget, while guaranteeing that the glazing system was on time and on budget, and supporting, never hurts either, to support 15 local manufacturing jobs during construction with all the positive ripple effects that come with that. And not to mention on the environmental aspect, saving over 4,000 tons of carbon emissions by effectively doubling the thermal performance of a typical facade or business as usual facade from about R3.5 to R7 on this project. So in this light, we can see that procurement is a design choice too, one with economic, environmental, and social impacts. It's a choice to shape our domestic industry into one that's more resilient, more responsive, and better equipped for the ever-evolving landscape ahead. And of course, the buildings still need to perform, right? It can't just be sourced in Canada. It has to actually do the job. And thankfully, Canada has several world-leading solutions to lean on, even when targeting net zero, with -40 winter temperatures and +30 summer temperatures. The design team at Red Deer Justice Center didn't back away from glazing. Instead, they made the envelope work harder and smarter by specifying the ThermaFrame 7 system to limit heat loss, resist condensation as well, and reduce carbon impacts. The result was a relatively high window-to-wall ratio building, given the performance profile of the project, and with also a mechanical system that didn't have to be oversized to compensate for the poorly performing facade. Demonstrating that with the right materials, we can hold the line of architectural intent as well, while still meeting stringent performance targets, even in the most demanding environments. And it wasn't so long ago, that all this being said, it wasn't so long ago that the best, quote unquote, glazing systems had to come from overseas, right? We'd had to import, whether it's from Europe or Asia or what have you. But thankfully in 2025, we have world-leading Canadian-made options that deliver unbelievable high performance while offering something imported systems simply can't match, and that's domestic resilience. At Red Deer Justice Center, the design team specifying ThermaFrame 7 had complete confidence that our triple glazed fiberglass frame systems were going to be manufactured, fabricated entirely in central Canada with full vertical supply chain in central Canada as well, ensuring predictable local options with no customs or tariff confusion and uncertainty. So this was a purpose-built system for the climate, with our construction realities and our energy ambitions. This kind of homegrown innovation is becoming more and more important on every project as we continue to strive towards net zero and low carbon goals. The technology solutions we need to specify have to be trusted, which means leveraging local capacities to create true community ownership, while resulting in shorter lead times and, really importantly, again, minimizing geopolitical uncertainty. There's less, oops, I didn't see that coming kind of moments. Especially for complex public infrastructure projects like this, domestic manufacturing and know-how creates a kind of resilience that's becoming fundamental and increasingly non-negotiable as responsible design and delivery. So what can we take from this project? What does it tell us about where the world is heading? Red Deer Justice Center demonstrates that high-performance facades developed and manufactured locally, right here in Canada, are already succeeding. This isn't just a theoretical or future aspiration anymore. It's happening right now. And what we're also seeing is the start of a broader shift in how building envelope systems are being procured as well as specified. Not just as line items to value manage, and don't call it value engineering. There's no engineering involved, please. You know, it's like, I hate when they do that. This is not real engineering. Value managing at best, but as key levers for performance predictability and holistic economic development. The public sector has played and will continue to play a key leadership role in this domain, building momentum and creating alignment across the construction industry and a construction ecosystem, forging a path for private sector to follow. As design teams specify with greater confidence, as builders gain experience, and as manufacturers rise to the challenge with investment and innovation, policymakers get the real-world proof they need to inform future standards that benefit us all. So that's where we are today, at the beginning of a journey to align high-performance building standards with domestic manufacturing and climate objectives. Red Deer Justice Center is a showcase of what's possible towards these admirable ends, a future-oriented elevation of local supply chains and Canada's can-do spirit. In the next decade, we expect to see many more such projects, as well we should. In this frequently crazy world, if we can look past all the noise, we actually have a unique opportunity right now to create lasting value together. Thank you very much for your time.
So I was recounting with Peter at the break that our office actually worked with glass curtain using triple glazed fiberglass frames on a project up in Iqaluit that I had the privilege of visiting about 2 years ago, March 2023. So that time of year up north, about equal nighttime, daytime, but I remember it being almost minus 50 centigrade. And I remember being in the building and two things struck me. I remember two things very clearly. Just being so impressed by just the amount of natural light and how it stood in such stark contrast with everything else in Iqaluit, right? The idea that you could leverage that performance to bring so much natural light and hopefully set a benchmark for what's possible up there using that technology. But also I remember being minus 50, I had to touch the frame on the inside, I had to touch the glass, and it was all warm to the touch. So how's that for an unscripted testimonial? Okay, so next up, Jennifer Mallard from Enriquez.
Hi, everyone. Today I'd like to talk about a project that we have on the boards right now and soon into construction in Scarborough, here in Toronto, called Kennedy Green at 2444 Eglinton Avenue East, that's right at Kennedy Station. I'm a principal with Henriquez Partners, which is a Vancouver-based firm, has been in Vancouver for over 55 years, and with a growing body of work in Toronto, I joined the firm to lead their practice here. We are specialists in tall, urban, mixed-use housing developments and a deep history of partnerships with nonprofits, delivery of housing of all types, from high-end condominium to assisted living and social housing. In total, we've delivered over 6,000 units of rental housing, which is becoming, as you know, part of a critical conversation here in Canada and in Toronto. So we'll talk a bit about Kennedy Green. It's being delivered in two phases. The first phase is with the Co-op Housing Federation of Toronto. It's 306 units of market co-op rental and 306 units of affordable co-op rental. Phase two, the third tower, will be another 306 units, and it's currently condominium, although the developers are thinking about shifting over to rental. We're working with civic developments and windmill developments in cooperation. The Co-op Housing Federation of Toronto is obviously our client on phase one. We're working with RJC, Smith & Anderson, CCXA, Arcadis, and Arup for envelope, as well as other things, other contributors. So we'll talk a bit about the project background. I'm going to touch on sustainability goals and coordination, and deep conversations with design assist trades. So it's a construction management contract, and we're working with trade partners that were brought on early to help us with detail coordination and some of the detail considerations that are being ironed out right now. This is a transit-oriented community. You can see the site there, the triangular site in the middle. It's at Kennedy Station, which is maybe the second busiest transit hub in the GTA, second to Union. There's the Eglinton Crosstown, the Kennedy GO, just the TTC, and the Scarborough line. So it's a very busy, hectic site. And at the first DRP meeting, before we were brought on board, when it was just in a rezoning, or potential rezoning, some of the DRP members quoted this site as being undevelopable. So it's a challenging site, but we like challenges. You can see here the site there, that tiny white triangle. So as busy as it is in transit connectivity, it's also connected to the lush greenery network in Toronto that if you live here, you know the rivers and the valleys, but also the hydro corridors. So you can walk from our site through the hydro corridors and the river valleys, and there's a lovely, lush connectivity to this site as well. And you can see this here. Those hydro corridors provide places to walk your dog, ride your bike, and also what we're calling these guerrilla gardens, where the residences that back onto the hydro corridor have kind of taken over part of the hydro corridor to grow their carrots and tomatoes or sit out in the sun. So there's a lovely connectivity with that green network. So we wanted to bring that into our design narrative, acknowledging the existing site. We located the parking above grade, and I'm going to get into that a bit later. But we had an idea of pulling up this green carpet, metaphorically, on top of the parking podium to create a green landscape that's accessible to all of the residents who live there. Cutting through a connection through the site from Kennedy Station more directly to the hydro corridor, so that's public access, and then floating these towers on top of that green carpet. We're working with the One Planet Living framework. Windmill Developments is very much committed to this framework. It's an international sustainability framework that goes beyond LEED or TGS, where it's just about the building, but this is about operations as well, and quality of life for people who live there. So things like access to local food or access to diverse food options. So those things are on the operations side. But on the building side, commitment to geothermal energy, zero waste. So in the construction process, recycled content, things we're all familiar with. And then we look at how that One Planet Living framework relates to TGS, and we're complying and surpassing version 4, tier 2 of the Toronto Green Standard. So both are strong frameworks, both are goal to reduce building emissions and zero waste and biodiversity on the site in terms of planting and interaction with nature. So we are surpassing TGS, and what we'll talk about a bit more today are highlighted in yellow. We've got a pretty aggressive window-to-wall ratio. We've got a super insulated envelope, so lowering our thermal energy use intensity, and we have no balconies. There was mention earlier, balcony or no balcony, but with concrete buildings, and this is a concrete building, the decision to go no balconies drastically reduces our thermal bridging in our energy model. So here are some of the sustainability initiatives we're using. We're net zero carbons, we're operationally. We've got a geothermal energy system, we've got a low window to wall ratio, And again, green roofs surpass the TGS requirement. And just to flip through some plans, just to orient you on how this project works, it's built in 2 phases. The phase 1 is the podium for 2 towers, the entry to the garage. Phase 2 will be the 3rd tower, the condominium. As we go up to the podium, where there's great green gardens on top, that green carpet that's pulled on top of the parking podium, community gardens there, you know, kids' play spaces, dog walking spaces, the outdoor yoga room, and the towers emerge from that green podium. Here's the unit plans as we work up the tower. So a couple of opportunities here. I mentioned our decision to go with above-grade parking. We have contaminated soil. There was a former auto body parts plant on the site. It's not incredibly toxic, but nonetheless, we would have to manage that soil. So that means either extracting it and, you know, dumping that problem on somebody else. We chose to encapsulate the soil and then build above, and we're not going into the ground. So that decision of not putting a parking garage below grade drastically reduces the amount of concrete in the whole project, and therefore reducing the carbon footprint of the project. The exclusion of balconies, again, reduces the thermal bridging, reduces the amount of concrete. And those 2 decisions reduce time in the ground, go down in time to get back up to grade, and reduce overall project costs, and therefore the client can invest those cost savings into the production and delivery of more housing units, which is ultimately the goal for the Housing Federation. So why did we choose precast? If any of you know the Office of Henriquez, we love design, we love to play, and precast gives us an amazing ability to play with the facade. At the same time, we know that this is affordable housing. We have to make this cost efficient. So precast actually gives us the opportunity to make fun elements that are immensely repeatable. And then we drive down into the production of the precast elements in order to make that more opportune. We all know that the cost of the facade represents 30 to 40% of the total construction cost. So everywhere where we can save pennies on those repeatable elements, it has a bigger impact for the whole project. This is a tall buildings. So the tallest one is 40 stories. The phase 2 tower is 30 stories, and the smaller tower is 18 stories. So with repeatable elements, we need to build in that element of play and that element of texture. So color can help us there. And so very early on, we develop a color application strategy, which you can see here. The color is applied to the precast panels, and it morphs its way as it goes up the building. So as I mentioned, repeatable facade elements, rigorous grid dimensions, standard floor-to-floor heights. So even at the mechanical crossover floors, and we make all the floor heights the same height so that we can have the precast element the same all the way up. So architecturally, that makes a big difference to us. And repeated floor plates. So getting our unit mix right to meet the client's demand, but maximizing repeatability as we go up the tower makes construction easier, more smooth, more efficient, and more cost effective. So I mentioned rigorous grid dimensions. So we're working with a 6500 double window panel, and we also have a half panel that's 3250. So we use those dimensions all the way around in a very rigorous approach. That 6500 gives us the width for a bedroom and a living room. And then the half panels give us the opportunity to incorporate 2 and 3 bedroom units. So those models, the modules are based on that grid dimension. We've got a height of 2950, as I mentioned, that goes all the way up the tower. So those modules also check in with our precast assistants. We're working with Res Precast out of Barrie. And it's not our first project with Res Precast, but nonetheless, we learn more every time. So that module suits the manufacturing process within their factory. It suits the shipping logistics, and it suits the crane capacity. So we've already calculated the weight of this panel, and they've identified through our CM what crane is appropriate. So all of those decisions in the design assist process are really informing the design at an early stage. We first approached this with the desire to stagger the module joints, as you can see in the tower, because we thought that would add a bit more dynamism with the panel in this 40-story tower. So the little diagram on the right there is the dashed lines are the columns, and then the precast modules. We develop a kit of parts. So there's the double panel module and the single panel module that you can see on the top left. We develop some preliminary details. There's a corner module that negotiates the corner of the column. But we learned as we moved into the design in more detail with our structural engineers and our envelope consultants. So the anchoring points to those panels, and those panels are 8,000 pounds, so they're heavy. The anchoring points are 1/5 of the way in from the side joint. And we look at where those anchoring points are in relation to the slab, and we're looking at slab deflection and the anchoring point. And we want to make sure the anchoring point is at the location of minimal slab deflection. So, and then we're considering the joint size. So we want a minimal joint. An ideal joint is 25 millimeters. But if we have to accommodate a larger slab deflection, then we're looking at a 40 or 50 millimeter joint size. And we want to make the joint size consistent all the way up. So we have to reconsider a few things. So each panel, and the little red lines are those anchoring points that are sort of 1/5 of the way in from the sides. Each panel has two bottom, and here we're bottom loading, so there are two bottom loading anchors. They can be hung as well, but this one we decided to bottom load. So two lateral movement joints and two panel-to-panel connections. So there's a lot of stuff going on in the back of these panels, and we're looking at where they coordinate in the structural grid. And we have 3 locations in this floor plan that are problematic for us. And we'll focus on the one on the top left. So in that 3-bedroom unit, there's a double bay and a single bay, and if we have an anchor point at that single bay, it's a double bay, then it's at a point where the column isn't right at the slab edge, and we're dealing with deflection there, and similar problems below. We're dealing with Arup as an envelope consultant, and this coordination from identifying that problem to coming to solutions, to figuring out what to do, to determining the joint size took us, I don't know, a month and a half or something. And Arup came up with these 3 options. We could do one single panel that's 3 bays, but then that's too heavy and too large for shipping. We could make the panels individual and then clamp them together so that they act as one panel in situ. And then the third option there is to make them bear on each other, so we're not bearing right at the greatest slab deflection point. In the end, what we decided to do was change the structure. It was proving to be too difficult, and we wanted to really tight joint size. So So we extended the column up to the face of the building, and we changed the panel divisions on the lower facade so that the joints were aligned with structure. Then we move into a bit further coordination. Originally, we had 36 panel types, and in the precast and custom precast manufacturing process, we want to really reduce that down. So the different window sizes, and we've got different window types for bedroom, living room, kitchen, and in different combinations as they go up. We learned that one mold can be blocked off in different ways, so that the windows can be a different block off, accommodating the different sizes of windows. With one mold, we can block off half, so that we get the half panel module from the mold that is a double panel. So we reduced the panel types from 36 down to 6, and in some organizing of the units, we reduced the window combination types down to 9. So it's a pretty careful coordination with res precast. And then we map it out so this is the largest tower, the 40-story tower, and you can see how those modules are all scheduled and mapped out. So we're rigorous with our unit mix that goes all the way up the building. And tricky meeting the client requirements for unit mix and making this pattern happen. But nonetheless, it feeds into the efficiency and giving us the construction budget room to play with custom precast. In developing the details, we learned through res that the minimum thickness of a precast panel is 100 millimeters in order to get some reinforcing in there. So our thinnest point where the window cutout is 100 millimeters, and then we can play with another 150 millimeters. So there's 250 millimeters maximum depth there. And of course, we're modeling this we've got a parametric model going, so we can push and pull those little high points and we look at it with the sun and shadow and pattern going up the building. So as I mentioned, we have a bottom-loaded anchor here. So the anchor is embedded in the precast and comes over to the slab edge. We've got a 25 millimeter joint, and it's a double joint seal. So there's a joint that's on the inside and a joint that's on the outside, so that meets our rain screen requirements. Sustainability considerations. We've got glazing to meet the TEDI requirements. So we toyed with fiberglass or aluminum windows. We're going with aluminum windows and some triple glazed to meet the TEDI requirements. So Tower A has a higher perimeter to floor area ratio. Therefore, the envelope has to be a higher performance envelope, so we're using triple glazing there. Tower B, because it's a larger floor plate, has a slightly lower perimeter to floor area ratio, so we can use some double glazing there. However, this is a very busy site. It's right next to a train line and a highway, and acoustics is a consideration. So there are some locations where we might want to use triple glazing for acoustics. But then working with the acoustician, it turns out a triple glazing window doesn't necessarily perform better than a double glazing window because it kind of acts like a drum. So it transfers sound energy inside. We ended up, we've got this pretty special recipe for some double glazing units that have a different pane thickness on the outside and the inside pane in order to interrupt that sound wave and get a better acoustic performance within the residences. We're using a green gird, so a fiberglass angle, but it's continuous all sides around the windows. That's to improve thermal performance and also air penetration and the possibility of condensation. We've got a minimum of 150, and here it's 200 depth of spray foam insulation on the insides, and so that's a deeper stud on the inside than might be normal, but nonetheless we need that for insulation. And then we've got a 150 millimeter gap at the slab edge, where 100 millimeters might be more typical. This is deeper in order to get more insulation right at that vulnerable thermal spot. So in the end, we run our energy model and we can see that the highest energy uses are actually from personal uses, from interior lighting and miscellaneous equipment, and the heating and cooling loads are way down. Similarly, if we look at our energy modeling report, the energy use intensity target with TGS version 4 tier 2 is 100. We're below that at 70.9. Greenhouse gas intensity, we're way low because we've got geothermal energy and we're net zero carbon. And the overall thermal energy demand is under the target for tier 2. So I guess we don't have time for questions, but we're delighted to be working on this project, and it's becoming a bit of a poster child for innovative housing in Toronto. There was an article in the Star yesterday about fast delivery, and it's ticking a lot of boxes with the city. It's co-op housing. It's the first co-op project in 25 years, first new co-op project in Toronto in 25 years. It's geothermal. It's net zero, it's rental housing, and we're super excited to be, we'll be in the ground in November. So, thank you.
Jennifer? Yeah, thank you for that. I really loved seeing the combination of rigor and play. And I can really share in a lot of what you said. I understand your general positivity, your firm's embrace of precast. I think it's something that we also share at Teeple. And one thing I always, the point I always try and make with clients, collaborators, maybe even critics of precast is just that really precast, although it's simple, it's kind of a dirt simple, even like, dare I say, cave person level of technology. It's really arguably one of the last bastions of true craft, local craft, in the sense that the GTA does have some really remarkable precast trades and suppliers that are really supplying amazing precast all over North America. And it comes down to carpenters, right? And a special kind of carpenter who needs to see everything in reverse, needs to understand every building, every project they work on in inverse negative volumes, right? So it's almost like a Rachel White-Reed sculpture. So anyway, just a thought, but yeah, we're also big fans of precast and love the level of rigor and play in that project. I think next up we have a panel. Okay, welcome back everyone. Hope everyone had a nice lunch. We'll do the 7th inning stretch apropos all the Jays stuff, but I guess when would the 7th inning be? Between the 3rd and 4th session? It's too early for that. Okay. It's a real pleasure to introduce a good friend of Teeple Architects, someone with whom we're very proud to have collaborated on as architects of record on the Schwartz-Reisman Innovation Center at the University of Toronto, Matthew Ferraro with Weiss Manfredi from New York.
Good afternoon, everyone. Hope everybody doesn't have their food coma and is excited to get back into the swing of things. As Tomer said, my name is Matt Ferraro. I'm a principal with Weiss Manfredi Architects in New York, New York. I've been with the firm for almost 15 years now, and I had the privilege of working on the Schwartz-Reisman Innovation Campus, which after the conference, if you want to take a short walk up University Avenue to College Street, you can see in person for yourself. Talking about the building and its context, you know, we were asked in 2017 to participate in an RFP with a number of international architects. We were successfully chosen and really excited to have this opportunity. This is our first project in Canada, and our partners, as Tomer mentioned, were fantastic to work with. I'll just mention Teeple was the architect of record, but their their work speaks for themselves as design architects here in Canada. So you can obviously see how the collaboration was one that we were very proud to have. We also worked with Thornton Tomasetti for the structure, which I'll talk about a little bit, and also RJC and Heinches for the envelope consultancy, amongst a myriad of other consultants that helped make this project a realization. When we started this project, it was part of a secondary campus plan from the University of Toronto. There were no givens. We were told to imagine the site in a way that we thought was both contextual, but also programmatically advanced for the work that they wanted to house in the building. So we started by thinking about this not only as a location for the campus, the easternmost portion of the campus for U of T, but also how did it relate to the Mars Discovery District in the neighborhood and to the greater skyline and city that is Toronto. So when we started to look at what does this building need to take advantage of, what does this building need to respond to, what guidelines does it have to respect, we started to look at it from the 5-minute walk, 7-minute walk scale. And the campus that you see in the center there essentially creates a gateway with the already existing Leslie Dan Faculty of Pharmacy building that Foster and Partners designed several years in advance, and we were framing the new gateway to Queen's Park and Legislature. We were on the hinge of the Discovery District and the large medical district, which you obviously all know much better than I in Toronto here. But we were also framing the four corners of what U of T considered its campus. So the site, as amazing as it is, was quite constrained for what the ambitions of the university really wanted to do. So they had ambitions to house startup from graduating startups, new startups that postgraduates. They had professionals that are in the industry, and we're already talking to Vector Institute for Artificial Intelligence. So how do you get 200,000 plus square feet on a very small rectangular site at this historic landmark? So we started to think of the building as a vertical campus. So here you can see the zoning massing. This was given to us as sort of the brief, the sort of podium, setback, tower configuration, which is a formula that the City of Toronto uses quite regularly. We, being a little naive, wanted to start to think about ways to challenge that independent volumetric expression into one sinuous expression that accomplished both. So you can see we started to think about how vertical connective spaces can open up views toward the campus, towards Legislature, towards the Discovery District, but then we started to formulate a response to shadow guidelines on Queen's Park. So you have here a diagram. We were asked as part of our work on phase 1 to also conceptualize and think about the future phases of this project. So what you see in poche in the dark gray are the heights that would be within the permissible guidelines for not creating new shadows on Queen's Park as part of the tall building guidelines on September 21st from 10 a.m. to 2 p.m. It was a very, very specific time frame. And we learned rather quickly that Toronto actually takes into account daylight savings time, where a lot of other jurisdictions don't. So let's say there were a lot of quick fixes during that investigation early in the design. But what you start to understand is that we're on a corner, we're creating a gateway, but we're also creating a relationship not only to the park, but also in respect and in reciprocation to the heritage building of the old Toronto General Hospital across the way that is framed by two contemporary structures on either end of College Street. So here you can see, this is a visualization. Phase 1 is the smaller Tetris-like tower toward the background, and there are ambitions to expand this further to the east to the heritage building that's the Zion Church, which U of T also is going to undertake to convert and restore back to its heritage conditions. So like I said, you have a box, you have your boundaries. What are the ways that we can start to create areas for commingling, for bringing disparate parts of separate programs together, because the whole impetus of this project is you're going to have startup companies that are learning, that are being innovative, that are trying to challenge some of the technological norms, whether it be through AI, whether it be through robotics, et cetera. And there's also professional companies that are housed within the same building. So how do you force rubbing shoulders in a way that people talk to one another and share ideas? So the idea was that we started to push back to respect the shadow guidelines. We started to carve out key datums for visual connections to and from the city, and then connect them through a circuitous setback reveal that acts as a way to connect all of the different floors in the public realm. So as I mentioned, we're looking at this as a series of public spaces and private spaces that are meandering through a 13-story building. How do you get people to have a sense of common space where they can commingle and get together, or even have programmed events around what they're doing and all the important work that they're doing in the building. So I'll just walk through quickly some of the floor plans just to give you a sense of orientation and the scale of the building. This is the first floor. As part of the zoning guidelines, working with the city planning, working with the university, we have a more generous setback as part of the rebuilding of the campus along College Street. So you see a series of rain gardens there with public seating along the lower portion of the plan with the trees. And then as you enter through a very transparent facade, which I'll talk about in a little bit, you have this very public lobby space. It's activated by a restaurant that was later developed and designed in the top left quadrant there. There's a cafe, but it's also where everybody meets in the morning before they go up to their office spaces. On the second floor, in a physically and volumetrically connected space, there's an overlook along the ledge of the mezzanine, and this is where most of the public programming happens. This is important for two reasons. One, they wanted the most clear spans, and this wanted to be down low because of the egress requirements of the building, but it also created a really challenging structural resolution to have clear spans at your greatest load within the building. There were flexible classroom spaces as well as a large gender-neutral public restroom on this floor. Then there were a series of floors in between that were all for tenant space, and it was designed to be both single tenant or multi-tenant. This is the 7th floor plan. This is the first floor where we are back together again in a public space. One thing I'll mention, the university had very strong achievements for energy usage. They wanted 40% over ASHRAE 91, 2013, I believe it was at the time, which was an aggressive goal. And that's something I'll talk a little bit about. How do you do that when you want a level of transparency in a facade when that's not always the most optimal for your U or R value for the building? But you can see here, as we ascend the building, one other thing that we did as a design trick or goal was to actually make what's usually typically a core element expressed on the building. So you'll see on the left-hand side there's a rather generous exit stair. That's for life safety, that's for fire egress. It's the giant reveal you see along the corner of College and University, and it was encapsulated in fire-rated glazing to allow natural light to permeate into the public corridor spaces for the multi-tenants. As we work our way up, these carves and these cuts interconnect again at the 10th and 11th floors. So each of we call them winter gardens. There's an ambition, and we're working with the university to further that ambition, to have the level of biophilia, as you heard earlier in other presentations, within these spaces, particularly around the cold winter months that we know Toronto receives. And so 7 and 8 and 10 and 11 were connected in the sense that they're double volume spaces, even though they're atmospherically separated for fire separation. So again, how do you take all of these different entities and organize them in tight floor spaces? As you can see here, we started to work with the university on how to allocate certain core tenants they knew they had at the beginning of the project and leaving spaces for future tenants, which the building was fully leased out before we were finished with closing out the punch list. So it's a testament to how excited people were to be in a new working environment. So here's a picture. This is looking sort of behind the Hydro building from the Leslie Dan Faculty of Pharmacy buildings to the left. That's the old Best building that was on the site. And here are some really amazing winter shots that one of our photographers were able to capture while I was in a cab ride back to Pearson that day. So really glad he stayed behind. But you could start to see how the building's volume is engaging the corner, but also breaking down its scale to relate to existing context. And you can see here the old Banting building, which is recently been removed, was at the same datum as the old Toronto General Hospital across the way. So the way that we were addressing the secondary plan, the podium and the tower, was to keep one sinuous tapered form, but create these inflections and these carves at the key datums that would typically be seen by the height guidelines of the tall building guidelines here in Toronto. And city planning was really excited about this approach. It was very different. We personally really liked the way that it came out, but I think we were trying to think creatively in a way to be respectful, though, of the city's built form. So getting into facades, right? That's why we're all here. Early sketches, thinking about geometries and form is one way. We work in our office in multimedia, so we'll do hand sketches, 3D prints, laser cut models, hand cut models, and then CAD Revit drawings at 1-to-1 scale. So we're very interested, in the overall impression, but then actually how the thing resonates and gets built. So as part of this, we started to think about 3 major material types. I'm sure everybody's familiar with budget. So when we were in the early stages of design, we keep a lot of things on the table when speaking with our clients because we want this to be a mutually agreeable approach to how the building gets realized. So we looked at 3 major facade types, one being precast, one being glazed terracotta, and one being metal panel. In the end, we went with the precast for a myriad of different reasons. One was ultimately based on cost, but 2, it was important for the city and ourselves to have a material that was relating to the chromatic and physical expression of the Ministry of Finance building, the old Toronto General Hospital. We were surrounded by a bunch of new architecture, but at the same time, we were right at the interface of heritage architecture that was part of the city. So we didn't want a pure glass resolution for this tower. We wanted something that respected the old, but represented it in a contemporary fashion. So we started, here's a shop drawing that can show you the level of complexity. I actually wish I showed you all the panel drawings, but essentially the tapered form, there's a lot of that happening in contemporary architecture, but the diagonals of the precast were actually working hard to make sure that the geometric resolution of the tapered form made sense and took shape. What we found, we were just digging the hole when COVID hit. So a lot of what you're going to see are our colleagues at Teeple's office going to various fabricators' plants and us being on FaceTime in New York from our homes reviewing and approving things. It was quite a very unique way to go through construction administration. But I believe, in a previous presentation, we saw the thoughts about how precast concrete gets fabricated. And here, the notion of carpentry being as important as the precast trade could not be further true. We had 70-ish different panel types on this project. The way the project worked is that all the punch windows were the same size, but the the plastic material of the precast was taking up the difference as the form tapered toward the sky. So our wonderful fabricators at Tricrete here in Canada came up with a solution for fabricating their formwork in a way that allowed them to make incremental adjustments to meet the different mold requirements for the various panel types. So you can see here, carpenters, basically almost mill workers, building the formwork for the project. They actually had a CNC machine cut out all of the forms, label them, so that it could codify them to build the forms for the panels. And you can see here, this is after one of the pours, and then out in the yard. And this was a fun FaceTime moment to get to see this for the first time. I'll say we didn't get a chance to be up here until about 2/3 of the precast was up on the building. So you can imagine the excitement when we actually got back to see this in person. But here are some of the details. In working, Heinrich's office worked with us carefully on the aluminum and glass systems, and RJC worked carefully on the thermal analyses of the precast system to achieve that thermal tightness, but also to look at some integral details that were critical. As you saw, the panels are shaped as a Roman numeral 2. That leaves a joint at the head and sill of center point of each of the windows. So careful considerations for waterproofing and flashing were needed to achieve this panelized design. You see some of the first installation photos here. And then this is a photo of one of the labs on, I believe, the 6th floor, and you can see the quality of light through the punched facade. The punched facade also was part of that multi-purpose room that I pointed out on the 2nd floor. Here we have a curtain lightly veiling it in the background, but it was something remarkable where you could start to see the staggering shape all in one space. The other major wall type on this project was our stick-built and mega-panel-built aluminum and glass curtain wall. And what I will say is when we went out to bid, we were AESS steel and glass for the entire system. Naturally, as we're going to work, our CM on this project was Ellis Don. We were working with Antimex at the time for the curtain wall and stick-built system. They proposed an almost identical system out of aluminum. There were some caveats we had to accept with larger horizontals at the mega panels, but it was a small price to pay for what we believe is an even better resolution to what we had originally designed. So it's really important to listen to your industry partners because sometimes their expertise and their experience will guide you in a way you didn't even know was possible. Here you can see an image of one of the mega panels being fabricated at their shop. To the right is the monumental fire stair. And I should note that the precast came all the way in, which led to some logistical discussions with Ellis Don on that. But at the end, it's really remarkable that the outside continues fully in. You can see a shot here from the fire stair looking back out into the distance to Legislature and Queen's Park. On the winter garden floors, this is obviously a finished photo, but the double height space is actually stick built. So although they look nearly identical in interior and exterior detailing and sight lines, the form of resolution or the form of construction changed relative to the positions on the building and what was possible. Here's the ground floor, so a very porous entry welcoming people in and a monumental stair welcoming people up to the 2nd floor, which was the main public amenity space for the building. Ironically, or maybe not so, the Fireman's Memorial led right to the fire stair. It was something that was a little bit serendipitous, but something we like to say we planned. But as you can see here, those carves and cut really not only illuminate the building, but showcase circulation and social gathering with terraces at the 7th and 10th floor winter gardens in the nicer weather days. And lastly, I'll just rotate around the building. You can start to see how we were considering even the punched windows of the Frost building of the Ministry of Finance, how that could be reinterpreted into a new form, respectful of the old, but looking to the new. Here's one looking back down College Street, and you can see the reciprocity between the old and new at the Mars Center, and how we were planning this for the second phase and first phase of this project as a contemporary sibling across the way. And then I'll just leave you with this, what I like to call the hero shot, at 4 o'clock in the morning, jumping up and down, turning on the light sensors to get this shot. So we don't only design, but we actually get out there and wake up early to take pictures. So I thank you all very much, and I hope you enjoyed this presentation. Thank you.
Thanks, Matt. That's a beautiful shot. I had no idea you took it. So, next up, I'd like to welcome Krista Palen, partner at Transolar Climate Engineering.
Okay, just making sure the clicker worked. Thank you so much. I am Krista Palen. I am a partner at Transolar. I work with the Transolar New York office, but I'm based here in Toronto, which gives me the opportunity to work on great projects like this. Just a very brief introduction to who Transolar is. We call ourselves climate engineers, but we are sustainability consultants that work on basically anything in the built environment. We have this philosophy of high comfort, low impact, that buildings that are low energy should not be uncomfortable. We have 3 offices, 100 people, and we have been operating for about 30 years with more than 2,500 projects. Some projects huge, some projects tiny, and all over the world. And although we are engineers, primarily, we have some architects on our team as well, the kind of process that we tend to use for our projects is much more similar to that of architects, where at the beginning, we try to keep the solution space as open as possible. We ask a lot of questions, and we explore and iterate as long as we can before coming to a design decision, at which point we simulate, we assess, we look for precedents, and finally start to kind of do all the right sizing and the detail kind of process. But this first phase is absolutely critical to achieving innovation in any project. So as I mentioned, our goal is to foster innovation in the built environment because we believe that our world deserves better than building as usual systems. And we really believe that design and engineering have to work together in order to create these spaces to shape our lives. Again, the process that facilitates this actually happening, vision setting, idea generation, this advanced simulation and technical analysis, very, very critical, but not useful unless you know what you're aiming at. Design integration, technical coordination, and of course, storytelling and communication. And again, we've been very lucky to work with amazing architects all over the world on incredible projects. And so Limberlost. Typically, I've been doing this presentation with the whole design team. So you're just going to get my part of it, but the design team is Moriyama Tashima, Acton Austri, Introba did the mechanical, George Brown College, obviously, was the initiator of the project. And this whole project really started as a design competition. People in Toronto may remember quite a while ago now. A very ambitious challenge was set out. 4 teams were presented all really incredible options for the final project, and Moriyama and Acton Austri's design was selected. We were involved with the project even in that early stage, and the competition really asked for a net zero carbon project. And what we decided to do as well was to really have natural ventilation be core to the whole project, from the form, execution, and everything. And so from that, we originally would have had a chimney. So when you have natural ventilation in a building at this scale, you need the intakes. That's easy enough. You have windows. But you also need a place to exhaust the air. And in classrooms, you need so much air that you can't just do single-sided ventilation. You need to have an intake and an exhaust point. And so a common solution is to have these kinds of solar chimneys. Solar chimneys, the solar part is just a small component. It's really about the chimney. It's about the difference between the indoor temperature and the outdoor temperature. It creates buoyancy in the chimney, and that creates flow up and out the building, and that flow up and out the building pulls air into the spaces. Because there was already a building to the south, which I will show, I want to come back to this, but let's see, no, not this one, the Daphne Cockwell building. We couldn't put the solar chimney on the south side, so we decided to put it on the east and west, which still do have really good solar access, especially on the east side of the building, because it's facing a park. We decided to put two chimneys. Again, when you do chimneys, if you want them to be really effective, you need to give yourself a lot of space. At the edges of the building, we created these breathing rooms, which are a type of active circulation. They're usable study space, double height spaces, that are the entrance points to the solar chimney. And again, the chimneys weren't able to go all the way to the ground floor, and so in the interconnection of the air volumes through the first few floors were also very critical part of the form of the building. You can see it all flows through, and a lot of analysis was done to make sure that the airflow was going to end up in the chimneys as well, and that was going to be sufficient pressure to create enough airflow and natural ventilation. Again, this is the section. The slope roof, as you can see, was also a really important part of the facade because we have such high ambition for carbon performance. We wanted to optimize the amount of PV we're able to put on, even though we're blocked to the south. But basically, by popping up above the building, by tipping to the optimal angle, we're able to have this completely free area of PV that produces a not insignificant amount of renewable energy for the building. And the chimney also only works with the stacks. So the top two floors have access to wind pressure basically coming in off the lake. So they have enough wind pressure on the front and back to just have cross ventilation, and they open up on both sides. And the top part of the chimney just serves, even like the 10th floor there has a double height stack above the space so that it has also enough stack effect to have natural ventilation. Okay, so I want to talk about mechanical systems a bit more. And the reason is because, of course, to make a building like this work, of course, the facade system and the mechanical system have to work in an integrated way. Otherwise, it's just not possible. And even further, in passive mode, the facade system really becomes the mechanical system in a sense. And I'll explain that a little bit more in just a sec. So in active mode, which is heating, cooling, there are two small dedicated outdoor air units per floor, one on each wing. And they provide only minimum ventilation. Air is intake from one side of the building into this. Oh, I can do this, can I? Okay. Into that little green box. It is then sent to the underfloor, pressurized underfloor system, where it's delivered to each classroom. Each classroom has CO2 sensors with VAV diffusers. The air comes into the room, is used, and then it follows the same pathway as the natural ventilation system back out, which is through the acoustically protected transfer vents, which span the length of the room into the corridor. The air goes back down the corridor and through the door of the mechanical room back to that unit for energy recovery, and then up and out. For the additional heating and cooling that needs to happen, we have radiant panels in each classroom all over the ceiling, which are connected to the district energy system. In passive mode, again, the only way you can make something like this work is if you try to use the same airflow pathways as much as possible for the active and the passive systems. So in the passive mode, the facade is also part of the mechanical system. It is the first pressure drop point as the air comes into the space. And the air is coming through these windows. They are manually operable by the occupants, and they're indicated to open the windows when the thermostat turns green. The air comes into the space. They're able to control the airflow based on how much they open or close a window, just like you do in your house. And then the air comes up and goes out again through that acoustically protected transfer vent, down the corridor, to the breathing rooms. The entrances to the breathing rooms, we have, this could be the next one. Come back to this. We have these. Okay, let's just go back. Oh yeah, there we go. Finally got there. These are the automated windows. They open towards us into this breathing room, and they are controlled by pressure regulation into this chimney. This is the chimney on the east side. There's Carol Phillips. They're doing a tour. And you can see inside the chimney, we have these shades. Those are really important if you have a solar chimney for many reasons. Number one is that you don't want your solar gain getting all the way into your space and overheating your space, and then you have to do unnecessary cooling. Number two is that solar energy does not turn into heat until it really hits surfaces. So you're trying to create as much surfaces inside the chimney as possible so that the chimney heats up, the space doesn't heat up, and also people are not dealing with glare and things like that. And these if you look at them at different angles, they have a lot of geometry. They actually look quite thin at some angles and more opaque at other angles, and that's aligned with the optimal solar angle that we were trying to protect. Okay, back. Yeah. So after they go up the chimney, the air goes up and out at the top there. Again, this is what the classrooms look like in section in terms of the control between the natural ventilation and the cooling mode. And the facade. So the facade is, it was unitized facade. It came prefabricated to the site. The cladding is metal and fully operable windows all throughout the classrooms. We did a lot of optimization for both energy performance and daylight. You can see the windows are as high as possible to the ceilings intentionally to create as much daylight in the classrooms as possible. Again, we have 29% glazing, but still really, really good daylight inside the spaces. This project had a lot of design assist, a lot of research that was done. There was a research grant, especially associated with doing the structure. I'm sorry, I can't give you as much information about the mass timber. There's honestly so many different aspects of this project to talk about. But again, the facade was really developed with this design assist program and installed on site very successfully. And you can see what it looks like when the windows are open. We've gone through a few different iterations of window operating systems to make sure that it's extremely usable, because the most important thing when you're designing natural ventilation systems is that you design window operation systems that people actually are going to want to use. I think in the first iteration, they ended up being hidden behind the insect screens. So people would have to lift up the insect screens to use them. That's not going to work. Or if the cranks are too difficult, or all these kinds of things, like small impediments can really break down the whole thing. They need to be easy, and they need to be obvious in terms of how people can use them. Again, so this is back to this kind of idea of how is the facade and the building itself really part of the building mechanical system. And so in passive ventilation, just like when you're designing a mechanical ventilation system, there's lots of pressure drop points along the way. So every point indicated here on this plan, so you can see the classrooms are really located on the north and south of the building. But the red is windows, the orange is the acoustically protected transfer vents, the blue is the intake at the solar chimney, and then we have the exhaust again. So those are all pressure drop points. And the important thing, we looked at this already, this is the, in the corridor, what the acoustically protected transfer vent looks like coming in, and it looks similar on the classroom side. We went with this design because it really allowed us to get a ton of free area. You know, when we're designing these things, we're always telling the architects that you need to save a ton of space in your partition wall for these acoustically protected transfer vents, because you need a lot of baffling in order to actually take that sound out of the air. And so it creates a big pressure drop, and the way to overcome that is have lots and lots of area. So this, I think, is one of the best solutions, is to just have it at the intersection of the ceiling and the wall. I want to go to this one first. Okay, again, this is the same diagram we just looked at, but just with a pressure flow. And this is what that diagram, those same pressure drops look like if you compare them to the available stack effect at every floor. So this project doesn't not actually have a fan or anything like that in the chimney. Sometimes we do design chimneys or any kind of stack effect building with an atrium to have an exhaust fan at the top that can kind of override everything and create some pressure and pull air through the windows, still give people the experience of natural ventilation. But this building doesn't have any of that. We're truly just relying on stack effect. And so you can see that at the lower floors, we have a ton of stack effect available, and at the upper floors, we are basically just at the very limit. And that's how it happens. And you know, it may be possible that sometimes that the top floor ends up being in mechanical ventilation, the lower floors are not, just because of the available stack effect is not enough to get the airflow. And the building is set up to do that. That's why we have such a nice modular mechanical system. So anyway, we are also able to regulate the pressure a lot through these breathing room entrances because we're able to modulate the openings of those automated windows. And it works a lot like a circuit system, actually. Going back here. The other big piece of this passive chimney is this damper. So the way that the opening of the chimney works at the top of the building is that we couldn't put the opening facing with the slope towards the water, because you know, when the wind pressure would be coming off the lake or from the west, as it often does, or even from the east, that it would just, the wind pressure would hit the surface and basically destroy all our stack effect. It would be putting wind pressure on the opening of the outlet, and so no air would want to come out of there. And so what we did instead is we have, this is us standing inside the chimney, and then this is me standing again on the slot on the other side. So we have a vertical damper inside the chimney, and then we have this slot, which basically allows us, the air is coming in off the lake, it will zoom through there and actually create more negative pressure on the damper because as the air is passing by another surface, it kind of creates a negative pressure. And the same with the other wind directions. So in this way, we were able to kind of create this protection that worked also for rain and other kinds of things. And finally, just to talk a little bit about the energy. Again, this was a very ambitious project with a lot of detailed look at the facade. All of the facade was focused on doing all the very detailed thermal bridging analysis to make sure that it was absolutely minimized. For those, probably most people are from Toronto, so everyone's familiar with the Toronto Green Standards, but we were going for Tier 4. So the EUI target for Tier 4, 65. The thermal energy demand target is 15, and the GHG target is 4 kilograms of CO2 per meter squared per year. And in all of those, we actually ended up exceeding the targets. As you can see, the EUI of 57 there is helped by about 3 kilowatt hours per meter squared of PV that's produced from the roof. And so we were really happy. And you know, you can see that the heating and cooling of this building is really tiny compared to everything else. And you start to think, Other things are really important, like electric lighting actually ended up being a really important one. Plug loads. Once you get down your heating and cooling really down, then the other kind of energy uses start to become really significant targets. And the other piece that really allowed us to be so successful in reducing the energy is that we did connect to the N-wave system. We were able to have the COP coefficient of performance of about 12 on cooling, which is, I mean, amazing compared to any other system. And for the heating, again, we are connecting to N-wave where they have a plant that has heat pumps where they take water back from the other buildings on the N-wave system and heat it up. And again, really good efficiency on the heating side as well, and all electric and very low greenhouse gas emissions. But overall, this project, I think, was an absolute pleasure to work on. The team was, everyone worked really well together throughout all the different, challenges that came up. It wasn't, oh, this is impossible. It was, okay, this is challenging. How can we work through this? Again and again and again, people stepped up and people took time to make it happen. And I really want to thank George Brown, Maureen Matishima, Acton Austri for making it happen. Thanks.
Thanks, Krista. That was really fascinating. I think there's a lot of fans of this building here in Toronto and elsewhere, and I think the mass timber story is such a big part of the media coverage to date, and I found it really fascinating to have that window into the mechanical strategies as well. And I think thinking of the framing of on building envelope as an integral part of the mechanical system is really evocative. So thanks for that. Next up, we have Robert Miller, President of Jansen America.
Thank you. Hello, everyone. All right, 3 o'clock sleepies might be kicking in, so I'll do my best to keep this educational and entertaining at the same time. I attended a conference a few months ago. There was a panel discussion on sustainable architecture, and one of the architects made a comment I really liked. Basically, they said, and I'm paraphrasing here, we need to demystify a little bit what is the workload behind sustainable architecture. At the end of the day, what we're really trying to do is create beautiful buildings. That remains the same. We're just trying to add a few more things on the to-do list, right? We basically want those buildings to be constructed efficiently, to be well maintained, and sometime in the future when people have to make changes, they can make those changes easily and without disruption. I thought, okay, well, that's a very good perspective. So I'm gonna make that kind of the core of the presentation, but I'm gonna flip it around a little bit. I'm gonna talk about it from a historical buildings perspective. I'm gonna talk about it from new buildings, and then a little bit about certification. But before I go too far, I need to explain a little bit who we are, because that kind of influences our perspective. At the end of the day, we are steel frame guys. So we are a Swiss company. We make steel frames. We sell those into local manufacturers who then produce entire elements and then also install them on the buildings. We are a 100-year-old company. We started with steel tubes. After steel tubes, after World War II, we got into taking those tubes, bending them, and making them into profiles for architectural steel. We are 3rd generation privately owned. Sorry, I'm talking faster than the sliding is going. In 2021, we made a strategic decision to focus on architectural steel because over time, they essentially became 2 different business models. So since 2021, we are focused on architectural steel. That means we've doubled down on our product portfolio and also means we've gone more international, which is one reason why we're here in Canada with you today. Yeah. So now let's get the party started, shall we? This building, for those of you who enjoy music, you probably will recognize it. Imagine a big floating pink pig, and you've got the album from Pink Floyd, Animals, right? It was an iconic building in London, built or designed in the 1920s, built 1928 and commissioned in 1933. Then it was a major power plant for London for 50 years until it was decommissioned in 1983. Right? In 1983, it stayed there for several years as a little bit of an eyesore. Outside, it remained an iconic building. Everyone still recognized it. It was very commonplace to take photos. But inside, it was basically starting to fall apart. In 2012, new ownership group came in. New ownership group decided they wanted to make this a multi-use facility. And then one of the things they did was they contacted us regarding the steel windows. The steel windows were produced by a company in Manchester. We took a look at those, and we had a certain relationship with the architects, which allowed us to trial a little bit. We came up with several reiterations. What you see here was the original design, and we reiterated that design by basically putting in a thermal brake system. Right? Now, with the thermal brake system, then you have, in a way, what would be the traditional look from the 1920s. The integrity from what those engineers had wanted in the 1920s remained intact, but with modern performance. And not just for U values. Of course, U values are important, but you got to keep in mind that power plant's got the River Thames on one side, it has a highway on the other. So the fact that it was able to protect against sound and air permeability was also very important. Right? We took that, of course, it started out as a window based on that design, then we took that and evolved it into multiple styles that could be done, not just with windows, but also then with doors. We took it into multiple materials, steel, stainless steel, and Corten steel. Now, Corten steel, if you don't know it, is actually basically pre-oxidized steel, but it's kind of an interesting concept when you talk about historical renovations, because one of the questions comes down is, what are we actually replicating? Are we replicating the original look from the 1920s, or what people have come to associate that building with if it has rusted? So anyway, there's a little comment there on Corten steel, but I'm also proud to introduce our new member of the Arte family, which is brass bronze. We introduced it into Italy last month, and we're bringing it to North America at the beginning of next year. Beyond the materials, then you have different types of applications which it can be used. Also with historical buildings, could also be then for new buildings as well. What you have with steel is the ability to get a little funky, right? So you can do curves, you can do crazy shapes. You have a material that is basically strong. And with that strength, you have the ability to play, which is why for example, these pictures all have semicircles, they have shapes, they have curves, they have bends. All of it is kind of intended to bring back a little bit of that fun element along with steel. If we move right along now into new buildings, I wanted to highlight two main things. One thing is when you have a material like steel, you have something that is very, very strong, right? We've gotten to many people, not just here, just in general, all of us, you get into a certain template where we all start working with, where we feel comfortable with. Sometimes it takes a little bit of a paradigm shift to think, well, what can I do with other innovations, right? The materials I've been working with have become more innovative, but maybe there's also other options as well. So one of the things I'd like to kind of think about is design with steel in mind means expand your spans. Think about the fact that you can go large on some of those areas. Just like there's Moore's law with computer technology, where they say things can get smaller but twice as powerful, you can almost apply that to building materials as well. There's something called the factor of 3. It's not just something from our company, it's a general concept. And with the factor of 3, you have something that's 3 times stronger than aluminum, for example. But with that then, if you were to combine and make these spans with aluminum, it would require 3 times the same material. This has an impact on your embodied carbon and the amount of materials that are used, for example. So that's just one point, but the second point I'd like to make out is the connections. Think of Stephen Covey with his famous quote of begin with the end in mind. It's very similar for this too. Think about the people who are going to put this apart in the future. Right? If these connections are welded, for example, they're going to have a very tricky time. Use different types of anchors. There's multiple ways you can do it. We found, for example, that some of the connections used in Europe were designed to make it easier for installers, but then when you look at it, you realize, well, it's just as easy to install with this type of technology. It's not just our company. There's a lot of fascinating experts that are out there. Talk to the material manufacturer, talk to those experts, and think about the importance of connections when you're creating new designs. Now, building certifications. Dangerous topic because there's a lot of people in this room who are experts on that topic. Let's pretend there's a few people in there who also it's new. So let me take it down to some basics, if I could. One certification that's out there is called BREEAM. BREEAM is mostly found in Europe, used on international projects. It is, I would say, trending, especially if you have European eyes and considering we're a Swiss company, that happens quite a bit. WELL is another type of certification which focuses on the well-being of the inhabitants of the building. And this is kind of an interesting concept because if you think about how much technology we have put into buildings over the years, all of those IoT sensors, all of those smart building features, they're really, really nice. At the same time, there is something called building sickness, which can happen, where people unfortunately have health issues. We don't fully know why, but it is definitely somehow related to the combination of going too fast with technology and not fully knowing the side effects from that. So WELL kind of tries to find that middle ground, right? We want to have innovation in buildings, but how do we make certain that those innovations and the whole way that the building is put together reflects the physical and mental well-being of those people who were in those buildings? Then, of course, one of the big ones, the most popular in a way, is LEED certification. So I'm going to delve into LEED certification a little bit here. There are 4 different types, my apologies. Which type you use is completely a one-on-one discussion with the owner of the building. What are their priorities and what brings the best ROI for them based on what they want to accomplish. All of it is a point system with little check boxes of things behind each of those points. I'm going to focus just very briefly on an example of a building in Spain where we did a lot of consultation, but that also helped us cut our teeth a little bit on what it means then for LEED Platinum certification. Now you got to keep in mind, building materials are not certified. It is the building that's certified, but obviously building materials play an indirect influential role on that. And the role that we played in that building, but also in general from what we concluded, is that we influence roughly 56% of these categories. So LEED, as I mentioned, is a series of checkboxes. These are all the different categories you have in it. Within those categories, there's a little bit more information. You kind of package together your documentation, and then you hand it over for a certification body to look at it. So 56% will basically come from here. Materials and resources, obviously that makes sense, considering we're a material manufacturer, and that affects then the embodied carbon footprint. Indoor environmental quality, think back to what I mentioned about the Battersea project, the quality of noise, the quality of air, think about what I mentioned about WELL certification and the well-being of the people that are in that room. But then the biggest boy on there is energy and atmosphere. The reason energy and atmosphere is there is because that's talking about the operational capabilities of that building and how much energy they're going to be using. So let's dig a little bit deeper in that category. Coming back, before I dig a little bit deeper, how do we know, for example, that we influence those categories? And what is the information we can provide for you? So for these buildings, and what we did, for example, is that we took our product lines and said, okay, if this building were to use this product X, product Y, product Z, whatever, these are the amount of points you would be receiving in those LEED certifications. This is the impact and the value that we can bring to the table in our contribution. We took this through a third-party consulting company based in Germany, and we're also, by the way, now bringing this into the United States. That information, and now this is the area where I wanted to dig a little bit deeper, it comes down to kind of two argumentations. One argument is the fact that these things are very durable. We offer 75 years for windows and doors and 100 for facades. All right, this is the material version of it. Now, why in a way, that sounds so far in the future, can we really make those claims? Well, again, think about Battersea project, right? That was designed in the 1920s, built in 1928. The thing was actually still pretty good. When it came down to what those engineers had designed, the only difference is we used modern technology to make certain that they had a very good thermal brake system that was added in. But that's just one example to show that steel is a material that can last a very long time. We also confirmed that with a third-party certification. The other aspect, though, is recyclability of steel. So recycling steel, if you take, I don't know, a big chunk of steel, X, you recycle it, it remains X. It retains its strength, right? You could recycle it a third time, and it still retains roughly the value of X. You compare that to other materials, for example, and randomly pick aluminum, for example. A large item X in aluminum today will become a Pepsi or Coca-Cola can, and then from there it becomes a pen. So those things basically go slower and smaller, or slowly smaller in terms of what can be recycled. One more example here, when we compare it, not to knock on aluminum, but it's purely a benchmarking exercise. You can basically see what is the impact of steel compared to aluminum today, but also I'm proud to say we did our first green steel application profile. It's still uncertain exactly the future of green steel on that, but at least we proved that it's possible. Now, there's a lot more than just Jansen involved in the green steel industry to see exactly where that goes, but we do know that it's possible, and it does have an impact on carbon footprint. So let's do a quick summary. What can you get with something like steel? You're basically getting high thermal performance. You have less operational carbon. You get less noise. You get better light, leading to better wellness. You get something that's strong, which means less materials and less embodied carbon. You have something that lasts for a very long time, including for decades. You have low embodied carbon, and then also green steel is something that is up and coming in the future. You have recycling that retains its strength, and you have adaptive reuse. Saying that all very quickly to basically say, how can we prove this? There's two ways. An LCA is a calculation of the life cycle assessment for a certain project, very project specific. Can also be standardized roughly into what's called an EPD. We have 20 of these in Europe, but what we've done is we've taken our first 5 and we brought them to North America. All right. You have one more second for the screens to catch up with me. We also, that lead certification that I mentioned was through the third party in Germany. We're bringing our first 5 also to North America. So by the end of this year, we'll have the EPDs and the lead contribution reports available. In the meantime, all of this stuff is available on our website. If you go to this QR code, you register, it's all free. You access all of our technical documents, including our EPDs and our lead assessment information. Well, it sounds like my time is over. I hope I kept you awake, entertained, and educational, was what I tried to promise in the beginning. And then I will hand it over and get ready for the next one. Thank you very much, Toronto.
Thanks, Robert. Okay, next up. Seems like we're on a roll with steel, no pun intended. Eric, seriously, no pun intended. Eric Claeys, founding partner of Fassada Steel.
Good afternoon. Can I get my slides? If I have no slides, no problem for me. I'm going to try to entertain you a little bit. 15 minutes. about curtain walls and systems. What is this? I'm the founder of the group Fassada. Fassada is a group focused on the development, engineering, marketing of high-end curtain wall systems. Disruptive. We hear a lot innovation. Innovation is okay. Disruption is a must for two reasons. The existence of our company has two grounds. First of all, our colleagues, system houses, so we are a system house, they didn't do anything the past 50 years. They slept all over the world. The only thing they did is copying their books and even their stupidities. There's a second reason. Curtain wall contractors go faster bankrupt than they can start. All over the world. Even in your country. In US, in Europe, it's a catastrophe. By the way, I'm Belgian. I'm from Belgium. It may be interesting to know I'm a civil engineer in construction, I'm a civil engineer in building physics, and I have a master in business administration from the Verlerik Institute, and I'm a tax consultant. Why is that important? Because it all is about money. When you engineer, when you develop, it makes no sense when your threat is not money. You can develop all what you want, but it has to be sellable. It has to be competitive. So what we did, we had the two reasons why we had to start our company. And then we started in 2005 to develop a completely new philosophy. We did the risk analysis of the market, which you have in curtain walls, and there are hundreds. Hundreds. I'm going to name one. Silicon is for us prohibited. Silicon you use in a bathroom, not in a curtain wall. I have nothing against silicon, but silicon is not durable. I even not speak about the word sustainable. Durable means maintenance, and that's not okay. When I construct a building, it's for a longer term. So silicon, per definition, is out. I'm going to tell you in a couple of minutes why we don't use structure glazing. Because it's nuts. I'm going to explain this. But before I go further, I'm going to tell you my main concern in this building, in this business. You see on the color of my hair that I'm a little bit older. I got some years. 40 years on the track in that business and involved in more than 1,000 projects. What do I see? A huge lack of the basic fundamentals of this business. What's a curtain wall? A curtain wall is an envelope hanging on a primary structure, controlled by two sciences. Building statics and building physics. Building statics and building physics. You know, that's an apple. You know the law of Newton? You know the law of Newton? I have sometimes the impression that most of the people even don't know the law of Newton. And the law of Newton, besides, it's very simple. You hear this apple, and when I open my hand, I see a lot, I think a lot, that architects think that it's going to float. It falls down. I see it every day. Every day we see projects which don't make sense when they arrive. In the past, I've known buildings, they had a primary structure. Now they give you a lasagna. We call that lasagna. You stand the end, the thing is moving, and then you have to try to put a curtain wall on it. Makes no sense. Building physics. So, and from this I can give you thousands of examples. Building physics. As I said, what is a curtain wall? It's very simple. You have a box and you put an envelope around. And these building physics are key to create something we expect. I have sometimes in that people even don't know the greenhouse effect. I hear speaking about sustainable curtain walls. Nonsense. Impossible. Glass is per definition not sustainable. It is nonsense. I can prove it, I can calculate it. What is the greenhouse effect? The more glass you have, sunlight is coming in your room, it's trapped by sun, and it gives heat. Did you know, if you can avoid this, that your capacity of your heating and cooling system can be reduced by 50%? Sustainability. Emission of carbon. 20% is embedded, 80% is operation. About 20%. Everybody is speaking about these 20% because they don't look at these 80%. But that's not the key. These 20% is a debate in the margin. The 80% is the key, and therefore we have to focus. Our company, we focus on that, and we solved all of this. Maybe one comment about these statics. Here in your country and in the US, they applied norms which don't make any sense. Why they don't make any sense? Have you heard about the inter-story tests? You know this? Did you ever see moving a building like that up and down? Every building on the planet follows the rules of building statics, and they are universal. They are the same in Brussels, in New York, in South America. A building doesn't move like an elevator. Buildings move like this. Why this is not in your standards? The reason for that is simple. I've been part in lots of commissions, standard commissions in Europe, ISO, and these are controlled by the industry. The industry will never allow that a standard is accepted from which they know that they will fail. That's the reason why most of your buildings here leak. That's the reason. Because you do testing which are not representative for what's happening in reality. Keep it in mind. Keep it in mind. I go fast a bit over. So what we do, 800 patents for 74 countries. I go fast. For steel, I was not allowed to speak about aluminium, but to be clear, we have a huge portfolio of aluminium products for all different kinds of architecture. And for these products, I'm happy to announce to you that we made a collaboration for the Canadian and US market with the company State Window from Toronto. So from now on, if you want the real stuff, there's only one address. By the way, the people are sitting here in the audience. Steel is different than aluminium. Aluminium can extrude everywhere. Steel is a different story. It's extremely complex, and what you see there on our booth, I'm very simple, I'm straight, we are the only company in the world who can do this. It's so complex, and the investments are huge. To make this possible, we made a joint venture with the group Montage, a Swiss company based in Stabio, is the #1 in the world of very complex facades. This is what about disruption. I hear people say disruption and sustainable solutions, they are costing. This is nonsense. When you do it properly, they're even cost effective. And don't come to us with all kinds of idiot calculation of return on investment. This is nonsense. When you do it properly, a smart facade is even more cost effective than a conventional product developed 200 years ago. That's what we did. By the way, I'm happy to announce second thing. The term, the code hybrid technologies has been trademarked all over the world. So be careful when you use that word, hybrid. What did we do? Everybody knows this. A stick system has some advantages. Unitized. And the people, this dates from the 60s, beginning of the 70s. The guy who started developing this, Sir Mr. Fenzi, I know very well, he's 88 years old. Everybody is working with this unitized. Forget it. Forget it. As well for technical reasons as for all other aspects, and not at least for the cost economic. You have very high material cost, astronomical transport cost. I just spoke here to somebody in the audience. They make a turnover of 3 billion and they have 300 million transport costs. High and long pre-finance cost. To do unitized, you need big pockets and a very high storage cost. We solved this, everything. We solved also the problem of that it's very difficult to find labor. We start shortly constructing in US 2 factories, what we call dog factories. No people anymore, androids. They will run 24 hours a day, and we will start with a capacity of about 30 million square feet per year to serve you, all you together. Unitized, the issues we solved, so no silicon anymore, no structure, and we combined this, it took 14 years to develop, in a solution we call that hybrids. My colleague just said, steel has a lot of advantage, 10 times less CO2, steel green, I can use it forever. Okay, I go over this. That's what I just spoke about, sustainability. That embodied carbon is nice to have, but it's a complete debate in the margin, irrelevant. This you have to solve, this 80%. And we can do this. We can reduce it to 0 by a smart facade. See this? Where they don't have money, they do it this way. This is a building, I'm not going to tell you what, it's a BREEAM Gold building, certificate. It's a monster. It's a monster. And they can say they use green energy to cool it. Makes no sense. You have to avoid that it needs to be cooled. That makes sense. And that energy use it for something else. Or give it for free to the people. We have here galvanized steel, stainless steel systems. Very competitive, not to forget. Fabrication time, 1 minute per square foot. Instead of 1 hour, 50 times faster. That's what we call disruptive. Circularity. Another buzzword of these days. I say the best circularity is no circularity. It makes no sense. There's something invented because we're using crap of materials. I'm going to give you an example. A Porsche. Everybody knows a Porsche 911. The first came on the market in 1963. Any idea how many cars are still in use? 74%. Porsche has no problem with circularity because it's good. When you have a curtain wall, you have 2 parts. You have your grid and you have your glass. We have a team in our company specialized in developing new products for Claeys. A grid is good for at least 50 years. A grid is good for at least 50 years. But the glass isn't. And for sure not for the years to come. And in Europe, there's the ESG regulations. In 2035, buildings have to carbon-free, so all the glass has to get out. What does that mean? Unitized. Impossible. Cost a fortune. You have to take off or dismantle your building. And structure glazing, you can forget it completely. Again, it's all about money. We can do an upgrade for a fraction of the cost. We just replace the glass from inside like you do for a normal window. People say you have a short execution time in unitized. Again, nonsense. It is nonsense. You can work fast in installation, that's right, on condition you have your panels. But you need weeks or months of preparation to make your panels and to stock them, which is very costly, and that's what I call the pre-finance cost. This is not okay. People thinking that, but it is not correct. That's what we do. Trying to help people and then do everything in a smart way. And I think the whole business has to be reviewed from skills, so the real engineering and doing what has to be done. The whole fabrication process has to be reviewed. We do the fully robotized lines just for one reason. We have a consistent quality. What we make the Monday morning at 2 o'clock is the same as Sunday night at 9 o'clock. It has to be consistent because your final client, the developer, he has right on a good product. That's what we try to do. Thank you for your attention. And people who have questions, they can come to the booth over there. Thank you.
Okay. Thank you, Eric. Lots to think about there. Thank you.
Thank you.
I'm intrigued, for one. Okay, next up, we have Jelena Madzarevic from Elliston and Andrew Galdard from BDP.
Hi, everyone. This is the last presentation before coffee, so we'll make it short and sweet. So we're going to talk about the changing landscape with sustainability guidelines, municipal codes, and all of that, and the process of making decisions in that environment. Very briefly, I'm from the Construction Sciences Division. I manage the Building Science team, and we have a lot of aims in our group, but the most important one relevant to today's discussion is bridging this gap between engineering, consulting, and construction.
Thanks, Jelena. Hello, everybody. My name is Andrew Galdard. I'm a senior associate and design director at BDP Quadrangle. Today, I'll be speaking about carbon and how it impacts design decisions on building envelope and building form. And then my colleague, Jelena, is then going to speak about the specifics through case studies, examples, and realities of executing on site and the associated challenges. So why is this important? As you can see, future climate and weather are going to be quite different than today. Increased rainfall, increased temperature, frequent heat waves. I'm sure you all remember the summer of 2024. These events are only going to become more frequent. So let's quickly align our understanding of the sources of whole life carbon. Whole life carbon then comes from three sources: the operations of the building, the materials used to build it, and then the construction process itself. This leads us to 6 ways that we can think about reducing carbon in buildings. We can reduce the amount of energy of a building that is required to operate. We can reduce the amount of construction material used to build a building. We can reduce the number of activities taking place on the construction sites. Damn. Sorry. Apologies for this. Oh, can I go back with the slides? Yeah, sorry, I couldn't see all my notes. Thank you. Sorry about that, technical problem. And then the last 3 ways, we can decarbonize energy used to operate the building, we can decarbonize the manufacture of construction materials, and then we can decarbonize the activities on construction sites. The last 3 are all about electrification and cleaning up our electrical grid. So just to put this into the real-world context of ramping up standards and linking it to the efforts to get to net zero buildings, municipalities have set targets like the BC STEP Code. We can see Toronto's trajectory setting a pathway of increased building performance over a decade, resulting in net zero carbon-ready buildings by 2030. Surrounding municipalities are aligning with or exceed Toronto standards. We can see here that in the past year, Mississauga, Whitby, Ottawa, and Pickering will all have metrics in place that align with the net zero pathway. In parallel to this, embodied carbon targets are starting to be set. Vancouver has its targets, Toronto has set its targets in place for city-owned buildings, and it is projected to be introducing mandatory targets for all buildings by 2026. The whole life carbon footprint is a way to assess the operational and embodied carbon simultaneously. It runs from cradle to grave, that is from product material extraction to ultimate building demolition, or better still, deconstruction, giving us a good indication of the carbon impact of a building's lifetime. If we take the Toronto metrics and map them over a 60-year service life, we see that the whole life carbon of a building operating under today's requirements is still dominated by operational carbon. The band at the bottom represents the upfront embodied carbon. This value would increase due to maintenance, repair, and replacement. As we move into 2026 performance standards, we see the operational carbon target coming down, as well as the new embodied carbon target coming into play. By the time we get to 2030 targets, the embodied carbon target drops again, and we see the impact of operational and embodied carbon equalizing. As the performance improves, embodied carbon becomes even more important. So from our analysis of our own buildings at BDP Quadrangle, Part 3 buildings in particular, the structural system accounts for approximately 77% of the embodied carbon, and the envelope accounts for the rest. What is interesting to me about the building envelope is that it impacts both the embodied and operational carbon of the building. And there are a few tools available to allow us to make informed choices with an understanding of both impacts. Envelope is the primary tool to help reduce operational carbon. It is also a key component of the building design that as architects we have control over. The fact that the narrative is changing around how to think about it makes it essential that we understand the impacts of our design decisions and the interconnections between embodied and operational carbon. As architects, we're also prioritizing the envelope. We're focusing on points 1 to 6. These are VFAR, or form factor ratio. I know that's been mentioned previously. The window to wall ratio, the use of triple glazed windows, targeting a very high effective R value for the envelope, which is inclusive of windows, exterior insulation, and airtight detailing. And Jelena will speak more about airtightness in the coming slides. All these together help reduce the operational carbon of a building, and it will use less energy. I'm going to now focus on 2 of the points in a bit more detail. So the first one, focusing on building form, or VFAR, as we call it in our office, vertical to floor area ratio. The more surface area of a building, so think stepping terraces, the wedding cake form we see a lot of in Toronto, the stepping to minimize shadowing. The more exterior surface area, the more heat is lost. We are now having to pay attention to this ratio in the early stages of design. We have met with energy model firms, and they've indicated that the building form ratio can massively impact the building metric, specifically the TEDI metric, by approximately 20%. The formula shown here is something we put together internally, where we've multiplied the VFAR ratio by the assembly ECI, or embodied carbon intensity. And it highlights how building form and material choices interact to shape the envelope's carbon intensity. Notice how the embodied carbon intensity for the same assembly varies significantly with the changes in the form, underscoring the importance of simple, efficient designs. For complex forms, selecting low carbon materials becomes essential to offset higher embodied carbon and meet reduction targets. This example on the screen shows a precast concrete as the primary cladding material, which has a lower GWP, which is a global warming potential, when compared to the same forms when done in, say, a window wall system. So what we're doing here is to help our designers make informed choices in the early stages of design before a full embodied carbon analysis through LCA has begun. The second metric is the window to wall ratio. It's very important to the aesthetics, obviously, and creating a low one as a baseline in our designs. To create a good foundation, we aim for 40% window to wall ratio. This is important because of window perimeter detailing. And think of the jamb and sill details on a window in a tower that's 50 to 60 stories high. The cumulative total of that interface is kilometers long. That's why it's so important to pay attention to this number, the window to wall ratio, and then improving this detail through minimizing thermal bridging, improving the air tightness, and all this combined and thermally breaking balconies improves the building performance a lot. As a company, we are encouraging the use of setting a carbon budget, especially early on, for projects, and the envelope is a part of that budget. The Toronto Green Standard sets an embodied carbon intensity target of 350 kilograms CO2 equivalent per meter squared, with the building envelope contributing, as said before, about 23% of the total embodied carbon. So that sets the carbon budget at approximately 80.5. So we analyzed 44 projects in our office, and these are shown as bars on the graph, each with a different cladding type. And as you can see, only 31% of upfront carbon emissions align with this target. So we have a lot of work to do still to get under this target. I'm just going to hand over to Jelena for the next slide.
Thank you so much. And yeah, I just wanted to jump in. So those were buildings in their portfolio, and this graph summarizes a number of popular wall assembly options. And what we did was aggregate the global warming potential data and also the order of magnitude cost data and ranked it from high to low. And we found that if we consider that 80 kilograms per CO2 equivalent per meter squared target that Andrew outlined, that the list of options just narrows down, and that there's not a lot of good options out there or options that we're used to that fit into this agenda of optimizing and lowering embodied carbon for envelope materials. So a lot of work happening based on what's been talked about today, and a lot more work to be done to keep working on EPDs and improving them so that they can fit into these projects that pursue these embodied carbon targets.
Thanks, Jelena. So I'm just going to leave you with the two last slides that I'll be presenting. And it's a primer that we've called envelope guidelines. And it's to help to lower the carbon footprint of buildings. And these are as follows: set a carbon budget, simplify building forms, limit glazing, the 2 points I discussed in details, choose low carbon materials, precast performs well. You've heard how good steel is. Aluminum is bad. I think we've all been beating up on aluminum, but it is in everything. Avoid high carbon assemblies, optimize density, focus on material efficiency, and collaborate across disciplines, working with contractors and other consultants, and leverage building information modeling tools as a means to create input to put into your LCA models, for example. And these guidelines provide a clear strategy for optimizing form, materials, and design to reduce the embodied carbon. And they empower architects to create sustainable envelopes that align with carbon reduction goals that we see will be coming next year. And I'm going to hand it over to Jelena now. Thank you.
Thank you so much. So now we're going to dig into an application of this guideline at a small scale. And it's a case study of a tall building where we were optimizing for thermal performance, operational carbon, embodied carbon, constructability, cost, so many different factors that we all have to balance for a taller building. So we opted for fully unitized or prefabricated systems, unitized curtain wall, sandwich precast panel, and large format prefab wall. And then we kept the insulation at R25 just to make some comparisons and keep it level and get a better understanding of bang for buck, for lack of a better term. So the results of the carbon portion of the analysis were that sandwich precast came out on top in terms of thermal performance. And I think this crowd can expect that results considering how different sandwich precast performs thermally compared to the high frame factor in unitized curtain wall or large format systems. Then in terms of global warming potential, precast as well came out as having the lowest global warming potential or lowest embodied carbon. And this result seems a little surprising if you're not used to this type of material. It was definitely surprising me when I started learning about this, but it just comes down to how carbon in aluminum products is just a lot more present there just on how it's manufactured compared to sandwich precast panel concrete. It doesn't have as carbon intensive of a manufacturing process. So these values are interesting, but what I find to be a more useful metric is a normalized global warming potential, just dividing that GWP over the per R value impact. And again, of course, precast comes out on top where for every R value unit added, there's a smaller global warming potential relative to unitized curtain wall and large format panels. Then on the construction side of things, we looked at like a number of scenarios and a number of considerations with schedule, complexity, et cetera. And we assigned ratings, as you can see, with this star system. And to be completely fair to the unitized curtain wall, it actually presented a lot of benefits when it came to certain aspects of constructability, just because there was a familiarity and there was a certain simplicity when it came to on-site work, and a limited amount of field work that definitely helps improve things on site and also manage some risk with envelope interface and whatnot. Sandwich precast rated pretty well, but there were some challenges for this particular case study when it came to some of the site logistics. And then lastly, the large format had some of the lower scores, and I attribute that mostly to uncertainties with just how the system's handled and how it works all on site. And then cost-wise, sandwich precast ranked the lowest, where the large format ranked the highest. So if we put this all together, sandwich precast panel was the winner. It was a winner in 3 ways, so I call this a triple win scenario. Lowest embodied carbon, best thermal performance, and lowest cost, which is a big motivator in most project environments. So this story was a tall building, and we compared the carbon that was avoided by using precast relative to curtain wall, and the savings were around 100 million kilograms CO2 equivalent. But putting this into context, it's like taking 10 different downtown Toronto towers and reducing their carbon by 30%, which is a pretty substantial amount. And then on a project this size, the savings between sandwich precast and curtain wall were in the magnitude of 7 figures, which is very hard to ignore. So altogether, wins on all sides. Next, I want to talk about a lever that Andrew had mentioned, and that's this parameter of air tightness. So we know conceptually, better air tightness, it tends to improve energy model performance, lower operational carbon, and sometimes I'm starting to notice it gets thrown in as sort of like a cost-neutral add-on, do some testing, call it a day. But what I'd argue today is that pursuing better air tightness should be looked at with respect to the actual design of the building, what systems are being used, and overall cost impact. And that's not to alleviate myself of responsibility. It's 50-50 between design and a construction responsibility and being successful in these projects. So on the design side, a lot of the elements mirror what Andrew had mentioned from a thermal standpoint, an embodied carbon standpoint. The lower the VFAR, the simpler the building, the lower the risks with complicated interfaces and workmanship error on site. And it's those workmanship errors that tend to propagate to poor air tightness results. Now, should there be a need for articulation and cladding? Of course, that's encouraged. It should stay in the plane of the rain screen of the cladding and not cause articulation of the air barrier system where things can get complicated and introduce risk. Even at the scale of interfaces, there's also opportunities with where the glazing sits relative to the cladding to keep that simple. And then lastly, those systems, whether it's a door, a penetration detail, or your glazing system, all of those considerations have to be aware of this air tightness target and be weighed and compared accordingly. So I'll zoom into this interface one a bit more. So on your left side of the screen, we have a situation where the glazing is flat with the adjacent cladding, coplanar, and the thermal bridging is a lot worse. The overall insulation thickness of the wall was around 8 inches. So it was not an ideal scenario. And lastly, on the air tightness note, with the glazing being very proud and sticking out, the interface was all 3D and a lot more complicated to seal correctly. Then on the right side, we have a very different detail where the curtain wall is further interior. It's more optimally aligned with the insulation, and the interface ends up being a lot simpler. And then all together, since the thermal bridging was optimal, the overall wall insulation thickness was only 6 inches. So this is a scenario where, again, we have this concept of triple wins. We win on costs because we reduce the insulation thickness. We win on air tightness risk because we made the interface a lot simpler. And we win on carbon overall, both on embodied and operational. Then on the side of systems, I'll bring up again the sandwich precast building. It's going to need glazing, of course. So a cost-driven decision might be to do site glazed stick-built curtain wall. However, with site-built work, you introduce, again, that workmanship error. And a greater risk of workmanship error tends to turn into risk in achieving an air tightness target. On the other hand, if one selects a higher initial cost system like a factory assembled unitized curtain wall, you actually manage that risk by putting all the critical air barrier system component assembly in a plant controlled environment where there's a higher degree of QC, and you end up having better results when it comes to the actual field performance of the glazing system. So again, to remind that if an air tightness target is introduced, all the systems should be reviewed to see if they complement the air tightness goal. And now the other 50%, my side of things, the construction side, just as responsible for achieving these airtight buildings. So a couple of best practices we employ are the following. First, we start with, can we build this? Detailed constructability reviews, taking apart details, picking at every component of the air barrier system, and identifying it and clarifying how it's supposed to come together at repeated interfaces. Now, the next question from that is, who will build it? Coordinating shop drawings, getting people in the room, and making sure every component of that complicated air barrier detail is well understood and it's known who will actually complete it. And then we get to validating performance in the field. And I try and remind teams as much as I can that it's not just one test that you throw in at the end. It's a series of steps throughout the whole process. And it can start very early at a laboratory stage where systems are validated and optimized if need be. And then it starts with field review, just looking up, is there a hole in the air barrier? It's simple as that sometimes. And then building that up slowly with various commissioning activities and envelope tests that are more qualitative in nature, but tend to not only put attention to the air barrier continuity, it also scrutinizes quality and workmanship and really motivates crews to pay attention to every little detail that contributes to an air tightness goal. And all this goes smoothly, it rolls into a successful result once you do your whole building air leakage test at the very end. I find that it's late in the game to really do much about the air barrier once it's all covered up and the building needs to be handed over, so I try to emphasize these earlier steps as being just as important. So, altogether, I'll just recap some of the points from today. Being successful in these projects that prioritize total carbon, both operational and embodied, require a number of different considerations, such as budgeting, material selection, simplifying forms. And then lastly, I would emphasize this collaboration process where there needs to be a lot of crosstalk between different, not only disciplines, but also parties, of course, coming from the contractor side, also from suppliers and material manufacturers. There's lots of opportunity to provide input on early decisions and provide as accurate information as possible. And this helps projects working in these environments be a lot more successful. So that's it for us. Thanks, and enjoy the coffee break.
Well done.
I'm not gonna...
Thanks, Jelena. Andrew? Okay, so coffee break coming up. And if I can just remind the presenters from this last session to make your way to the stage for photos. And also a reminder for folks, probably worthwhile sticking around, not probably, for sure worthwhile sticking around to the end of the last session of the day. We have a great panel coming up, peeling back the curtain on the Forma Tower going up not too far from here. The Frank Gehry Forma Tower, I should say. Okay, thank you.
About a case study as well. Find the clicker. So the overview, new building energy compliance. Things are getting more stringent over time, as I said. Focusing on energy performance of the facade. It's a key variable when determining the amount of energy a building is going to use. We're going to touch on methods for estimating the quantity of thermal performance and quantifying thermal performance of new designs. And assuming the thermal performance of a new building meets relevant codes and standards, we're going to talk about how that compliance is eventually demonstrated. And then we're going to talk about a case study, 950 King Street West here in Toronto. So I work at Engineering Link. I'm in the building envelope department. I'm a building envelope engineer. We're over 60 staff, founded in 2009. Offices in Toronto and Calgary. I work a combination. I'm sort of a generalist, but I do quite a bit of new construction design, but restoration of existing buildings as well as recladding projects. And today's focus is a facade, building envelope, but we also have integrated structural engineering. So the new building energy compliance framework in Canada. It starts with the NECB, National Energy Building Code. Most provinces have adopted the code and reference it within their provincial building codes, or if they use a national building code. Quebec, BC, and Ontario are exceptions, but they have standards that work similarly. At the end of the day, if you have a new building and you're going to develop it, there's 3 pathways to demonstrate compliance with energy codes. You have the prescriptive path, the trade-off path, and the performance path. So with the prescriptive path, it's fairly antiquated at this point, but basically it's a list. They tell you exactly what you have to do. Thermal performance with regard to minimum amounts of insulation, glazing performance values, and just overall system values in general. With the trade-off path, you have a little bit more choice. There's the overall performance of the thermal performance of the facades mandated of the building. And then you have the choice. If you have a higher performance component, it could offset a component that might be a little bit lower performing. Finally, what we might be used to now is having to comply with the performance path or whole building modeling. In this performance pathway, you use an energy model to show the proposed building performs as well or better than a reference building that's defined in the code. So in Ontario, we're still using supplementary standard SB10, even though that we have a new building code here. So SB10 is fairly basic, and we'll show you why in a couple of seconds. But in Toronto, you also have to comply with the Toronto Green Standard. I'm sure everybody here knows about this, but it's going to apply to all buildings for which, or all new developments that you're going to get site plan approval for. And at the heart of it, Tier 1 at least is as good as the performance requirements in SB10. And then when you go through the tiers, as a couple of the colleagues here demonstrated today, you do quite a bit better than the minimum requirements in SB10, working up to zero carbon buildings and passive house standards. So if you're going to comply, what do you have to do? You have a new development, and this is what you'd be interested in as developers and architects. First, the team's going to select the compliance path, and if you're working with the Toronto Green Standard, it's going to be the performance path. You're going to have to do whole building energy modeling. Because down in the bottom here, where we're talking about Toronto building permitting, at the site plan approval stage, they're going to ask for a preliminary energy model. So when you're for the performance pathway, the energy model is really calculating the energy performance of the facade. But step 2 there, calculating the performance, you could also do it for the prescriptive path, or you could do it for the trade-off path, and all this is defined in the standards in the code. So when you're developing the energy model, you basically have to demonstrate that it meets the codes in the standard, and that's sort of the final step. So through design and eventually the building permit, the energy model's refined. It's eventually resubmitted with updated thermal performance, mechanical performance. And then finally, there's going to be an as-built model or modeling report that's submitted at the end of the project to make sure that you actually built what you were going to build. So just touching briefly on thermal performance of the facade, our R value, we've all heard of an R value, and we've all heard of a U value. R value is basically how much insulation do you have, or how much resistance to heat flow do you have through your facade. You could be talking on a material level, you could be talking on a system level, or you could be talking about the whole facade. U value is the inverse, and often we use U value when we're talking about glazing, but it's how much energy actually flows through the system. The overall effective thermal performance is what the energy modeler cares about. The overall thermal so at site planning approval stage, there's going to be a report, and it's going to say you're going to have an overall effective R value of whatever. It might be 10, it might be 20, it might be even more. So at that stage, that's sort of set in stone. as the design develops, you have to stick with that value. So you make, it's a bit of a preliminary value in the first instance, and then through design development, you have to refine the details and make sure that the thermal performance of the facade's actually gonna meet what you said it was gonna do at the site plan approval. So it's almost a line in the sand, doing this preliminary energy model. So the effective overall performance, it's not just gonna be how much insulation do you have. If you look at the figure on the right, there's a whole bunch of red lines and red circles. And basically these are areas where you have increased levels of thermal bridging. So you have increased framing, you have reduced amounts of insulation. There's building penetrations, there's interfaces between different building elements. These are gonna be areas where there's gonna be less insulation and more energy is gonna flow through those areas of the facade. Key envelope components then to look for: above grade walls, roof soffit assemblies, fenestration and doors, below grade walls and slabs. And a key here is gonna be how do all those come together, because that's where you're gonna have your thermal bridging. So I'm not an energy modeler, but I know what they need from me, and what they need from me as an envelope consultant is the R values are the U values, basically the thermal performance of different elements that's gonna make up our building. So they need accurate, effective U and R values for the building assembly if they're gonna have an accurate energy model. So they need somebody, or they'll do it themselves, but a thermal bridging assessment has to be made, and that's a calculation of effective U and R values for clear walls and for linear and point transmittances. So here in Toronto, how do we do this? There's two methods. One, you could use a catalog method, so they're pre-computed transmittance values from the building envelope thermal bridging guide. This was produced by BC Hydro and co-authored by Morrison Hirschfield a number of years ago. So it's literally a catalog, and you can see the figure on the top. It has cut sheets where for different typical assemblies for a building, it gives you all the thermal performance information that you need. Or you could do project-specific 2D and 3D modeling. And why would you do this? Well, I'll talk about it, but there were situations where for your particular building, your situation might not actually be in the guide. So what thermal bridges do we need to consider? And this has become more stringent over time. When SB 10 first came out around 2012, and then National Energy Code for Buildings 2015, basically when you were calculating the thermal performance of a wall, you weren't considering all the linear transmittances, or certainly not point transmittances. So you could see in the figure on the left, the slab edge and the shelf angle for the brick, it wasn't included. You didn't have to account for it. So clearly we're not being completely accurate at that point. And we tried to get a little bit better in NECB 2017 and NECB 2020. When you're doing your thermal modeling, the slab edge and the shelf angle are going to be included. So it's a linear transmittance, and that gets inputted into a calculation based on the typical R value for the wall. You take into account these linear thermal bridges and get closer to the real value. If you want to get even closer to the real value, energy modeling accuracy, what we call, if you really want to know the real answer of how much energy is going to flow through your design, you have to also take into account point transmittances. So you could see a number of brick ties there. They were never accounted for in the first two instances, but if you want to be accurate about it, you should be accounted for it. So again, key facade details that we're going to look at are all the interfaces: spandrels, slab edge interfaces, window perimeters, parapet terminations, roof-to-wall junctions, balcony and canopy penetrations. And again, they're either taken from the guide if they're there, or they're thermally modeled specifically for the project. And I should say, as time goes on and we get more stringent, I could imagine that thermal modeling is going to be required for most of your details. So we usually take a hybrid approach unless we have to be extremely accurate. We take details from the guide as applicable. And where project-specific modeling is essential is when the details fall outside the guide's coverage. So that's pretty simple. But if the project is too close to compliance thresholds and accuracy is needed, that's when you might do project-specific modeling. And also, if the design uses cutting-edge thermally broken assemblies or there are unique thermal bridges to consider, stuff that isn't covered by the guide, you're going to have to do thermal or project-specific thermal modeling. The figure on the right is a modular panel. It's based on the Flynn speed wall system. You can see it's a curtain wall chassis. It's a unitized curtain wall system, and it's got insulation, metal panels, and glazing all built into a panel that's built in the shop, brought to site, and installed, similar to a unitized curtain wall will be. So this type of thing you're not going to be able to get from a guide. You're going to have to work with the trade and understand the thermal performance of this system. You're going to be into thermal modeling 100%. The case study I'm going to talk about where a couple of these concepts apply is a redevelopment at 950 King Street West. It's the former Palace Arms Hotel. It was originally constructed in 1889, and you could see an older picture of the building. It's designated under Part 4 of the Ontario Heritage Act. So the facade has to be maintained during the redevelopment. It's, as part of the redevelopment, a residential tower is going to be integrated in behind the building. The ownership group, Greenwind Corporation, International Capital, Windsor Private Capital, the lead architect, Sweeney & Co., and the heritage architects, Giacomo, and Engineering Link is a building envelope consultant. So there's two distinct portions of the building when you're thinking about thermal performance, and the first portion that we'll talk about is the reconstructed heritage facade. So this building was sort of neglected over time, and the brick masonry was in terrible shape. It was deemed to be unsalvageable. But a lot of the masonry elements, the stone elements, and some of the other critical elements for the heritage portion or heritage fabric of the facade was the conical turret and some window elements. So these are salvaged, and they're going to be integrated with a new masonry system. We could see a conceptual sketch on the right where the salvaged stone units are going to be integrated with new modern brick and a concrete block backup wall. And then we're going to install spray foam insulation on the inside, which is actually fairly continuous. So the overall effective value of this portion of the facade is fairly close to the insulation value plus the brick. And that's because there's minimal thermal bridges until you get to slab edges, like we're showing the structural detail on the left, and other interfaces like the interface with the roof and transitions around windows, etc. The new residential tower, you could see a rendering on the right there where the new residential tower is set in behind the reconstructed heritage facade. It's going to be clad with a combination of window wall, curtain wall, and metal panels. And so when we came on, it was great that we came on during design development. The team got us involved early. The site planning approval, or the SPA model, had been already completed, and we knew that what overall R value we were targeting for the facade, or what we needed to chase. And we understood that the window wall system itself, specifically opaque areas at spandrel panels, wasn't going to work on its own, and we had to insulate behind it. So when we first started undertaking this to be efficient and not just burn time on it, we started with the catalog. The building envelope thermal bridging guide. Through that process, we understood that we were going to have to look at a couple specific elements of the building, and I'll talk about 3 of them here. 1 being the window wall spandrel bypass, 2 being column insulation, and 3 being the heritage wall and slab interface. So the window wall spandrel bypass, you can see on the figure on the left, it's a typical window wall system that's installed. It bears onto the slab. So at the slab, you can see that there's a reduced amount of insulation just because the slab protrudes a little bit out past the typical opaque wall insulation. So there's a linear transmittance there. That's an area where we have a little bit of extra thermal bridging. So we could take this a value from the building envelope thermal bridging guide, and it's going to be relatively accurate, but actually because we had extra insulation inboard of the spandrels, it's not going to be accurate in our case. And by doing thermal bridging assessment, the transmittance value is actually better than what the guide would have given us. So it was actually worth the time, cost, and effort to do the thermal bridging modeling in this case. Conversely, we figured out areas that we didn't have enough insulation, and it was going to be at columns was one of the areas. And the reason why is because just with the geometry of the structural frame and the way the window wall sat, in between the spandrel backpan and the concrete element, you only had about 50 millimeters or 65 millimeters of space there. So you couldn't get the amount of spray foam insulation in that we assumed at other areas of the opaque wall, nor is it practical to install the spray foam behind these elements. So we had areas of the buildings where all the columns are and where all the corners are, where the original assumptions of the SPA model didn't hold anymore. So we had to insulate behind these. We did some thermal modeling on it, and we understood that if we pack this with mineral wool insulation, we'll get by on the overall opaque wall value. So that's what we did. Oop, back. Oop, I still have the old one. So the other one was the heritage wall slab interface. So there's supposed to be another slide, but I must have deleted it or something. Sorry about that, but we could talk about it here. The good thing I put this structural detail in here. What it shows, the structural detail on the left, there's the masonry wall is self-supporting for gravity loads, but for lateral loads or wind loads, it needs to be connected to the slab. And there's a continuous steel angle, and there's a cast-in-place plates, and then they're welded together, and the connection's slotted to allow for movement. Well, this is clearly a thermal bridge. Everybody could see that. So we modeled it, and through modeling and working with the design team, we're actually able to iteratively work on this. It looks like a simple detail, but it's actually relatively complex. Are you going to put a thermal pad in there? Does this have an effect on the amount of steel you have? So now you need more steel. You're going to have more thermal bridging. So there's a balance between having a thermal pad in there and connecting the steel. And then perhaps we bring the spray foam around the cast-in-place plate to mitigate cold spots at that slab edge where the smoke seal is. There could be some extra thermal bridging there. So thermal modeling here was necessary to iteratively design with the team, optimize the connection, but also we could go back to the catalog. You wouldn't be able to use a catalog here. It just doesn't exist. So those are 3, wrap up, it's saying to me, okay, I'll comply. So those are three situations I want to go through quickly. And so the building's going to comply. And it's actually going to be a bit better than compliance because, we through experience, you could see where you can use a guide and where you're going to try to optimize things. Working with the team, we were able to get in early with the design development stage, use thermal modeling as a tool to optimize a bunch of the connections between different facade elements. What I would say is that energy performance requirements are becoming more stringent over time. What happens if you get it wrong? Well, you're going to have increased energy use. You might have cold spots, condensation spots, and you might have localized areas of discomfort. So you should try to get it right. You should try to accurately represent the facade at the site planning approval stage, all the way through demonstrating compliance. So that's it, right on time. Thanks very much.
Thanks, David. Okay, so moving right along, our next presenter, Jorn Teeple. Am I saying that right? Probably
Perfect.
not. Apologies. Okay, good. From Outokumpu Nirostra. Probably not saying that right either.
You're saying that right as well.
Thank you.
Yes, thanks for the introduction. It's a pleasure to be here today and talk a little bit about stainless steel as cladding material for facade applications. And for those of you who don't know Outokumpu, we are a Finnish company headquartered in Helsinki. And we are the biggest stainless steel producer in Europe. We have 3 major sites where we melt the material, and that is Tornio in the very north of Finland, Avesta in Sweden, and in Calvert, Alabama in the United States. And then there are further cold rolling mills, 2 in Germany and 1 additional one in Sweden, and then also in Mexico, in San Luis Potosí, there is another cold rolling mill. What makes Outokumpu special is we have our own chromium mine, which is located very close to Tornio, to the big mill in the north of Finland, in the city of Kemi. And that is actually the only chromium mine in the EU, I have to say. And our melting capacity here is 3 million tons per year, but in the end we produce around 2 million tons of stainless steel per year. And of course that doesn't all go into facade applications, unfortunately, but into all sorts of applications where stainless steel is used. So white good industry, automotive industry, oil and gas industry. So we produce a lot of different alloys, and a couple of them also go into the stainless steel, into the facade application. So my presentation today will be first about sustainable features of stainless steel, and then I will talk about a special facade finish, which is very often used for facade application. It's called the linen finish. And then as a last point, I will talk about the longevity of stainless steel and how you can actually exploit it. What do you need to do in order to have a really durable material on your facade? And when we talk about sustainability, in my opinion, most important sustainable feature of stainless steel is the fact that it's 100% recyclable. And now you might say, well, also plastic is recyclable, aluminum is recyclable. But the special thing about stainless steel and also carbon steel is when you melt it, it goes into all the different products, white good industry or transportation, kitchenware, trains. And then at the end of its lifetime, it goes back, it's going to be recycled. And the symbol of infinity here shows it is endlessly recyclable. So there's no limit, there's no loss in quality when you recycle it. You don't even need to have the same alloy that you melt. You can mix the alloys, you just need to make sure when you remelt it, you must have the correct chemical composition. And when that is fulfilled, there's no loss in quality, it can infinitely be recycled. And that is in today's circular economy, I think, a really, really important feature. And we have a recycled content, an average recycled content in 2024 of 95%. So 95% of the material was recycled. And I just talked about we have roughly 2 million tons of material we are producing. That means we use 2 million tons of recycled material. And the kind of funny fact is The biggest mill in the north of Finland is actually the biggest recycling company in Europe. So it's not just a stainless steel producer, it's also a recycling company. And now when we talk about the CO2 footprint of stainless steel, there's quite a difference depending on where the material is produced. If we go to mills in China and Indonesia, we have a carbon footprint of 8.8 tons of CO2 per ton of stainless steel. And if you globally take a look at the CO2 footprint, the industry mean globally is 7 tons. In Europe, the average is 2.8, and at Outokumpu we have 1.6. And that is not just taking the European mills into account. I was telling at the beginning, we also have our mill in Calvert. This is over all our mills, so it also includes the Calvert site. And then we have a special product, it's called Circle Green, where we actually can further reduce the CO2 footprint down to 0.5, but just the definition of Circle Green is carbon footprint smaller 1. It is possible, but that will then be more costly if we go down to the 0.5. And another, I think also interesting fact is when you order stainless steel, you will always get a certificate that comes with the coil. And that states the chemical composition, it states the mechanical values of the material you have ordered. And now there will always also be the carbon footprint pointed out directly on the certificate. Yeah, and in the next chapter, I would like to talk about this linen finish that I mentioned already in the beginning as facade finish. And what is this linen finish? So in order to understand it, I have put a photo of a linen fabric next to our linen finish. So it's a textured stainless steel. It's pattern rolled with these dots and little spaces between the circles or the ovals. And that is imitating this linen fabric. And also very typical for the linen are these lines which are running through the fabric. So it's a thicker thread which goes to the linen, which is very typical for the fabric. And that is also imitated in our linen on stainless steel, because you can see there are also these lines running through it. And that is quite a popular finish, which nowadays is used as facade cladding, not just now. I mean, even the Lloyd's building in London, which is quite an old building, it already has this linen finish on the stainless steel. And it is available in 3 versions. It is available with the lines, with the linen thread. It is available without, then it's called linen without slabs. And it's also available as vertical linen, where these slabs are rotated and running vertically. So that would be for applications where you want to emphasize on verticality. And so what is the effect of this texturing of the surface? So why do you actually do it? And in order to get an understanding what effect it has, you can take light bulbs and colored light bulbs and then shine it onto the surface, and then look how the light bulbs are reflected. And the light bulbs, they would be reflected here in the center, and you actually can see that the colors here are mixing. So instead of seeing clear light bulb in blue, red, and green, you see some white in the center. And you cannot really resolve those light bulbs anymore. So there's a very diffuse reflection, and also from not just the center, there will be light reflectance, but also from all around the sheet. So it seems that the whole sheet is lightened up. And now imagine how would a building look like if that would be the finish. And there's a nice example here in Manhattan, where the podium, the first 2 floors are cladded here with linen finished stainless steel. And you can nicely see how at the glass over the stainless steel, the opposite street, the building of the opposite street are reflected, and you also can see it below, but in the stainless steel, it is diffused now, reflected, the colors are mixing, and you get this quite color-consistent, homogeneous, let's say, silky-looking, metallic look on the stainless steel. And that is exactly what the texturing does. So that is the effect. And in that case, the architect was Jakob Fried of this building, who uses stainless steel quite frequently, also always with linen finish. And Permas-Leser was the facade company in this case. And another example where also Permas-Leser was the facade company was a project in San Jose, 200 Park Avenue. And in this case, not the linen with the slabs was used, but the linen without, so this clean linen. And the architect here is Gensler, facade company is, as I said, Permas-Leser. And Richard Orser, who will be in the panel afterwards, was the project manager for this project. So, so when you look at the building, I think he must have done a good job. I mean, everybody has done a good job, because I think it looks quite amazing, especially here. So the color consistency is really high. And also, if you look at the fabrication, so the flatness is really, it's flawless. And the fabricational skills here are more or less, one can maybe say, even on a next level compared to earlier projects. So yeah, it's a very nice project. Another project which has recently been completed is 40 Leadenhall in London, and architect here is Make Architects, facade company is Foki. And also for that project, the linen without slabs was used, 460 tons and grade 316L. And I will just flip through. So here in the evening sun, you can see the stainless steel changes its color and looks gets a golden tone. Also here, you can see again this silky looking appearance on the stainless steel. Also here, the fabrication was quite amazing. Cantori was the metal fabricator in that case, also an Italian company. And so this is stainless steel in cases, and cases where the linen finish was used. And in total, since 1986, 67 buildings have used this linen finish. And some are also quite remarkable, like Ping An Tower in Shenzhen or the Petronas Towers in Kuala Lumpur. There are typical architects who tend to specify it more often than others. And then the last chapter, the ensuring the longevity by selecting appropriate stainless steel grades. So the question is now, what makes stainless steel durable? Why is it durable? And of course, the reason is because it is corrosion resistant. But why is it corrosion resistant? And what is the secret of stainless steel? And the secret is actually the chromium content in the stainless steel. So chromium is what makes stainless steel corrosion resistant, because it is oxidizing, the chromium on the surface is oxidizing with the oxygen, building chromium oxide, and that is functioning as a passive layer. And that chromium oxide layer is protecting the iron atoms to react with the oxygen and form iron oxide, which is nothing else than rust. So it's a protective layer. And what can be really harmful to stainless steel is chlorine ions. And chlorine is contained in salt. So sodium chloride, that's usually, so salt is what can be very harmful to stainless steel. That's why you need to make sure when you build something close to the ocean, use higher alloy grades, or if there's de-icing salt in cities, that can also be quite harmful. So that means in those locations, or if there is de-icing salt, the chromium content in the alloy needs to be higher in order to have a more stable passive layer, so that also then the stainless steel is protected. And this passive layer, the chromium passive layer, leads to the corrosion resistance, and that's in the end the durability, because you do not need any extra painting that makes sure that the material is corrosion resistant. And when there's no painting, you don't need any repainting. That means when it comes to maintenance, stainless steel just needs cleaning and nothing else. So you need to make sure you clean it, but no repainting after 20 years, 15 years whatsoever. And of course, in order to have the corrosion resistance, you need to select a grade which is suitable for the location. And in order to make this selection, there are of course standards, and the ISO 9223, they categorize these various corrosivity classes, and depending on the location, so for example Toronto here, Toronto is a C3 location with a little hint towards 3.5, and that means you have a selection of grades available. So typically one would use a 316L here in Toronto, but then there are other locations which are more extreme. For example, Dubai, close to the sea, would be a CX climate. And then 316L does under no circumstances work here. But how do you find out what kind of corrosivity class the location has? And in order to find that out, so-called corrosion field tests are performed. And then you have a rack, you place different alloys on the rack, you leave it there for 1 year, for 2 years, and then you examine the surface and you see, is there corrosion on that grade or is there no corrosion on that grade? Of course, the surface finish has an influence, and we did a corrosivity field test including the deco linen, and I want to show you now the results that we have in these locations. Berlin in Germany next to the motorway. Songkhla, Thailand, this is an industrial area close to the sea, so it's kind of a brutal environment. Genoa, Italy, very close to the sea, and also Bangkok. The reason was there were no real data available for material in subtropic environments, so that's why we were kind of curious, how did those locations in Thailand here perform? And that is the result. So Bangkok was very mild, it's a C2 climate. Berlin next to the motorway, C3, that was kind of expected. Genoa, because of the proximity to the sea, is 3.5 climate, also expected. Songkhla, CX, was very unexpected. So that is, again, we don't really understand it. It probably has to do with the industry which was next to the site. And probably they have a lot of sulfur dioxide or something that they pollute, and that probably makes it quite a severe climate here. But anyhow, that's how you in the end find out what is the corrosivity class, and according to the corrosivity class, you then select the stainless steel alloy. Yeah, and if you have selected the appropriate grade, you will exploit all these beautiful features of stainless steel. The non-combustibility, of course, always comes with stainless steel. The longevity, the low maintenance, impact resistance, and strength because of the good mechanical properties. Yeah, and there are, if you look at the highest building in the world, there are quite many who use actually stainless steel as facade material because they exploit this durability character of the material. And yes, I'm at the end of the presentation, and I hope I was able to show that stainless steel is a sustainable material, at the same time aesthetic, and also durable material. And if you need further information, details on stainless steel, we have a facade design guide downloadable. Yeah, if you want to know how linen finish looks, we have a booth, and we have small samples where you can actually have a real look at it. And Again, thanks very much for your attention.
Thank you, Jorn. And an excellent reminder for all of us here that next time we find ourselves designing a building in Thailand, let's be extra careful about our stainless steel alloy spec. So I think we're assembling chairs on the stage again. And I actually have a note to pass on from the fine folks at Zak. So just a reminder that there will be a magician in the expo space after this panel, in case any of you feel like delaying your own disappearing tricks. And another note, just to remind everyone to take this final opportunity after this panel to ask the exhibitors any lingering last questions you have. I'll also pre-introduce this panel's members while we're finalizing the seating configuration. So the moderator will be Camilla Bannister, Development Manager at Great Gulf, and the panelists consist of Abel Gill, Associated Adamson Associates, Dan Francis, Facade Designer at RJC Engineers, and Richard Orser, Project Manager at Primastila. All good?
All good, great.
Fantastic. All right. And without further ado, our final panel for the day.
We're good. We'll be fine. So good evening, ladies and gents. My name's Camilla Bannister. I'm with Great Gulf, Development Manager for Forma East Tower, West Tower for the past 2 years. We are here today to talk about Forma, and on the stage with me are the lovely gentlemen from Dan Francis from RJC, Facade Designer, Abel Gill from Associate Architect, specializing in building envelopes from Addison Associates, and Richard Orser from Primastila, Senior Project Manager for North America. I'm excited to be on this panel with these gentlemen. I've got to know them over the past 2 years working on this project. I've traveled with some of them as well. And this panel is mainly about bringing a legacy project to life in the Toronto market and a vision of an award-winning architect and the collaboration it takes between ownership, fabricators, designers, engineers to bring something to life. The four of us are just a small subsect of a small army that it's taking to get this project off the ground. So Great Gulf, Dream, and Westdale are bringing this project to life. Of course, Frank Gehry and his team in LA are working on this project, Adamson, RJC, and Primastila. So Forma is in the entertainment district of Toronto, where Frank himself grew up, delivering newspapers in an area known as the entertainment district, formerly marked by railway lines and warehouses, and now a bustling area of the city. Forma, when it's complete, will be flanked by the Mirvish Theatres, Princess of Wales, and Royal Alex Theatre, and Roy Thompson Hall. And the East Tower will include an OCAD campus for arts and visual design as well. So just in context, the East Tower with OCAD is under construction right now. We're on the 19th floor. West Tower to come at a date to be announced. We'll also be incorporating a heritage facade on the West Tower. And the entire concept of Frank's vision was to bring whimsy and design that stands out to the Toronto marketplace and reflect light through the stainless steel facade. So the design started as an idea in late 2000s. Then a sketch progressed to handmade scale models and handmade mock-ups to the finish to the Italian rules of curvature and execution of the facade that you see going in today. So I'm going to go to the design vision and ask Abel to say his thoughts on the Gehry process and walking us through how we got to where we are today.
So the design process at Gehry's office always starts with a sketch. I think that's coming up here. These are just some views of the facade. Oh, here we go. Okay, so it always starts with a sketch, and this is a two-tower scheme. And they always think of the space in between as the third figure. So as you're moving around through the city, it is very distinct two-tower composition, but at some points it visually forms one. But modeling in the physical model is inherent to the way they work, and they just iteration after iteration of models. And you can see here that as it's basically formed in 3 stacks, and it kind of steps back and twists in relation to the adjacent building. So the form of the tower itself is shifting and rotating depending on the height of the building. In the original sketch, it's a very fluid building, but you're looking for efficiencies when you're building these towers. So it's coming with a more standard floor plate, and the undulation happens in the facade. But with Gary, from the models, then they scale up, and when they finally figure out something that they like or a design direction, then they start building bigger models. This is a paper model that they fashioned at Gary's office. This is in their parking lot there. And it's to validate the idea of this articulating facade. And it's basically, the vertical panels, there's sort of one tilting out, one's sloping back, and then the horizontal panels, it's going left or right, and then they introduce texture to it. But, when they're looking at this, and then it, goes into 3D modeling, then they realized at some point it didn't have the kind of movement that they wanted, so they started introducing a micro-texture, which is sort of gets into a finer scale from the big move that's happening. So this is the paper model that they did. It's quite large. It's amazing that they make this down there. And then so from that they did a full-scale panel as the paper mock-up, and then they wanted to validate their ideas. So you'll see in the next couple of slides, this is Gary's office back here, and they're locating the panel, in the parking lot, and then there's viewing it from moving back to validate the ideas. So this was the panel. This is made out of paper, and you can see there was Frank. So here we're at like about 10, and then we're backing up, and then we're like down the street, just to visually, before moving forward with the design, just to ensure that this is following the design intent. This is the kind of process that they went through. And then at some point, we built a visual mock-up here in Toronto.
In an undisclosed location, but if you drive on the Gardner, you can see it.
And the visual mock-up, and Richie can talk to that later about the process of how we did the panels and how you get there. But the important thing about, I think, was validating the kind of the moves and the materials. And it's very interesting to see that the panel beforehand with the linen finish. Sorry, it was the previous.
Sorry, I was like.
But the tower, as it's twisting in the city, and then because panels are like tilted down and up, and it's how the material changes depending on time of day.
I think maybe for clarity, we are also a linen finish, correct?
We do have the linen finish.
Yeah. And then this is just what we have seen today. This went up during the TIFF process. And I think one of the things we talked about last night was, Rich, what did doing a VMU through this process allow you to not know that you could achieve? Can you not do a certain angle? Can you not do a certain depth?
Sure, yep. The early involvement is definitely helpful with the design team, and working through visual mock-up, validating materiality, aesthetic intent through the design process, as well as the finishes that are ultimately going to drive what everyone sees from the macro view within the micro textures. So testing out a little bit of our procurement, supply chain, as well as manufacturing process to validate some of those initial steps.
I'm Rich. To Camilla's point there, when you were doing your sort of trial with the tooling and the dies in the manufacturing process, was there anything from conceptual design that couldn't be achieved?
We definitely worked very hard with our fabrication process to make sure that we were reproducing through the 3D modeling process something that was manufacturable at scale, so not going into a computer model with the intent of something that could not be manufactured at volume for the project with high repeatability.
So the design team was assembled quite a while ago when Great Gulf Westdale and Dream took on this project in 2017. Gary, obviously, first on the scene, Adamson, RJC, and Permis Lisa came about very quickly to engineer this facade. And so I'm going to ask you each, maybe we'll start with you, Dan, like what you think the importance of getting the design team on board early through the process helped RJC in your case.
I think speaking sort of selfishly from a facade consultant's perspective, we always want to be engaged as early on as possible, right? And to the wider project, it certainly introduces a lot of efficiencies. We wrote a lot of the building envelope associated specs from below grade waterproofing right up to the roof, and then the curtain wall and podium precast somewhere in between. So that removes a lot of the development in the DD phase, and there's also, you know, some finicky details that we're not sure about, and we can sort of work on those before it gets to a shop drawing review, and it has to be dealt with that way. So we get efficiencies there too, and then you know your typical sort of validation through thermal analysis and that sort of stuff as well. And as well, I mean, Richard's team were engaged earlier than usual, right, which gave them a head start to hit the ground running with their design. I mean, it's the scale of this building. There was a hell of a lot of drawings that went into it, so it was nice to have that head start with it all.
And then Abel, maybe I'll say Rich first, and then Abel will go to you at the end. So Rich first.
Sure, compounding on Dan's comments there, the early engagement through design assist has definitely become slightly more common with complex facades over the years, and working with the project team, muddling through the spec sections, sending back 10 pages of, hey, here's what we should talk about, what might go differently, the way we would see it was definitely helpful from a technical perspective in maintaining a high performance facade, despite the undulating and very textural metal on the outside. Additionally, we see it as a very valuable step in the overall process, interfacing with the design team directly to make sure that we're exploring and properly explaining our proposed manufacturing techniques to build an understanding of basically the output and tailoring it back into the input so that they understand how material flows through a plant, how the 3D vision will be achieved at a manufacturing scale. So getting some of our technical and technical inputs back into those design drawings.
Abe?
I think it's been great, you know, working with Dan and RJC, and then having Permis Lisa on early in the process was really, really helpful, because, you know, when you go from the paper models, even at the large scale, and then, you know, Gary has their own proprietary software, and, you know, they model everything in there, and you can see visually how they can get it to be what they want it to be, but then bringing on Permis Lisa early on, then we figure out, okay, how can we fabricate these panels? You know, they're quite bespoke, but, you know, we need to find efficiencies within this. And then, you know, through working with Permis Lisa and the rest of the team, you know, we came up with the Italian rules of curvature, which Richie can tell us more about.
And then Abe, do you want to touch on, this is like a snippet from the proprietary Gary software, and how it helps dictate we'll go into the Italian rules of curvature in a second. Anything to add, or we're good?
No, the software, it's amazing because it allows you, there's such flexibility within that software and to rationalize the panels in their own way. But at a certain point, then we need to go that step further with Perma Stelisa to figure out how we're going to make it, right?
Yep, absolutely. So the input to us of the surface drivers, again, coming from the initial hand sketch through physical modeling, paper models, and then handing it over to us to show, hey, here's the micro movements, the radii, how many shapes or moves per panel you'd be interested in, to achieve that kind of at scale macro sense. We were able to extract a manufacturing process that was both efficient in our facility over in Italy, as well as achieving the overall architectural intent for the shaped metal panels. So utilizing the skill set that we possess, the machinery that we would propose for the job, and then ultimately basically trial and error out, okay, we could do a radius of this size at this width, or we can do it with a machine, or we should do it by hand, and then testing out basically the breadth of the radii that they were interested in to make sure that it was something that was highly repeatable, but also visually appealing at the overall facade level.
Do you want me to just click through?
Oh, or I can keep going on these too. Yeah, so again, another beautiful part of the Gary software is just how much data can be extracted from it. So as we're providing inputs back to the design team, they're going back and manipulating the model to make sure that they don't have too many moves in a panel, for example, that would create inefficiencies or a lot of handwork in the factory. They would come back with a new model, a new data set, all spread out in a beautiful 3D model, and we would spend hours toiling over this problematic panel and that problematic panel. There's too many fasteners here, not enough fasteners over there, and really developing truly as a team how we got from something that was a sketch to some of these large-scale panels that you're seeing on the screen right now and on the facade. I'd be remiss if I didn't note that our skilled team over in Italy is hand bending each and every one of these panels according to the 3D model. So again, linking up with the design as early as possible allows us to tailor the output to be something that we can track through the entire process, ensure that it maintains the quality required, and that it's something that we can do over and over and over again across the entire facade.
I think what's interesting to note is, the panels are being, we're hand making these panels, right?
Yep.
But the profile ribs inside, that's all based off the 3D model, which is all CNC cut. And then there's a certain tolerance to get that panel. And, there was definitely a lot of whoa, to get it right.
Yep.
And I got to see this in Italy as well. This was just really cool because this was the first opportunity, I think this was last summer, that you got to see the light reflect in the sky, and a sunset in the Dolomites was very nice. And so I think as people follow the project in the city, you'll see more facade going in this fall. You'll start to see that reflectivity and the culmination of a lot of hard work of a lot of people. So we've touched on the VMU originally. We also did a PMU, and I asked Dan and Rich to talk more about the performance mock-up and lessons learned. You don't find it done that often in the typical facades that you have in Toronto, but with something like this legacy asset, a VMU was required, a PMU was required, and again, these are just another couple shots of the VMU and our Windows system, and then we can go to the PMU procedure. So Dan?
Well, I think for any project to this scale, it's essential to do a PMU, even if it was a more off-the-shelf system. This was a custom system by P&A, so we really needed to, we had quite a stringent spec for air performance. I think we were working to 0.1 liters per second for air, right, which is tight. So, you know, we needed to validate that before anything got manufactured or hung on the project. And largely it was a great success, which in my experience is quite uncommon. You know, we did have a couple of little issues naturally. So I mean, this is in reverse. This is the building maintenance unit roller impact. So these rollers are attached to the swing stage to protect the facade from getting damaged under maintenance. We did do this after the official PMU. We didn't want to rip it to pieces by throwing these weights at it too early. So, but this was a really valuable exercise. The panel design was finalized well before we had an access designer on the job. So we did a little bit of trial and error with this and found out at what point we would get deformation in the panels. And then that really helped the access designer come up with something that wasn't going to damage them under the service loads maintenance. So, you know, they played around with the material of the rollers, the frequency of the rollers, which will distribute the load. And then also the ISA tiebacks as well. These, the vision glazing is unusually recessed. And the tieback anchors actually sit in the proprietary curtain wall mullions, right? So your cable is in the zone of that recess. And what we found when we did the downward force is that it was bearing on the top lip of these panels and causing a lot of damage to them. So doing that, you know, before there was an access design completed, it gave them the opportunity, again, to make sure that there was the required amount of adjustment in the cables and making sure we had a sufficient amount of padding on it in the zone that it's going to touch the top of these panels.
I have a quick question, which I should probably know the answer to. What's the depth of the sill? Does anyone know that?
Anywhere, I think it's 225, 450. You got a number?
18 inches. It maxes out slightly over that, but ultimately the facade depth is around 2 feet to 28 inches, depending on the mullion set behind it.
So just when I started on this project, I was like, how does one clean this? So we'll see in a few years. And then Dan and Rich, I'll let you guys go through the PMU testing.
Yeah, these are just, this is the wind-driven rain test setup. You know, we repeated these tests a number of times, you know, before structural, after structural, before thermal, after thermal. It was quite a rigorous procedure, but it, you know, like I said before, for a project of this scale, I think that's super important to make sure that we're all absolutely sure it's going to perform as intended before we proceed into heavy manufacture. I think one thing that was super valuable, although I said before it was a great success, particularly in comparison to other jobs. You know, I've had projects in the past where we've reconvened 6-7 times for a PMU, right, and struggling to get it to work. This was very smooth, and kudos to P&A for their diligence in the design to make that happen. Again, introduced a lot of efficiencies into this stage, but we did have, part of the procedure was to reglaze a unit. So we're replicating, there's always going to be a few IGUs that get broken on site. So when we do the reglaze, we want to replicate a site reglaze opposed to doing it in controlled plant conditions and ensure that it's going to perform following that site reglaze. And we did have a small issue with that, but in my opinion, it was a good thing because it gave Permis to Lisa the opportunity to go back, look at their reglazing strategy, figure out what went wrong, and then we know from the outset that when that's done on site, it's going to work as long as it's been done per that revised strategy. So.
Anything to add, Rich?
Yeah, certainly a unique one with the depth of the panels that I just mentioned there, making sure that the exterior reglaze has access to shoot the structural silicone around the perimeter. So special consideration, and to Dan's point there, always valuable to test out on a performance mock-up with the performance criteria as stringent as it is, working together as a team through each of those test steps to achieve a successful PMU.
Yeah, and like that, reglazing that unit was definitely not the typical reglazing,
exactly.
just because of the recess of the panel and access to
It was
reapply the
tricky for
silicone.
them. I was one of the last ones that sort of hung around for this part on the day, and you know they're trying not to get the corner of the IGU on the metal panels. It was tricky to say the least. But again, you know, it just really highlights how valuable this is to do it at this stage and know exactly how it is going to be done on site, and walk away from that knowing that when they are reglazed on site, we're not going to get any issues.
So I think I mentioned earlier, we've traveled, the ownership team is committed at this point to making sure we execute this project well. I think all of our reputations stand a bit of damage if we don't. And we trust the partners well, and we really wanted to empower the consultant team to be able to go and see the facilities. So RJC and Adamson are there a lot. Rich gets to go to his facilities all the time, so it's just a treat for the rest of us. For me, it was just seeing it all come into play. Primacesa in Veneto also has like what I'm calling a museum of all of their greatest projects. It was a great sense of pride to see that Forma made it up into that room, as long as a couple others throughout the world that they've worked on. But I'm going to ask the gents to give me each a hot take of what they appreciate through the plant reviews, either from a engineering, architectural perspective, or something more fun. And I'll start with Abe.
I thought it's always beneficial to go to the factory to see the panels being fabricated. One, you want to see the capacity of the factory. You want to see the QA/QC process. You just want to ensure that everything's being, you know, the gaskets are cut, you know, precisely, nicely. But interestingly enough, speaking to Carlo, the deputy manager of Permastolisa, he said an interesting thing at dinner the other day. And, you know, he said, you know, the factories are, you know, it's whatever, you know, like you can load up your factories with like super expensive automated lines, you know, and there's a lot of like CNC happening at Permastolisa, but, you know, his take on it was that and you could see it, you know, from seeing the people working on the line. You could see that there was pride in the work that they were doing. The workmanship was excellent. And so what Carlos was saying was that the factory is the factory, but the real important thing is the people. And definitely I could see that, you know. I know it sounds kind of corny, but it was good. You know, yeah.
Dan, how about you?
We'll typically always do plant reviews, and to be honest, we were always quite impressed with the sophistication of P&A's facilities and their QA/QC procedures. But you know, I think particularly getting in there early on, right? There's always going to be a couple of little improvements that can be made that'll get, you know, translated into a report, and that'll be actioned, and largely everything was. And that getting in there early on really sort of sets a precedent for the rest of the project, you know. So then we're going for the repeat visits, and everything is pretty much perfect. But also, you know, verifying that there's quite a few different curtain wall types on the job, and verifying that, you know, the correct components have been used and it's per the approved design, super important. And I know P&A are very good at doing their own internal QA/QC procedures, but we're also there to verify that that's being done correctly and per project specifications. And then, you know, even down to an invoicing and billing standpoint, right? You know, we're verifying that we're there at the stage that that they say they are, and we can sort of give peace of mind to our client on that basis as well.
And Rich?
Permasalisa is always very excited to welcome our clients to the factory, especially at the onset of manufacturing and prescribed times when we're switching wall types or other events of that nature. In my opinion, it's definitely the penultimate event on a project. The design team, the project team as a whole, has worked tirelessly for years to bring the project to this point, from initial concept through mocking up both visual and performance. This is the first chance with project materials that will finally exist on the building to be manufactured. So it's always a very exciting moment to demonstrate the workmanship and the pride in workmanship that goes into each and every one of them, as well as, to Dan's point, the quality controls, the controls in general, both from incoming materials, the manufacturing, both CNC, hand fab, and internal machining processes that take place before anything even hits the assembly line to come together as a curtain wall panel.
And just to sort of add to that, I mean, it's quite unusual to see a group of people that are so passionate about the quality of the work, right? And that made our job a hell of a lot easier, and I'm sure Richard's job too. But, you know, the team down there really care about what they're putting together and the quality of the work. So that was a great success.
Okay, so we're rounding into the last couple minutes, and then if anyone does have questions, we'll try and get to one or two. My favorite topic in all of this is number of panels and how the crap do you track all of these things, because they're going from many places in Europe to Italy to Canada. I don't know, does it go down Gardner? Like, to get to site? So quick facts, and I'm going to hand it off to Rich to tell us more about tracking and traceability, and hopefully you'll talk about the RFID technology.
Thanks for the prompt on that one. So overall, we've got about 7,500 panels on the project. Obviously, making sure that they're all built to the wireframe that came from the design team, and that surface matches the design surface is the ultimate goal in the project. So the tracking through our internal systems from the onset of ordering materials to the output of a finished crate exiting our facility and heading down to the job site. We have controls in place that obviously monitor every individual, and there's thousands, many thousands of components that go into some of these panels. I will say one of the interesting parts of the overall system is to adhere to that high-performing curtain wall spec. We did create a high-performing curtain wall system behind and maintain all of the movement inside basically a stainless steel rain screen panel on the exterior. So we harnessed all of that complexity on something that's highly controllable while maintaining a highly repeatable system behind that. Within our glazing processes, we do track all silicone batches, numbers, primer application dates, testings that are required for warranty and performance requirements. And one of the most common ways we do that is through use of an RFID chip in glazed panel assemblies, so that we have all of that data that I just rambled off there readily accessible within our systems for harness or accessing at a later date.
Next one, or?
Here we go. All right. So looking at the overall building as a series of individual modules that have to come together in a very specific manner at each step throughout the process, we start with a work breakdown structure at the early design phase, basically categorizing the wireframe into small building blocks, subsets of our panels that make sense from a manufacturing standpoint to assemble together due to similar features, for example, inside corners, outside corners, flat glass, stainless steel of various typologies. So we take that view at a macro level and drill down into the micro of how is the factory going to build this on a weekly basis for years at a time in a sustainable manner. Next, in the middle, we see how that design basically morphs into our design development and fabrication modeling up the tower. In those middle two shots, you can see a snippet of a moment in time for our design release. Basically, we've modeled every curtain wall component and released all the procurement, purchase orders, requisitions, et cetera, to make sure that the material will arrive on the assembly line at the right time as it was designed to come together. And then lastly on the right, obviously the ultimate event, which we're beginning to experience here on site, is the installation of the curtain wall. So looking at our installation crew and how we break all of those panels down into deliveries to the job site. So they start, as Camila said, all around the world into our facility. They need to exit in a module that can sometimes be intermodally transported from Italy to the final site here in Toronto. So sea containers, box trucks, flatbed trucks, the man and material hoist on the job site, or tower crane rigging all have to be taken into account to make sure that the process comes together and the ultimate product arrives intact in the right spot at the end of the day. Which is what, the dream coat colorized one on the right side is. Each of those colors is a little cell of a pack of a curtain wall unit that'll end up on the job.
All right, so that is everything we had today to present. I guess we'll open it up to facts, or we can spitball it or end early. Facts, sorry, questions.
Time for a Q&A? Okay, yeah, well,
It says we
thanks.
have 5 minutes and 51 seconds.
Perfect. So I can be the mic runner as well. So, oh, you have one. Oh, perfect. All right. Well, I have a question. I can start with a question.
Go for it.
Well, first of all, thanks for that presentation. That was fascinating. And it'll obviously be a very beautiful project and significant contribution and a real benchmark to show what's possible in Toronto. My question on a detail level, sills, sill drains, sills, how did you folks handle that?
Sorry on that?
Sills?
Window sills. Yeah.
Drainage of the window sills.
Oh, drainage of the window sills,
Yeah, like
yes.
is there like a sill drain?
Yep,
or
sorry, I
flash
missed
and
drainage.
later?
I'm with you.
Drainage,
So,
drainage.
Yep, the undulating shape on the window sills on the horizontal panels have some clearance around the perimeter to the face sheet, so there's kind of a naturally built-in drainage system around the perimeter. And then at the deeper areas where ponding could be a concern or wind-driven rain ends up sitting on there during maybe a temperature change, there are drainage holes on the top edge of that windowsill to allow the water to drain through the panel out on the facade down below and ultimately off the building.
They're effectively rain screen panels. We've got a fully sealed back pan, which is your air and water barrier inbound of mineral wool. And like Richard said, there's weeps sort of either side of the top of the panel that allows the moisture to vent through that rain screen effect.
Any other questions?
All righty, that's it.
Okay.
Thank you, everyone.
We'll end on drainage. Thank you. Sorry, I have been asked to also remind speakers to make their way up to the front for photos if they haven't had them taken yet. And I think the folks at Zak also have plaques for all the presenters today.
And please give Tomer a big round of applause for keeping it going today. And thank you all so much for coming out. And we're going to make Toronto an annual event, I think. So look for us again next year. Thanks so much.